All right, good morning. Welcome to KiCon North America 2025. I really appreciate you all being here. We have a number of people, I don't know if you saw on the way in, our badge desk is still a little bit full, so we have a number of people rolling in as the morning goes on. My name is Seth. I'm one of the organizers for the conference, and we are back in North America for the first time in 6 years. So, which is fantastic. So I hope that you really enjoy this conference, that you get a lot of useful information out of this. I wanted to thank particularly the staff at the Qualcomm Institute here. They have a fantastic space, and they've done a lot of work to really help this event be successful and be as comfortable and enjoyable as it is. So in addition, the University of California, San Diego, and particularly Karcher Morris. Karcher, if you can wait, there he is. So he has helped us locally on the ground get all of this together, and we have a number of UCSD students doing volunteer work around here with us to help this event come off smoothly. During the day today, we're going to have 2 breaks. You can find the schedule on the Pre-Talks website. This is linked off of the KiCon website, so kicon.kicad.org, and you can find the schedule off there. We are generally following a 2-2-2-2 format, so we'll have 2 talks this morning, then we'll take a quick coffee break. We'll have 2 talks late morning, break for lunch, 2 talks in the afternoon, break, 2 talks until we finish. So we'll be doing that today and tomorrow, and then we'll have lunch out here in the courtyard. And tonight we'll also have a reception from 5 to 8, which will include some dinner. So we'll get a chance to chat with speakers who you heard today, talk about interesting things that are interesting to you, talk about KiCad if that's interesting to you. It's interesting to me. So feel free to pigeonhole myself. Wayne, I see Mark Roscoe here as well. I think Graham is floating around. Oh, there he is. And so there are a number of KiCad developers floating around. Feel free to grab us, ask us questions. I wanted to talk real quickly about why this event and KiCad in more broadly is important. And so to sum it up, I'll put it this way. KiCad is the sole inheritor of a massive oversight. And that is that we are focused on one audience only. We are focused on the people who are using KiCad every day to get their jobs done. And this is shown in our choices in how we build the software, how we interact with our community, and how we choose to create a larger system that fosters the growth around the world of new engineers who are going to be the ones who are building the innovations that we look for to make our lives better, the innovations we look for to solve problems, the innovations that are going to be the ones that we rely on to make our system, our world better. And that can't happen without a focus on the experience of using that software, using that creative tool that all of us contribute to. We contribute to it by building the code, by writing the documentation, by doing the bits and pieces, doing the translations, doing the artwork, designing the UI that go into how it's used, but this is a half job. And the other half is the people who use KiCad every day. That's you, that's the engineers, that's the designers, that's the makers, that's the students, those are the people who are going to make KiCad actually useful, make it a tool that can build something out of nothing. You are creating actual art. And one thing that KiCad does better than any other tool out there is we engage with our community. And we engage with our community through KiCon, we engage with our community through the issue tracker. If you're not on the issue tracker, you should definitely be on the issue tracker, because it's a great way to talk to the rest of the community and design KiCad for the future, because what happens in building KiCad comes out of the professional engineers and the professional designers who go out and say, this is something that I need to do my job better. And that interaction allows us to go out and build that for you, to create that system that allows you to do your job. So one of the things that we face in open source software is a question of how do we endure, or do we endure? And so this question is not usually asked of commercial software, because there's a commercial motive there. So the assumption becomes that this commercial motive is going to drive you forward to endure. For us, we look at this in a different way. KiCad is 32 years old this year. This is, it's a milestone. Well, it's a nice milestone because it's being geeks. It's a nice round power of 2. So we celebrate this milestone. KiCad has existed for decades, and we are going to continue to exist going into the future. But what that mean that might be in a different form, and the confidence that we can give in how KiCad exists allows businesses to plan around KiCad, allows businesses to create their work around KiCad, because they can look at it with confidence and say, this tool is not only going to exist going into the future, but it's going to have the same purpose going into the future. It's not going to suddenly change to a subscription model, for example, going into the future. So I bring up endurance because some of you may or may not know, but right now we're in the middle of kind of this season where we're halfway in between these two major. I'm going to go off on a tangent here, but there's two large Jewish holidays that were right in between. There's 7 weeks in between, and we're kind of counting days along there. And today is the 46th day of this Omer counting. And this is we talk about different ideas on each day. And today is the endurance of sovereignty. And KiCad exists as a sovereign, as an independent, as a program that is not tied, is not dependent on these external forces that are not relevant to your design work. And how we endure in that, Wayne and Mark and Graham and myself and all of the KiCad development team, we all work every day to make sure that KiCad is not one person, that the bust factor in KiCad is very high. A bust factor is how many people can get hit by a bus before the program falls apart. Our number is very high. There is no one part of KiCad that will fall apart if one person is unavailable. And buses are gruesome, so let's just say that they get an offer that they can't refuse, and they move to an island and throw their computer in a waterfall and never touch electronics again. We're not going to follow. We're still there because we have these layers of backup, and we build more each day. Wayne and I have built out KiCad Services Corporation. This is our corporate arm in the United States that provides for interface, that provides support to the KiCad project. We sponsor things like KiCon. We sponsor development efforts. We sponsor documentation and design efforts to make KiCad better. This year, we're expanding into Europe. We have a European corporation that we're standing up as well. And we have an affiliate in China, Washoe, who is building KiCad and developing KiCad in China as well. Each of these independent entities is providing redundant support to KiCad. So at the end of the day, we, and by we I mean all of us as the KiCad community, are going to be here next year. We're going to be here the year after that. And every year we're going to be a better program for you. We're going to be a better program because you're here, because you're contributing, and because we're working to build out this system as the best possible EDA platform for businesses to use going into the future. So thank you for being here, and I hope that you have a useful, informative, and enjoyable conference. So thank you. Oh, I almost forgot, housekeeping. Bathrooms are down the hall, all the way down the hall on the right, and then if you have any questions, please do stop by our wonderful sponsor tables out front. Our main sponsor is Circuitly. They're down at the end. They have a very interesting program that they are tying into or providing interfaces to KiCad. And then, of course, DigiKey and Sierra Circuits are here as well. And please do ask them some questions. I know that they are a wealth of useful information, and so thank you to them as well for making this possible. So with that, we have a, let's see here. Our schedule has our next speaker as Morgan, so we'll just kind of roll right in. I'll stop real quick. If there, for each talk, we'll do a Q&A session at the end, and we have 2 microphones on the side, and we'll have some folks walking through the audience to pass the microphone around, so do feel free to raise your hand. If you're watching on the live stream, you can type your questions into the live stream, and we'll relay the questions to the speaker as we go along as well. So do feel free to ask any questions. So with that in mind, before I call up Morgan for his talk, are there any questions that people have about KiCad, about our direction, how we're structuring this as an entity going forward? Oh.
So how do you plan on scaling KiCad Services Corp? Like, how many engineers do you plan to bring in, and like how does that scale up past, I think, the handful of people who I think are working there now?
Yeah. So the question is how do we plan to scale this to support a larger community as we grow? Is that a fair restatement? Okay. Right now, we're in the process of hiring people to build out that support in the United States. As I mentioned, we have branched out. We're starting a European arm as well, which is going to have independent engineers working for the European arm as well. And as we do that, our customer base is going to be split as well. So how we build up the individual support and development efforts are focused on building local talent and local support options. So by building up individual efforts in separate parts of the world, we are able to coordinate a number of those development efforts with larger support streams. So in the one thing that we do avoid is we do avoid the sort of VC pathway, because, and this has been a conscious choice for us, because a venture capital, although it does infuse and allows rapid scaling, has required exit points and exit timelines. When these desires do not necessarily align with the needs and desires of the KiCad user base. And our mission, as we have defined it for both KiCad services as well as KiCad Europe, is to support our community and support the development of KiCad. This does mean a slower growth path than if we brought outside funding in, but it focuses our mission directly on that development, and we think it provides a more stable, long-term view on how the company grows and the support that we're able to provide KiCad. So the answer is slowly, but focused in each market and coordinated to work toward a common goal.
You mentioned that you're organized in order to survive. So what is the legal structure behind KiCad? Is it, I mean, in the U.S. it might be a nonprofit organization. I mean, how is it organized so that it can survive even if it were under attack?
Surely you're not prescient here. So the way that we have organized ourselves as independent entities in multiple jurisdictions provides us with a number of overlapping magisteria, we'll say. So our European arm is organized under EU law. KiCad Services in the United States is a California public benefit corporation, and this with a direct mission to support the KiCad community. As we spin off support for European customers, KiCad Services is looking to reorganize itself as a not-for-profit. At the moment, we are the California Public Benefit Corporation status does not confer a tax differential, so people can't deduct their donations to KiCad directly because they either go to the Linux Foundation, which manages our trademarks, the KiCad trademarks, or to an account that's managed by KiCad Services, and neither of these are 501c3 organizations. By reorganizing under 501c3 status, this would allow United States taxpayers to deduct donations to the KiCad project. So once we have moved the international operations out of our purview, then we have an easier method of approaching that. So from a legal standpoint, existing in multiple jurisdictions provides fallback development options when we may, if there are legal, I don't want to say legal attacks, but if someone decides, our code base is open, so it's very easy for someone to look at it and see if there's anything that we have done improperly. And so we're very fastidious about making sure that our development process is open and above board both in the United States and in Europe. Where those conflict are generally around how we interact with other platforms. So as we build importers for other EDA tools, we have to be very careful that we're not using other EDA tools to build those importers, because this goes against their end user license agreements. And so we build up basically these firewalls of separation, and the code that we develop ends up being uniquely KiCad and can be verified in that manner. But that doesn't mean that someone won't make an argument that it's problematic. And the argument itself can be, as you're aware, I guess from your question, the argument itself can be damaging. And that what we look to prevent that is both building these kind of multiple organizations, but also we build relationships. We have relationships with people at Altium. We have relationships with people at Cadence, and we look to build those relationships such that our existence and our system is beneficial to them, because they need engineers. If they don't have engineers, they don't have customers. And their new engineers aren't, there's a limit to how many people can be trained on a $10,000 platform. And we provide a good way to build our talent pool, both in the United States, because we're talking about in KiCon North America here, building the local talent pool increases the number of engineers that are out there, increases provides a increase for the number of potential customers that they have. So KiCad, although their advertising arm might not agree with this, KiCad is incredibly beneficial to each of these major EDAs, and you can see some of these light shifts. We're not they're no longer advertising that that KiCad is a bunch of basement dwelling wannabe hacks. They're saying, KiCad's great for when you start out, but when you get to the big boy tools, come over to us, sort of. Right? They've kind of shifted their advertising away from attacking KiCad to saying, KiCad's this gateway drug. And part of this is about building the relationships. So we don't just want to build relationships with our customer base. We want to build relationships that build the entire engineering community. And as people view us as a benefit to the entire community, that's when we are safest. That's when we are the most able to guarantee our long-term success.
I was just curious if you're doing anything to get into the schools more. Maybe you're already doing it. I don't know.
The question is, are we doing more to get KiCad into schools, into educational institutions? So one of our projects this year is developing curricula at the university level. So if you are watching the stream, or if you are teach a class on electrical engineering, on circuit design, on a class where you need to use EDA software, we're interested in supporting that. So how we support that is by building freely available curricula that match a 3-week subsection of a course, a 10-week full quarter course, and then a 15-week full semester course. By building out those curricula based around current KiCad standards, we are hoping to provide an ease of transition, both for new instructors coming in as well as established instructors who are teaching their classes, but might want, they have new students coming in who want to use their Macs, and that's a problem for major, or they want to use their Linux laptops, or they want to be able to use their software at home, and not on a dongle protected school machine. So we think that by building out these opportunities for instructors to easily transition their courses or integrate some KiCad content into their lesson plans, we think that will have a positive impact. And if anyone is interested in testing out these lesson plans with me, please do get in contact. I'm Seth at KiCad.org, and send me a note, and I'll have you on our first test system. Okay, so lastly, so this is these are our KiCons around the world. I mentioned that this is the first KiCon in the United States in quite a while. That's because the United States is a really hard place to run conferences. Which doesn't mean that it's not worth it. It just means that we need to put a little extra effort in. So these are KiCon Europe and KiCon Asia. We run these conferences, if you are interested, in Germany, in Europe, and then in Shenzhen in China for Asia and the Pacific Islands. We have a really fantastic group of people who work with us and help to put these events together. Every year we get bigger. Every year we get more interest and more interaction. And I think that you'll see why as you experience this conference this week. And I hope that you'll spread the word. And if you're interested in any international conferences, the content is all local. So as we go around the world, the content and the concerns are highly localized, and it is fascinating to see how people are using KiCad to solve their the problems and the opportunities that are presented in local environments around the world. So. With that, thank you very much, and I'll have our next speaker, Morgan, come on up and get plugged in for turnover. So. Last minute.
I'm just finishing the talk
Okay.
right now.
There we go. All right. So
I tested out earlier.
okay,
I
you
think
got
I'm
it.
done.
You
Yeah.
got it. Okay, I'm just going to shut this down then. And go ahead.
That looks about right. How to do, everybody? And also, thank you to Seth, and you're making me very nervous when you started calling my name 30 minutes ago. Like I said, I'm kind of finishing the talk right now. And also good news with that, I doubt I'll fill my whole 40 minutes, so we'll get to the coffee break early. So introducing myself, I'm Morgan Allen, longtime professional programmer, about 20 years experience. I started as a front-end developer 20 plus years ago, a lot of JavaScript and web design. About the last 10 years, I've been mostly exclusively a Python developer, focusing a lot on back-end and specializing in Django projects. I've also been a long-time fabricator, including I worked for many years as the lead exhibit fabricator at the Chabot Space and Science Center in Oakland. And it was during my work there that I really started pushing my use of FreeCAD, jumping into a lot of the internals, programming scripting. FreeCAD uses Python for its scripting interface, and doing a lot of CNC work as well, using the Path workbench, now called the CAM workbench, and some minor contributions, particularly to the CAM workbench. Today I'm going to talk about KiConnect. It's a FreeCAD workbench that utilizes the new KiCad 9 API to do interactions, bidirectional interactions between FreeCAD and KiCad. See kind of a demo running in the background where you can see edits going on, and the far right there is actually KiCad in the background. You can see that updates work in both directions. Bit more about, like I said, I've been doing fabrication with FreeCAD for a long time, particularly a lot of CNC work. I am an enthusiast of beverage assembly robotics. This is called the Barback 2.0. This was completely designed in FreeCAD, CNC'd out. It's been fabricated and it's made entirely out of plywood, designed in FreeCAD and CNC'd as well. So all G-code generation is done in there. And had the great pleasure of attending Robo Exotica in Austria last year, and we took a pair of the barbacks and had a really great time with that. Then general FreeCAD, additionally FreeCAD ecosystem. I also work on a project called the FreeCAD Parametric Web Viewer. This is a website that I'm building to view FreeCAD models. Being able to present your work to clients was the particular motivation. But unlike your 3D printing websites, Printables and older Thingiverse, this one actually extracts parametric information out of your model and allows you to do updates on the fly. So things like the SMD reel, you can define all of your diameters and how big of a reel you want, export as an STL, and do a 3D print. Had high hopes to release the new version of this before the conference, but we didn't quite make it. So next couple of weeks, this will be being released. My motivation behind KiConnect, I'm not a professional PCB designer. I've been a hobbyist for a long time, and I tend to make weird and unnatural circuit boards. 2018, I decided to build the ultimate shrine to dying batteries. This is called the Cacophony. It is a 13-piece PCB, and it actually is about 13 millimeters. It's exactly 13 millimeters deep. It has the LEDs that you can see are shining downward into it. So all but one of the 13 boards have some active element on them. The front bezel has LEDs shining in. All of the side pieces have buttons, and it was a highly interactive badge. This was, obviously, I designed this in FreeCAD and KiCad. And as this project progressed, I kept finding myself backed into a hole where I wasn't able to make updates that I wanted, particularly when it came to panelization. So as the boards got panelized together, I was really stuck where I couldn't make major changes to the outline because then I had to repanelize. And things weren't working out. And in fact, I spoke at the first KiCon in 2019 in Chicago. Where did we go? What are we doing here? Oh, come on. There we go. Oh, boy. We're not going through this whole talk. Sorry, everybody. We're going to hit refresh. So my 2019 talk was about the headaches in which went into doing this design and a lot of the shortcomings in this process and where I wasn't able to do the things that I wanted. And as part of this talk, I made a threat that I was going to come back one day with tooling. And I've several failed attempts. Due to particular limitations, I never was able to really build out what I wanted. I got some things working, but just never like the complete package that I wanted. And so with the release of KiCad 9 and the new API and an API that could be relied on going forward for consistency, the time was right to take another crack at this. So in FreeCAD, if people have not used FreeCAD before, it's made up of workbenches designed to focus on one aspect of work. I've already mentioned the CAM workbench that I use a lot. This is to take your 3D models and produce G-code for a CNC, or maybe even advanced 3D printing. There is architectural workbenches that follow international building codes, so you can do legitimate professional architectural work with it. There are workbenches for, what other workbenches do I use? Several different ways to do solid modeling. They're all written in Python for the most part. There are some facilities to write C++ add-ons as well, but for the most part, you can accomplish most functionality with just a Python workbench. Workbenches are largely split into two parts. One aspect is to actually control your objects that you're generating, and then the other part has more to do with how things are displayed. Do you want wireframe? Do you want shading? And that part's not actually used that much. And then there is a very powerful feature built in. They're called Python features or Python feature objects. And these are programmable entities in your model. And KiConnect utilizes this heavily. Customized sketches for their outlines, API connection to KiCad, and just the overall control uses many different Python features. You can have customized groups, customized sketches, custom parts, and they're all generated using Python. And under the hood, this is what is being used. Prior to this, there were some facilities to do this before. None really worked out for what I was trying to do. And effectively what I was stuck doing at the time was just importing and exporting outlines. And when going from a three-dimensional assembly in FreeCAD to a panelized board in KiCad required a significant amount of manual intervention. I attempted to automate some of this stuff with customized footprints that would signify where a bridge would go. It was very delicate. It was a process that didn't work all that well. Anybody who has used FreeCAD in this method has used KiCad Step Up. This is a workbench that's been around for many years. A lot of powerful features. Too many features, I think, in some ways, and it has some inherent problems. They ship their own parser, so they're actually parsing KiCad files themselves, which is error prone because every time there's a new release, and particularly releases of 8 and 9, where many primitives were introduced, things like arcs and circles and rectangles, rather than just line segments, required a lot more parsing. So updates, thankfully that team there is very responsive, but it is still an error-prone process. And that's kind of it. There's not really a lot of other options right now. So again, like I said at the beginning, with the release of the new API, I thought it was a really good opportunity to really jump back into this project. So from the website, the KiCon why are my slides not updating? KiCad Python project is a set of Python bindings to the KiCad IPC API, officially maintained by the KiCad development team. And a huge shout out to John Evans, who's doing a lot of this work. Yeah, basically wouldn't be possible without. John's been incredibly responsive too for helping me directly getting some features rolled into this. To make this workbench possible. Simmer down. Prior to the new API, we had the KiCad Swig API. And if anybody has used this, you'll understand that it is also problematic. Shares a lot of the problems that KiCad Step Up had, where with new releases there were unexpected changes, particularly because Swig bindings are auto-generated. So you're not, with every release, you're not quite sure what the API will look like next time. They're also Python only, and already now, there are at least two bindings that I know of. For the version 9 API, there's the Python API that I'm using, and even prior to that, I believe the first one was a Rust API. And then just inconsistencies, and this is about the how every release came out. These APIs were auto-generated, so you have issues with things changing in unexpected ways. There's been a couple libraries out there that have attempted to address this through version checking and creating a consistent API on top of it. These are also not without their problems, because with every release they need to update and make sure that they're actually working. So there's a general theme here. I like Python. FreeCAD likes Python. KiCad likes Python. So bringing everything together, Python all the things, and that's really working well for what I'm trying to accomplish here. So KiConnect, there's a very pre-release version of it out right now. A lot of this talk is for a call for support and call for people to look at it early on. Again, I'm not a professional designer. I have niche features that I'm after, but I would really like to broaden the feature set to bring it to a more professional audience and just make sure I'm providing features that are actually useful to a broader community. So with that, I've got what works. So importing board outlines, as you saw that background demo earlier. Pulling in board outlines was the first feature. It was surprisingly easy to implement, and really got me motivated, got the ball rolling to continue with this project. Footprint pads work. Pulling out copper pads in particular was very straightforward. Again, just very easy to set up in FreeCAD as well. We can import the part actual 3D models for everything. And I can push outlines back into KiCad. Slight caveat there right now. The Python API interface the current release does not work to do this, but when the 0.4 release comes out, all of the current bugs are fixed in that. So hopefully we'll see a lot of that coming out very soon. And especially with the KiCad 9.0.1 or 0.2, I think, fixed several bugs on the back end of the API. This is kind of a broad demo showing much of the features. It's a little bit dated now, but shows off. There you go. All the parts. We see copper pads. It's very fast. The slowest part of this is actually importing those 3D models. And then we can see we've got all of our references to our parts. Here is all of our individual nets. And this is a place that I'm really interested in getting feedback in, is how does it make sense to lay these sorts of things out? Do you organize things by net? Do you organize things by individual pad? There's a couple different options, including being able to view them in multiple different styles of view. Where are we going next? Okay, so current limitations. So as I said, this is very pre-release. There's a list of issues that are probably about equivalent to the lines of source code. Not quite there, but and then the great thing is like a lot of these problems are very solvable. There's known solutions to many of them. They just haven't been implemented yet. I'm trying to go for broad surface area at the moment to really get that initial feedback. So limitations are I'm only supporting polygons at the moment, which from what I've seen, many people have not moved to polygons yet. A lot of line segments. Again, solvable problem, because I believe the polygons weren't introduced till 8, maybe, I'm not quite sure. Solvable problems, taking line segments and organizing them and turning them into polygons is doable. There's nothing really there. Same for internal cutouts. I just, bounding box checks, there's nothing crazy about that. I am extracting tracks as well. And they just need their lines thickened. So things like that. And then back to back to what I was saying earlier, pads and tracks are there, but I'm not quite sure what the best way to organize these things is. So that's a big part of where I'm looking for community feedback and just early eyes on this project as I move forward with it. General broad plans. Again, like I said, I do kind of weird 3D stuff. So that's my goal. Multi-board support. That's a huge thing for me. There are currently limitations in KiCad itself that make this difficult. Namely, you can't open multiple documents. I hear that's coming. Tabs are coming, maybe. There's going to be some support for that in the future, I believe. So that will ease a lot of that sort of development. And beyond my weird needs, like I believe this is a legitimate professional need. If you've got multiple boards and you want to lay them out into a project, this currently can be done. I do support it already, but it requires you to open each of your projects and then import. And if you want to push back, you need to reopen that other project. So it does work, but it's a little bit finicky. And I'm hopefully not speaking too broadly or uninformed, but I've heard that the API, the KiCad CLI at some point should support the API functionality. If that comes through, that's correct? Cool. So when that comes around, the idea is just to launch the CLI in the background. Do your imports and your exports that way. You won't even need KiCad to be running if you don't need it. And then for the professional crowd, the thing that I really, really want to support is Flex PCBs. So this is a huge underpinning part of multi-board is if you're doing an FPC connector, some sort of custom Flex connector in between boards. FreeCAD already has a lot of facilities built in. There's a curves workbench built in. And then there's another one called Surface. And these are both for working with non-planar three-dimensional surfaces. So those are the sort of things that can be utilized to do the Flex Connect style of stuff. And not on the list here is another thing. I've already started dabbling a little bit with panelization built into here. This is one of my big goals. I'd like to work on something in a three-dimensional aspect and then be able to just switch views and it's flattened out and it's panelized. If anybody's used KiKit for panelization before, that's also written in Python. So my plan is to integrate that into this workbench. Licensing, compatibility, permitting. This is also licensed AGPL2. That's a requirement to get anything included into FreeCAD. So that's the license that will be used going forward. And that's kind of what I got. I'm about 10 minutes short, but I think that it summarizes kind of what has been going on here and what my plans for the future are. And with everybody's feedback, I think that this is an opportunity to build a really great tool going forward. Now we can get questions.
I don't generally do the ECAD to MCAD so much because the tracks, don't work very well.
Sure.
Most export well if you're looking at particular layers, copper layers. Like for test pad points for mechanical alignments. For the bed of nails. That's helpful. But from a visual, especially going to MCAD, just the look, with silkscreen is awesome.
Sure.
And just the test pads in terms of test points. I don't really need it's great that you did the, the component test pads in general, but that's kind of sort of unnecessary, perhaps. So I would think silkscreen is
Sure.
should be.
So generally, the comment question is the lack of silkscreen, and that's just not implemented. There's not. Again, this is a solvable problem. The information is all there. I'm already doing, extracting information and drawing outlines. So that's just a very doable. Again, I'm going for broad surface area first, just trying to get a lot of the functionality done. It's on the list, and it's not a difficult thing to implement. And then about parts, for me, parts clearance was very important. So that's why pulling in the 3D models is critical, because then you can, in your MCAD design, you can see those clearances. Bed of nails sort of thing, pads are already being extracted. So you can just reference those. FreeCAD has a concept called the shape binder, where you can be working on one solid or one body, and you can reference features in another one. So in something like that, you could go into your combo view, the hierarchical tree, select all of your test pads, hit shape binder, and now you've got a virtual connection. The really cool thing about this as well is that they automatically update. So if your test pad gets moved around, it will automatically reflect in your new body. So your bed of nails will basically always be up to date.
Thanks.
Do you have in mind that the tool either is mostly now or will become usable without Python programming directly, or is it intended to be a tool that a Python proficient person would operate?
Nope, it's just written in Python. Ideally, nobody would. You would never have to use Python yourself. But one of the really neat features of FreeCAD is you effectively every line of Python is run on its own, and you actually get a log of everything that's happening. So let's say you wanted one really small part of what I'm doing. You can pull that out and write your own macros, is what they call them in FreeCAD. So you could write your own macros to use very specific parts of the workbench, but it's absolutely not required. So up in the back? No.
So you said that you do support multi-board, but on the KiCad side, it involves multiple instances or multiple imports. On the FreeCAD side, are you using the assembly workbench to assemble these, or are they just individual bodies that you shift around?
As of now, they use what's called the attach extension, which is the basis for assemblies. But the idea, I want to be assembly agnostic. So yeah, as of now, the parts, I had a demo here somewhere. Kind of relevant. So there is a parts group, and that is like a virtual object. And then all of the parts within are using an attachment offset to localize themselves there. But within FreeCAD, and this was one of the big goals, and this is for me personally, one of the shortcomings for our KiCad Step Up was it's difficult to use the boards complete in another assembly. And from the very get-go, I was testing that, and I test in the new built-in assembly workbench, and then my preferred workbench assembly is Assembly 4, and I've tested in both of those. And the whole kit and caboodle, the whole board is able to be included in assemblies, including arrays. So if you have, say you're doing something with a bunch of LEDs built into it, and you've got a small custom board, you can array those out. And then it works for all of the individual parts become their own linked references. And if you move one, so say you need to do a little bit of a tweak, you can move one, it updates the original that everything is linked to, and then you can push that back as well. Oh, and also a kind of a follow-up earlier about multi-layer. Right now, a board itself is a pretty abstract object, and I did that keeping in mind for multiple stack-ups. So a quote board could be just an individual layer. I think one way in the back there, yeah.
Thanks for the presentation. Looks like a really cool project. Any thoughts on using IDF or IDX files for broader ECAD, MCAD compatibility with other systems than KiCad and FreeCAD?
No. I actually don't quite know what a lot of that is, so yeah. No, and again, community, yeah. I hope to support a broad set of features, so that's if somebody were to come at me with a pull request, that's I don't say no to other people doing code for me.
All right, cool. Maybe I'll take a look. Basically, IDF and IDX, they're interchange files that allow all sorts of ECAD and MCAD systems to talk with each other with board shapes and component placements.
Cool.
So that might be kind of interesting.
Yeah, very. It sounds neat.
What is the relationship that between KiConnect and the KiCad step up to KiCad? Is there do you have a relationship with Maurice or exchange of ideas, or are you working completely separately on this project?
It's completely separate. I have some bug fixes here and there with KiCad with Step Up. I've used it for years. The one big difference is I have no intentions of supporting other APIs. I'm not going to go back to the SWIG. I'm not going to attempt to support 6 that some people are still using. Step Up has very broad support, and there's even talk they're going to start supporting 9. I don't intend to do any of that. I'm only going to use the API going forward. Yep.
Yeah, you kind of captured my attention with the bed of nails talk. And, the problem I'm trying to solve with that is I generate a board, it has to be manufactured. I need functional test, maybe in-circuit type test. Do you have any way to automate that? I don't even know how to approach what you've offered here.
Mm-hmm. Yeah, so like I mentioned before, there's something called a shape binder. So what you could do is you would select all of your test pads and you would make a shape binder for them, and that would be your test bed. Your test bed would be referencing the pads on your board. And what are you doing? Just vias to put your pogo pins in, or through holes to put your pogo pins into. And because they're a direct reference to the original test pad, anywhere that pad gets moved, that reference is always just updated. So in that case, all you would really do is maintain your board outline, put your test parts, whatever you've got an IDC header or whatnot, to actually connect to your test system. And then you wouldn't mess with the test pads at all. You would just utilize that shape binder to always keep it up to date. And then I don't think people are going to be doing a lot of track manipulation in FreeCAD. I don't think it makes a lot of sense. So then that's the only thing you would really need if you made a drastic change. That's the only major update you would need to manually do. But hey, maybe we can call the auto router from the API. Everyone loves the auto router, right? But for something simple like that, that legitimately could work.
Do you have any documentation about how to get started on that?
No, the documentation right now is just literally build documentation. This is still very, very pre-release. Just really trying to get a feel for what this should look like, and particularly what this should look like to other users. Documentation will come. And again, you can't really use this right now just due to the fact that the KiCad Python API has several bugs in it. So until the next release comes out, this won't be really broadly supported. So it's very much in developer mode at the moment.
That last question was similar to what was online on the YouTube livecast. Alexander had a question related to, do you have any plans to have a screencast explaining how to use it, how to set up FreeCAD and KiCad, or some examples?
Yeah, so I've already got some examples built in, just kind of my daily testing, or as I'm doing development. I hope that this starts getting broad enough attention that that's those sort of things. Yes, doing some videos on how to use and doing better documentation is all in the pipeline.
Okay, any other questions?
Okay, thank you very much, Morgan.
I almost made my full time. Thank you.
Okay, so we have a short break. There should be some coffee and snacks out in the hallway to recharge your batteries. We'll reconvene here at 10:50 with Wayne Stambaugh's talk on the status of KiCad. So please feel free to stretch your legs, grab a nosh, and get some coffee.
We ready to get started? Yeah, it might be underneath my power supply.
Yeah, I know, you're just jumping on it. All right.
All right, we ready? Okay. Well, welcome everybody. Welcome to KiCon. It's great to be back after a long absence. 2019 was the first one, so it's nice to be back in front of the American audience. So for those of you who don't know who I am, my name is Wayne Stambaugh. I'm the lead developer for the KiCad project, and I've been in that role since 2011. And I joined the project in 2007, so I'm one of the old timers with the project. Probably there's only two people that were there before me, and that was JP, the founder of the project, and Dick Hollenbeck. And then we were probably the first three to get the ball rolling, and the ball rolled pretty quickly to get us to where we are now. So today I'm going to cover where we are in the project, what's going on, what's new, what's coming up in the next release version of KiCad, and gives me a chance to say thanks to all the people that make this happen. So without further ado, unless you've been living under a rock, stable version 9 was released on February 19th of this year. For those of you who don't know, we have a release schedule that's supposed to be January 31. We missed that by a couple weeks this year. But we've been doing a pretty good job of holding on to that annual release schedule. So obviously the goal will be to release version 10 in January 31st of 2006. At the end of every release cycle, we have a donation campaign, and this year we had $100,000 donated to the project. The original goal was 128, so the individual donations were a little lower than we were hoping, but we had a lot of people stepped up with companies stepped up with matching donations, so that helped offset that a bit. So we ended up raising a total of 160. We are currently we applied for a NLNet grant. For those of you who don't know, NLNet is a European organization that helps fund open source projects. 2 years ago, we had a $50,000 NLNet grant, which helped pay some of the dev team to work on a bunch of new features for version 9. We made the second round of the submissions, so hopefully that will come through this year, and we'll be able to use that going for the version 10 development. So last year was this year, will be the third annual KiCon in Europe in Bochum, Germany in September 11th through the 13th. So if you have an excuse you want to go to Europe, come to KiCon Germany. It's a little different than some of the other KiCons, but it's a good event. We will also be having our third annual KiCon Asia in Shenzhen, China in November of this year. The date hasn't been finalized yet, so if that's something that you might be interested in, keep an eye on the KiCon website, and that as soon as we have a finalized date, that will happen. We also had 11 new members added to the library team during the version 9 development cycle. It is the biggest growing team in KiCad, so you can thank our lead librarians for kind of convincing people to contribute footprints and to all the libraries. So that's one of the fastest growing parts of KiCad is our library, and our libraries are exceptionally high quality. So real proud of that as a team lead. I'd like to see a few more core team members there, the dev team, but we have quite a few new contributors. So hopefully maybe next year or during this year, the version 10 cycle, we'll be able to add a few more new members to the lead dev team. So the goal is to have 3 KiCon conferences every year, and this is the first one of the year. So if you know anybody or are interested in going one of the other ones, sign up when the tickets go on sale. We enjoy getting out in front of one of the fun things for me as the project leader is to get out in front of a group of people, all of our users, the community in general. It's just nice to hang out, talk with people, and then go somewhere for dinner and a couple of drinks afterwards. I really enjoy this part of the project. I instead of sitting in my office all the time by myself in front of my computer, I do get to, this is one of the things I really enjoy doing. So come out and see us. There's a KiCad store. So if you're interested in KiCad swag, you might have seen some of the dev team got people walking around with KiCad shirts. You can get most of them on the KiCad store. Always like to give a shout out to our sponsors. We currently have 4 platinum, 5 silver, and 8 bronze sponsors. They help keep the project moving. That helps pay for events like this and my travel and what, the team paying to help the team to travel, and we get to meet up once a year or twice a year as a team to discuss development for the coming year, which is always far more productive than doing it online through chat. And if you're interested, there's a page on the KiCad user forum that allows you to follow V10 development. The dev team's pretty good about, as soon as a new feature is introduced into the development branch, they'll either post a little video or a quick blurb with a screenshot. So if you're interested in seeing what's coming for the next release version, you can click on the link and that'll take you there and you can follow along. So I always like to give a big shout out to our platinum sponsors and the people who step up and contribute to the KiCad project. Eisler, Watch You Next PCB, KiCad Services Corporation. One of our goals is to give as much back to the project as possible, and PCB Way. So what came in version 9? So lots of things happened in version 9. We introduced an internal procedure call interface for the board editor API. That was just in the last talk. It's replacing the old SWIG API, which probably will last another version or so, and then we'll deprecate that. You can now embed files into your symbols, your footprints, your boards, your schematics. So instead of having to have them externally linked, which you have to do now or what you had to do with version 8, you can now actually embed those files into your design files. It makes them portable, so you don't have to remember to keep a folder somewhere and archive them and take them with you. So there's now custom ERC DRC warnings and errors. In other words, you can create your own and give them interesting names and uses. It's pretty unlimited. This is what you can do. There's also DRC and ERC exclusion comments. Let's say you add a comment or you have a DRC exclusion, you understand what it is, and you say, hey, this is okay, and then you leave a note for the next person that comes along and tries to figure out why you left that DRC in your design. You can now export the 3D models, including ray tracing from the command line interface. All the editors now support tables natively, so you don't have to manually draw tables with lines and text. So that's available in all of the editors in 9. There's now an output job manager, and for those of you who have fixed output requirements for your manufacturing and your corporate documentation, you can now do that all in one place. And that's in the main KiCad window. This allows you to create a complex series of outputs, and with a click of a button, you can just generate them all in one go. This is one of the things that's been requested forever. That got into 9, was change the direction of the mouse zooming. So you can do that now. I think there's a few other CAD tools that go the opposite way of what we have traditionally done. So that's there. You can now modify the images with a reference point. Before, you can only scale them and it would be relative to where they were. Now you can scale them relative to a reference point. There's a Bezier curve tool now you can draw. I know it's a little light in the image, but there's a complex curve there that you can draw. It's typical Bezier curves, and that's in all the editors, which we supported importing them from other projects for a long time, but we never had a tool to actually use them. But now we do. You can now create component classes in the which allows you to assign a class that defines properties for that class. You can see here in the schematic editor, it's circled by just a rectangle. It's enclosed in a rectangle with a component class object attached to it. And then all that information gets passed through to the board editor, so you can do things with custom DRC rules. Here's an interesting one that a lot of people aren't aware of that was released in 9. There's now a mouse scroll wheel action. So you can use the mouse scroll wheel along with the modifier keys to automatically increment and decrement labels, pin numbers, just about everything in the either the board editor, the footprint editor, or the symbol editor. You can automatically just hold down a modifier key. It's a great shortcut. So that's been available now. That's been available with release in 9, but it's kind of not obvious that it's there. So one of the big new features, if you do a lot of repeated layout blocks, is multi-channel design. This was implemented in 9. You have shared sheets. Those of you who are familiar with hierarchical sheets and complex hierarchies, here you can see there's that you have identical. Those are the same sheet shared. What you can do is map them to a block of. So each circuit inside each sheet gets mapped to a block of footprints and all the objects that go with that. They're grouped together as a single group. Then you can go back and fix the groups and point back to a reference. So there's the groups. And they'll point back to the reference. There's already, to your left, there's a reference channel already laid out. He'll select that, lay out all the other, mirror all the other ones as the same. You now have 4 identical channels. And then you just place the whole channel as one block and then do the rest of your routing. So if you have a lot of common, which does happen quite a bit on lots of designs, that tool is now available. So what's new in the schematic editor? Well, there's now in the past, you've had to synchronize your sheet pins and the hierarchical pins in your schematic manually. In other words, you had to add them to the schematic, come back out, then manually place them in the sheet. Now there's a single tool which allows you to go back and forth without having to go up and down the sheet hierarchy. It's one tool. So you just pick the sheet. You can add labels and pin, and they automatically get assigned. Then you can go position them on the sheet where you want. So that was introduced in 9. Excuse me. We now have rule areas. In version 8, you could add a rule like RAM adder, but you had to add that individually to RAM adder's a net class. But you could add that to each individual net one at a time, right? You could do that. I want to assign, each one of those wires. Now you just draw a rectangle that touches each one of the wires, and now you can assign all 8. In this case, it's 8 channels, but obviously for more complex designs, that could be 16, 32. So it saves you a lot of time instead of having to do it one by one. There's now schematic design blocks. You can save your designs into a little subcircuits into a library, and I'm going to have a little bit more comprehensive demo on how to work on my talk. Is that tomorrow? Yeah, that's tomorrow. But so this allows you to save libraries of proven designs that you can reuse in any other project, any other schematic. We changed the net navigator to show all nets now. The original design was way too not performant enough to handle this for complex designs. It still may be. I know some people in here have some designs that push this to its limits. But now you can see all the nets in your entire schematic, and you can, when you click on it, it'll take you to that net, that object. So like if you go to symbol L1 pin 2, you click on that, it'll show you the place in the schematic where that exists. We added selection filtering now is available in the symbol and the schematic editor. For those of you who do lots of board designs, you know how this works. You just enable the things you actually want to select. You can draw a box around everything, and it'll only select those types of items. So that's now available. We also added, this feature was so you can add parts or symbols to your schematic that you don't want to simulate. In other words, you don't want to include them in the net list for some reason. And then, so it doesn't get passed to the SPICE simulator. We also, in 8, we had do not populate for individual symbols. Now you can do not populate an entire sheet. So you see on there, it's an option in the sheet properties. And what will happen is when you generate a BOM, anything under that sheet won't show up in your bill of materials because it'll be considered do not populate. We had a couple new electrical rules checks. If you have local and global labels with the same name, that can cause problems. It catches people off. So there's now a warning for that. There's also a warning if you have dangling ends. Before, we would always show just a little empty square just to indicate that it was a dangling end, but now it will throw a warning. You can now assign multiple net classes to a single net. And the reason you can do that is you can have like a net class that has one property that you want to use in a lot of places, and maybe net class 2 just has a property for that particular net. And then it merges the properties for both net classes. So you can do stuff like that. Prior to that, the schematic editor would complain if you tried to do that. There's now, you can highlight by net class color. So if you assign colors to your net classes, you can have different colors for different nets. This is just a visibility tool for people who have really, really complex schematics. It helps make things a little bit easier to see. You can plot or not plot the do not DNP indicators. Some people don't like them on their output plots, so you can turn those on and off. We can now import modules and Eagle schematics. For a long time, it would just ignore those up until now. But so version 9, you can. So for those of you who have a lot of legacy Eagle import or schematics, you can import them without them being broken. We now have in the symbol editor, you can now drag pins and it goes along with the edge of the board. Prior to that, you had to kind of do, you kind of had to do a manual thing. Yeah, so if you just drag like the old way it used to, but if you select the pins, it'll just drag the whole side of the. We've had alternate pins for a long time, but there was no way to know if your symbol had alternate pins. So there's an indicator, that's the little arrow and the arrow underneath it. It tells you that each one of those pins that has that indicator has an alternate pin definition for it, or more than one. And so you can go in and select the alternate pin, and it'll change the name of the pin. We finally fixed a long-standing issue where you had to save, when you use derived symbols, you had to save the derived part first, the parent symbol first, and then you could save the derived symbol into another library. Now, if you just copy it, it'll automatically copy all the derived, the whole parent tree. It'll just copy it over to another library. So what's new in the board editor? There's now a zone manager. Instead of having to manage zones one by one in the schematic editor, there's now a zone manager that allows you to, like, one place, edit all your zones. So you can change all the normal zone settings, and you can you'll get a preview in the preview panel. So you can kind of get an idea of what it looks like, it's going to look like before, rather than do one at a time and then have to go back and do the other one, go back and do the other one. So that's a handy tool. For those of you who use manufacturers that require ODB++ support, we now export all the board stuff in ODB++. The net inspector is now dockable instead of being a floating dialog that can, you have to move out of the way. You now just docks down in the bottom. Like all panels, you can turn them on and off, but it's the same information that was in the old dialog. It's just now a panel. Via tenting control. So we used to be able to tent or not tent, and that was it. Now you can tent front or back. And then there's per, if you look down here in the bottom, there's per via So you can tent the whole side, whole one side, whole other side, both sides, or individual vias one by one. So if that's something that you use regularly in your designs, that's now available. So there's a bunch of 3D model export improvements. You'll notice there's the silk screens and some of the other stuff that used to not get exported with 3D with the 3D export. Now it does. You could also filter. So like say you don't want to export certain certain models like components, and it also supports wildcards. So you can filter those out when you export your 3D models. There's now a DRC for differential pair skew, and there you can see the rule at the top. If you're working with, you have real tight requirements for your differential pairs. We made some significant improvements to the differential pair stuff in 9, and there's more coming in 10. Before you could only have a couple of like your layer presets. Now you can have an entire list of layer presets. So if you're doing a lot of blind and buried vias, and you might want to go from this in2 to in4, you can create that, and it, well, as you're routing, it will go, your vias will go between those two. And you can loop through those. I think there's a hotkey, and I don't remember what it is off the top of my head. While you're routing, and it'll just go through, you can go up and down through the list as you're routing. There's a dog bone shape modification tool. So for any time you're dealing with internal routes, you know router bits can't cut square edges, so we have a tool that you define the router bit size and it'll automatically dog bone your square stuff. So that's what you would actually get if you tried to manufacture it, because you're never going to get a 90-degree corner or like the triangle. You're never going to get that with a router bit. So we have a tool now that generates those automatically. So you can now define an arbitrary reference for the relative position tool. Before you had to just use the grids and the other coordinates, but now you can pick any position. Another big feature that was added during 9 was cursor snapping. So you have indicators that will tell you what you're snapped to. You can see the cursor changes on the circle with the target. Those are going to be snap points. So that makes life a lot easier when you're like drawing outlines and odd shapes in the board editor. So we've had user-defined layers for quite a while, but now you can link them as front-back pairs. So in this case, user 1 and user 2 are now front and back pairs. So the back one will be inverted like any other back layer would be. There's now an outset tool for those of you who design a lot of footprints. This is a real handy helper. You can create silkscreen stuff outset from your other objects drawn. It's pretty handy. It does it pretty quickly. And then you can just, cut out the unused pieces, but it's a time saver. See, it merged them. So yeah, if you do a lot of stuff like this, the outset tool is your friend. We now support pad stacks. This is another one of those features. Not everybody uses this, but a lot of tools do. So when we would import from like Altium or other projects, we would lose fidelity if you were using custom pad stacks. So in this case, you can define any number of any shape, any size, for a stack of for your pad stack ups. It includes custom shapes. This was just a simple drawing, so that's available if that's something you need, and that's fairly new. Next is you can now remove the solder mask over a trace if you have a design where you need to do that, where you don't want the solder mask covering the copper. Obviously, you'll want to probably coat that with something like Hazel or gold plated so it doesn't. But you can do that now. There's a new DRC to check for acute angles if you have strict requirements where in your designs that you can't have acute angles. It will point those out, and then you can set what that angle is if you prefer. there's now DRC clearance indicators. So if you have a DRC clearance error, before you get the indicator, the little arrow at the top in the middle, but it was always hard to tell which one of those and where the clearance problem was. And now, as you can see, as you click on the clearance, it'll show you the indicator where the error is. I know something simple, but was before all our leaders were internal. Now you can define external leaders if that's something you do on your dimensions. There's now an interactive positioning tool. This is really nice. If you can position one object relative to another object, along with offsets, if you so choose. It's pretty handy. There's now creepage DRC check. And for those of you who don't know what creepage is, instead of being by physical dimension, this is by voltage. So if you violate any of those, it'll complain about it. This one's pretty intensive, so if you're going to use it, it's can really slow down the DRC test. You can now define vias with varying diameters. So like the outside, you can have, and you can see how it draws them. It gives you an example of the different types of vias that we offer. That kind of came along with the pad stacks. We now have multi-track drag. Prior to this, you could push one, and it would push all the others out of the way. Now you can drag them simultaneously. We can't route yet, but that's coming in 10, I think. We still don't have the router's a complex beast, so but hopefully we get multi-track route in 10. So we now export 3D. We can now export 3D models in XAO, STL. We always could do STL, BREP, PLY. Most of the formats that OpenCascade supports, we can now export to, in case your company uses those as instead of the classic step file. So you can now chamfer polygons. Before you had to draw the polygon with the chamfer. Now you can do the chamfers. And miscellaneous. We did add some the tolerance calculator to the regulator panel. So that's by no means all of 9. That's a lot of the highlights. There's dozens upon dozens upon dozens of quality of life changes, dialogues, layouts, copy and paste into certain things like that. Were added in 9. So if you haven't updated to 9 yet, I highly recommend you do. It's a pretty big jump from 8. I said the same thing at 7. We just keep going along at amazing clip, and some of this will show that. So between 8 and 9, the 8 and 9 tags, there was 4,388 commits to the source code branch, and that's not including translations. That's just basically C++ code by 32 authors. We are now up to 1.78 million lines code. 150K was added between 8 and 9. That includes 200K lines of comments. So we use Deoxygen to export our comments to a developer documentation. So that's always available if you really want to dig into KiCad source code. It's on the website. The library team's been busy. There was 420 commits. They added 1,485 symbols for a total of 21,748 symbols. The footprint library had 346 unique commits. They added 750 new footprint libraries, and that's for a total of 14,204 footprints. And there was 156 commits for 132 3D models for a total of 683.35. So, and the documentation had 253 commits, and that was 27,760 lines of documentation. To me is one of the most improved parts of KiCad in the last couple of years is documentation. Used to be pretty rough and lots of missing bits and pieces. Not anymore. KiCad documentation is really good. So if you've been frustrated in the past with KiCad documentation and you want to look up how a new feature works, use it. It's really, really well done now. And of course, our translations were nearly 100% translated into 8 languages. That was down from 1 in version 8. And we have 16 languages another 16 languages that are 85% or plus translated. So you can see KiCad's an international project. So anyway, on to V10. So if there's nothing to the right, that means it's probably hasn't been implemented yet. But so it's either gonna. This is not this isn't absolute gospel. So take it with a grain of salt. This is what we're planning to do, but things can change. So custom toolbar layouts, we're going to hopefully finally get that done. I think we're waiting for WX Widgets 3.3 though for that to be implemented. That will allow you to reorganize your toolbars however you want. We want to do a design migration import wizard. Right now, our importers are a bit of a mishmash so like when you import Altium and Eagle and, from all your other third-party projects, it's a little bit of a mishmash. We want to kind of streamline that into a common thing. So we're hoping to get a design wizard because sometimes things don't map perfectly to KiCad, so it needs a little manual intervention. So we want to kind of provide a tool that's, hey, I want this layer to because KiCad doesn't have a layer, whatever, on that Altium has. So it gives you a chance to remap the layers where you want it. One of the things that really has been a kind of a burden is library table management. Right now we only have 2. They are chained. It's just that you can't see it. But we're going to allow library tables to reference other library tables. So you'll be able to build up like a tree of libraries instead of one big flat table and then the project table. That's coming. We want to do a visual diff merge tool for Git. Merging graphical objects as their text is not easy to do. It's hard to look at, oh yeah, I changed the size of that rectangle, without looking at it graphically. So hopefully we can get something like that done. Barcode support, we were hoping to get that done in 9. It didn't make it. Here's one that happened that I didn't even know was going to happen. It's kind of fun how that works. You can now arrange arrays by selection order. So in the order in which you select things, you can arrange them in the board editor from the schematic editor. It's just a little helpful layout tool. If you're doing like a lot of like LED boards or LED arrays, it's a helpful tool. There's now hatches, and so you can draw hatch lines in any object. So anything like a circle, rectangle, polygon, you can fill it with a hatch. In 9, tables can only be rotated right angles. In 10, you can now rotate them at any angle. I'm not sure why you'd want to do that, but you can. You can, and it renders correctly and saves correctly. Altium, so for those of you who've tried to import Altium prior to 9, it's a little bit of a Byzantine process. You have to import the board separately from the schematic, and then you got to sync them up so that the UUIDs in the board match the UUIDs in the schematic, because otherwise you're going to have a mess on your hands. And that process is a little tricky because you can get it wrong. Altium importer has been added now. You just import the entire project and it'll do that for you. It'll do the synchronization for you. We also want to add a importer for pads because we've been getting a lot of requests for that. And somebody wants a Gita project importer. I don't know how many people use Gita, but that's on the list. Okay, so the schematic editor. What do we got coming for the schematic editor? Well, as you heard in one of the earlier talks, there's the board IPC API. We want to flesh out the board editor API to it, the internal procedure call, to have its own set of So you can reach into things dynamically in the schematic editor. So you can modify schematics or change material, fields and all the kind of things that you would normally do in a schematic editing session. Pin and gate swapping. This one's been around for a while. It always keeps getting pushed back. Hopefully that makes it in. It's a common use case, especially if you're using FPGAs. You're constantly swapping pins as you're changing the functionality of the FPGA. Flat schematics. Right now, KiCad only supports hierarchical schematics. There's one root sheet, and then all the other sheets are inside and down from there. We want to, because a lot of our third-party vendors like Altium, they support them, so we need to do that. So when you import, you get an accurate import. So hopefully that's coming. Variants. This has been one of the ones, probably the biggest one, and that's on my list for 10, is variants. And for those of you who know what they are, you basically change, let's say you have a value that you want to change for one, you want to stuff a board with one set of parts and you want to stuff the same board with a different set of values. That's a variant. So that's coming in 10. Stacked pin definitions. Right now, in order to draw complex FPGAs are the perfect example that have 30 ground pins or 40 ground pins. We stack them on top of each other so you have one ground pin you have to connect to. It's an ugly hack. Now in 10, you're gonna be able to define a list or a range of pins, and just with one pin, and then connect to that, and it'll fan it out to all the pins in the footprint. Per-file symbol libraries. So if you know, we have this little bit of strange dichotomy between footprint libraries and symbol libraries. People want to be able to split out symbol libraries as a symbol per file, like the board editor or like footprint libraries. So that's something we're going to add. Conversely, we're going to add the opposite to board editor. You'll see that later. We now have local power symbols. Prior to 9, when you define a power symbol, it's global to the entire schematic. If you notice on the right, this 1v1 power symbol has a little symbol next to it. That means it's local to the current sheet. In other words, that power symbol doesn't go anywhere outside of that sheet. So that's coming in version 10. That obviously that's already been there because there's a we're gonna add support for jumpers, right? So jumpers pass a net through from one pin to the next. So here you can see when you click on the net highlighting, the net passes through the jumper in the schematic, and then you can see they pass through in the bottom in the board. So that's going to be, if you use a lot of jumpers, that's going to be a handy feature. We're adding groups, so now you'll be able to group things like you can in the board editor. You can create groups, give them a name, drag them around as a group, and then copy them and paste them as a group. Here's a cool feature. Pin tables can get rather complex and lengthy, so editing them in KiCad can be a little cumbersome. So you can now export to CSV, comma-separated value files. Yeah, maybe you want to edit them in a spreadsheet, and then you can import them back. So if a lot of people, I know a lot of people who do complex pin maps like that, where they'd rather use a spreadsheet to do it. There's now, in 9, you could only have 2 cursors. You see the simulation cursor, so you can see where your voltages and currents and powers are. Now it's arbitrary. It supports any number of them. And object snapping. I showed you the object snapping in 9 for the board editor. We're going to add object snapping for 10 in the symbol editor. Now, what's coming for the board? Automatic neck down. This is another feature that keeps seeming to get pushed down the road, but hopefully we'll get this in 10. We want to make the grid system a little more flexible to do things like polar grids and custom spaced odd grids, in case you happen to lay out things on those types of coordinates. I said earlier about about the file libraries for symbols. Now there's also, we're going to create footprint libraries that are multiple footprints in a single library. One of the problems we run into, and you know this if you use KiCad over a some kind of network or cloud service, when you load your footprint libraries, because there's literally one file per footprint, you could have tens of thousands of them. So the operating system's statting every one of those files as it's trying to load them. And on Windows especially, it can be quite slow. So hopefully that will speed things up a little bit under those use cases. Route multiple tracks, I talked about that earlier. You can currently drag them, but hopefully we'll get the router done during 10. You can dynamically assign component classes. In 9, you can only assign them one at a time. Here you can use things like wildcards, like C star means all the capacitors. Assign this component class to them. I know this used to be in one of the, so what we did in 9 is we consolidated a whole bunch of footprint viewer things into one footprint viewer. Of course, we one of the footprint viewers had the measurement tool, so we added that back in 9. But now, whenever you're looking at a footprint view, it's the same viewer, not 4 different viewers. Speaking of things that got unified, for those of you who do length tuning, the router would give one number, and you clicked on it, on the object, the whole net, and it would give a different number. And then I think was it the DRC or something gave yet a third number. So we finally unified that code. You're going to get the same number all the time. And that helped with this because now you can define. So right now you can define tuning by length, but now you can define by time and propagation delays. So you can say I want it to take X, and it'll do it, and you can see there where you can see what the delay times are in that route. It's just another way of doing the same thing, except it may be easier to do it in time rather than length. We now support IPC 4761 via protection features. If you look over there to the right where the red arrow is in the pad or in the VIA properties, you will be able to change that. Those get exported only to IPC 2581 and ODB++. The Gerber format doesn't have a way to export those that I'm aware of. We added another little handy feature here. When you select on a piece of copper, like a copper zone, you can see what the total area of the zone is. Before you had to do a little bit of work to figure that out. And we've also added remove segments. So this like when you're in the router and you hit the backspace key, it'll just one segment at a time go back. So you can get back to some point where you were happy with. Well, you can now do this, but just by selecting a bunch of routes and hitting the backspace key. We also add to help you with some of the propagation stuff. There's now a propagation delay calculator, as well as a symmetric coupled strip lines in the calculator tool. So that list is by no means complete, and most certainly will change between now and the time 10 is released. But it gives you an idea of what the team is trying to accomplish for this development cycle, and hopefully it will happen. So, in conclusion, I want to say, I get to stand up here and talk about KiCad as the project leader, but I'm just like the front man. There's just such a great group of people who help make KiCad possible, and none of it would be possible without them. And I'd like to say thanks to all those people who develop, contribute their time and talent to KiCad. I want to say thanks to the event sponsors for the today, or for the KiCon circuit lead, DigiKey, and Sierra Circuits. That helps offset the cost of putting one of these on. And so thanks a lot for your support. Thanks to everyone who donated and all of our sponsors. Your generosity is much appreciated. Thank you, the community, for your continued interest in KiCad. It's really humbling to see where we stand now and where I started 17 years ago. It's truly amazing. Give Seth a big round of applause. He did the lion's share of organizing this, and from what I've understood, it's no small feat. So thanks for him for stepping up and doing that. And I hope to see you all in another KiCon conference. I really enjoy this. It's a chance for me to sit and talk to everybody. You can tell already my voice is starting to get a little raspy. But that's fine. That's why I come to these. I get a chance to talk to everybody who's in our community, and it's always motivating. I always feel motivated when I get back home after one of these. So thank you very much. If you have any questions, now's the time. Thank you.
I'm wondering how you prioritize features.
Well, okay, that's a great question. We get that asked a lot. It's several. So we know just basically by inquiries, but most of the features that you saw up there are in the KiCad issue tracker. I tell people, look, if you really want a feature that you think it's really important to you that you need, if you go into you find the feature request, there's a little, was it a thumbs up icon to upvote it? Don't submit another issue request for the same thing. If it's there, fine. You can go through the database. It's pretty searchable. The issue tracker is searchable. You can find it and upvote it, and then we use that to prioritize. Then there's the ultimate priority, which is, then we try to schedule. Before I go there, we try to schedule based on availability, because it's open source, so everybody's a volunteer, even me. So we prioritize based on what's the most popular, who's going to be available to work on it, and that's the kind of sets the priority for the whole development cycle. Occasionally we have to juggle things around. Somebody, change of life, all kinds of change of life situations. They're not available. But that's how we do it from the team standpoint. Then there's the KiCad Services Corporation perspective, where as if you were here earlier, Seth mentioned that if you need a feature now or in the immediate, near future, we'll send you a quote, and you either agree or disagree, and we give you a date and a time, and that goes to the front of the queue. And that's what KiCad Services Corporation exists for, because there's some people sitting in this room that have paid for features, and the reason they're there is because they said, hey, it's just going to make our life a lot easier. Can you do this? Yes. And and the beauty of that model, I know some people will grouse about it from time to time, but who loses? Everything that gets developed, whether it's paid or it's voluntary, goes into KiCad proper. So it's available to everyone, not just the person who paid for it. We can't do that because KiCad's under the GPL. So does that answer your question? Yeah. Okay.
Hey, the first slide showed a funding goal. I think it was 128K. I was just curious kind of where that number comes from and how that gets set.
Well, we base it on previous. So, we've been getting donations for quite a long time. So we kind of look at where we were last year and say, how much do we think we can bump that up a little bit? We're always trying. KiCad's growing. So, I remember when CERN first got involved. We thought one year we had. I don't want to put anybody on the spot, but I'll give this example because it's one of my favorite ones. It makes me smile all the time. When Autodesk pulled the license out of Eagle, changed the Eagle license, we got this huge spike in donations. So it's like $40,000 in 1 month. So that was a big year, right? So we thought, okay. So as the user base has grown, we have a pretty good idea what that is. We actually work with quite a few PCB vendors, and we have a pretty good handle on how big KiCad is, just based on their numbers. So we just, it's not a perfect science, but we just try to, as the community grows, we try to make that proportional to the community.
Wait, so how many people do you think opened KiCad and viewed a PCB in the last year?
Conservatively, it'd have to be tens, but probably more likely hundreds of thousands of people. You think millions?
We actually just looked that number up. I just looked that number up for, and we are currently month to month. People who opened KiCad every month, or last month, we had 450,000 that we know of. And those are just the people who are doing update checks.
Oh, okay. So they're running the update check. Okay. So that's just Windows, though, right? Does that include?
No, the update checks for the plugins.
Oh,
so,
the plugins. Okay.
So we just have a
counter?
tick mark, a counter that doesn't have any information in it. It's just this. We have a unique person there.
So yeah, it's a lot. We know from some of our board vendors that we have over 50% of all their orders are projects that were designed with KiCad. That means we're bigger than everybody else combined. Now, that's not universally across, but we work with enough board vendors where that's not an uncommon thing.
My question is, when does the dev team sleep? And also, thank you.
Oh, we sleep. I sleep. Yeah, it's busy. We're busy. There's no doubt about it. Because most of the dev team have full-time jobs. I think there's a few of them that don't. I could throw some names out there, but I won't. But yeah, there's a couple people I'm like, man, when do you sleep? But yeah, it's a lot. We're busy. I'm not going to lie to you. But it's a good busy. It's rewarding busy, and that you at the end of the day, you like what you do, and you like the community that you serve and work with. So it's a good thing. It's a good busy.
So if you've got 450,000 checking a month and you collected 128,000 in donations.
So we just need you to talk into the microphone.
Yeah,
otherwise,
sorry.
the
If you've
live
got
stream doesn't
450,000 checking in every month for revisions, and you've got $128,000 in donations last year, that means on the average, the user has given you guys a quarter, which I think we should try really hard to do better than that.
Yeah, I'm not going to comment on that. But I won't complain. I won't turn the money down if you send it. Yeah.
We are grateful for everyone who has contributed financially, and we're also grateful for everyone who just uses KiCad, because that helps us build it as well. Community comes in all forms, and we're here for it.
Yep. It's interesting. From my perspective, I get to talk to people from Central and South America, and those are markets that people don't have the kind of money that would take to just even think about buying something like one of the commercial tools. They'd be way outside of their purview, and KiCad gives them a chance to develop pretty complex electronics. So we're allowing prosperity in places that maybe not otherwise be available. So yeah, it's very gratifying. But yeah, I won't turn down the donations.
So a question on the language support. Does that extend to the GUI or the documentation only? And I'm also curious what motivates your choice of languages. The
answer is all the above. those statistics I was showing you was for the software, the user interface software. So that's all the strings in KiCad software. That was, so I said we had 8 languages that were 100%, basically 100% translated. That's all volunteers. So that's, we have, there's a software tool, an online software tool that allows KiCad to be translated in any language. We just need people to do it. Obviously, I'm not going to be translating into anything into Chinese. That's just not going to happen. But I will tell you that Chinese is one of the most, so WatchU, one of our sponsors, does a great job. They actually hire people they translate KiCad, the documentation, and I think the dev docs too. Yeah, the developer documentation. So, and I think that's all translated, right?
So Tao Tian is the fellow who does the DevDocs translation, not Washo.
Oh, that's right.
But they do overview. They keep it up, and they also contribute that back. So they are a massive force in moving KiCad forward in the Chinese language market.
And JP still does all the French. Jean-Pierre still does. Yeah, I still see him push the language changes. All the string updates. He stays on top of it. I mean, there's a string change, he's on it. So yeah, it's just if there's somebody who can translate into that native language, and if you know people, sign up. We'd be more than happy. It's not really it's not a workflow issue or an extra burden on us. It's just we need somebody who can translate. A lot of time technical jargon is hard to translate well into other languages, and I know that's a problem. But if we have people that are strong bilingual and can do the translations, I'd love to hear from you.
Well, thanks for the contribution. So my question is, are there right here?
Oh, there you are.
Yeah, are there any 2 or 3 other non-monetary contribution that the community can help to grow KiCad?
Well, okay, the one I just mentioned, translations. That's a great place to start. You don't have to have any technical capability. It's just you have to sign up for Weblate, and you go to KiCad Weblate, and you just start translating. It's an online tool that allows you to take the English string and you translate it into the language that you're translating into, and then that gets updated and then pushed back into KiCad proper. So yes, that's one way you can help with translating the docs, any of the documentation. If you're a strong enough coder, you can join. There's certainly plenty of way. If you got to be a C++ programmer. So that's the only thing about that. And it's, as you saw from the stats, KiCad's getting close to 2 million lines of code. So it's not, you don't just jump right in. It's not like that anymore. There's a little bit of a learning curve. But yeah, there's lots of places where we could help. I mean, librarians. So if you're good at drawing symbols or footprints or 3D models, they can always use help. There's the regular documentation. Graham's here somewhere. There he is. He runs the documentation. I'm sure he'd be more than happy to have some help with documentation. Organizing KiCon. Seth would love some help. No, in all seriousness, that's a big one. It's a heavy lift, and we're fortunate enough in Europe and in China to have somebody on the ground that just does all of it for us. So KiCad just does most of it. We do the ticket sales, the website. What else do we do? When for China and Europe. Well, we did the catering for Europe. Hey, so as you can see, if somebody because look, I'm an engineer. I'm not an event coordinator. If somebody has those skills, man, sign up. Oh, we could always use some help with website maintenance and so. I mean, I'm not a web designer. I'm an electronics engineer. I can muddle my way around it if I have to. But if we had somebody that has some good ideas, knows what's going on. There's lots of places. Social media. I hate social media. So if somebody could take that over, I wouldn't lose a minute's sleep. Here. No, there's a whole bunch of places that you can
What about industrial support? Because we talk about community, but more on an individual level. What about, working with specific industry, for bigger adoption?
Evangelization, yeah, that's the best thing the community can do. Go out and say, look at this tool. Look what it can do. Open up the, take it and show it to them. Like the KiCad demo, the CERN just contributed their VME Ren board, and that thing is pretty significant. Show them what KiCad can do. That's a 16-layer. It's a real design. KiCad's more than capable of complex designs.
One of the things we do provide is we work with individuals and companies around the world who want to do that sort of evangelization. We provide them with resources, so we can provide you with fact sheets. We can provide you with stickers, swag. We can provide you with additional elements. And so we do this in Thailand, we do this in India, we do this in South Africa, places that we don't have corporate boots on the ground in these places, but we have individuals who use KiCad for their company. And if you're going to a trade show and you want to say, hey, KiCad is we use KiCad for this, and here's some additional things about this, and you want resources to support that, that's something we can do as well. So just contact us.
Yep. Yeah, reach out. I'm not hard to find. My email is probably, at least the spammers know my email address, that's for sure. So I shouldn't be that hard to find.
I was wondering if you could show a list of the 8 and the 16 languages. I think it'd be really interesting to see what those languages are.
What's our weblate? Hey, look, KiCon. What is it? Hosted.
There it is.
Oh yeah, look at that. I love computers. Yeah, I hate laptops though. All right. So here's all the languages you can see down the left, and then you can see the % translated. So. Nope, it did the other way. So, yeah, Polish, Swedish, Tamil. How'd that one get? Yeah, there you go. Russian, Korean. So yeah, we're actually doing pretty well. But there you go. So yeah, there's the whole list, and you see down here some that are just somebody probably started them and they stopped there.
I don't see Esperanto.
No Esperanto? Well, we probably can enable that language. And
we've had a request. I didn't think it was serious. Okay, thank you, Wayne.
all right, let's turn this guy off.
Okay. Up next, I lost my schedule.
Let's see here.
Oh, good. I'm glad Eli knows he's up next. All right. Up next is Eli Hughes. Let me get Eli's bio here. We'll give him a good introduction. Okay, so, Eli Hughes runs Wave Number LLC. It's a full stack product design firm doing design services and internal products, and they migrated to KiCad in the past year. Now he is going to give an overview of how this works. So from Altium to KiCad and everything in between, the do's and do nots of migrating your shop from a commercial tool to KiCad. Please give a warm welcome to Eli Hughes.
All right, so I'm standing in between you and lunch. So I have no problem. My wife says I can BS with the best of them. So like, I'm gonna try to move. I'll be a little fast. I probably have more slides than I have time. The front matter I'm gonna move through. So when I say a story, I like the soft skills and the storytelling part of engineering. So like all storytelling has this sense of the dramatic, right? And so I always like to talk a little bit about me so you have context so you can apply that context to what I'm saying he's full of crap or this is useful to me. So, right, this is where I started, rural Pennsylvania, playing NES when I was little, loved Zelda. It was this magical machine, right? Kind of Gen X, this is what it was. But in school, we had Apple IIe computers, and where I grew up, this was, it was a very poor rural school district, but like Hello World on the Apple IIe was mesmerizing to me. It moved from video games to something else, but, this was like the reading at the time. I had Nintendo Power, but I was the nerd, and this was like 7th grade. They had this manual, and I would just go through it. It's either that or I'm bored in the middle of the woods, right? Well, the link to hardware, and this is not a software, we're going to hear about hardware. There's a link, and for me, in the manual, learning about peek, poke, and call, and what the heck does that mean? And I found this book on programming the 6502 and realized, right, to do the cool stuff, to do the graphics and the fast, this is, to get to the hardware, that's how you become the wizard. And so, and I bet you didn't know that the Terminator on his heads-up display, it's 6502 running the Terminator. So that's where, right, that's where I realized if I want to build the Terminator, I'm going to need some boards to do it, right? And this is the good stuff. But later on, as I kind of failed out of high school, I got really into music and performance and keyboards, and also Sega Genesis. But kind of linked to hardware is that's where I learned about Motorola 68000 and continued with the music. And this is kind of where the irreproducible career path is. My friend Ben Jordan and I were super into guitars. Line 6 Pod was one of the first real amp modelers, and I really got into how does that thing work, but more hardware tie-in. And so this is when I was getting to college that the hardware design was as big as the software and the algorithms to me. And so this is why I say the irreproducible path. I would never call myself a PCB designer. I really like them. But I started with electronics, but I went to grad school for acoustics, the science of sound, master's and PhD program into the whole theoretical. But I like to kind of be in the middle, because that's where the cool stuff is, and build guitars. And I like the physics of it as much as I do the thing. Now, to do all this stuff, boards, I learned, the first tool I used was Protel, right? And Protel was really the first Windows. At the time, it was Windows 3.1.1 for work groups. But in college, that's what we used. And so, but I discovered, I got hooked because we actually had the etch boards and using ammonium persulfate and ferric chloride, and I dumped things down the drain, and after hours I probably never should have. But that's where it started. And anyone who knows, right? And I'm going to pick on Altium a little bit, but it's for fun. But I couldn't find the screenshot. But when it would crash, and it would, even back in 1998, you got a little bomb, this little pixelated bomb. And so anyway, that's where I started. But just a little bit just for context of where I'm coming from. I mean, starting with Protel, and that went into the first job, but there was OrCAD in my first job. There was a stint of Eagle, and a lot of these things were overlaid, where I had to do multiple for different jobs. Altium had been, when Protel, kind of the company renamed into Altium, that's been pretty much consistent. But there was expedition workflow. If you have a lot of money, that's what you did. And then I put KiCad on there. But it's been everything. 1 layer, cheapest possible, to 20 layer with a $50,000 FPGA and billions of little traces. Rigid flex, HDI, a little bit of everything. even if you look hard enough, I actually keynoted Altium Live in COVID. So, you know, a little bit of everything. So just so you know where I'm coming from, right? But so like, why am I here, like talking? So when I say like full stack, like the software world uses that for like if you're web front end, you do a little database. Well, to me, full stack is like soup to nuts, right? You know, semiconductors to writing, you know, Python on a web backend. But like our company, like it's less about technology, and I come from a ownership, accountability, first principles, like drive like everything. So like tooling isn't always dictated by like customers. Sometimes it is, but like at the end of the day, we have to deliver, right? We have to deliver a thing. That's the outcome and what I'm accountable to, all right? Especially on a small business, there's an alignment problem between what's being developed to keep people productive, right? And what drives profit at EDA companies. And it's been diverging a lot, not just a little, like a lot. So just as another, like, I love open source, but I'll pay for value, and I'll pay a lot, right? I have no problem with paying for tools, but, right? One instance, I can't name a name, but I moved a company, it was a $200K deal to get, you know, 30 or 40 seats into Altium. This is a while ago. Maintenance costs, like the whole deal. So I bought in when it was $16,000 a seat, right? But at the time, I mean, it was a good deal. It was what I needed to do the job. So a lot of what I'm going to say isn't necessarily about the cost, right? I would actually pay for KiCad, right? It's not, and actually I do. I pay some of the KiCad Services Corp, right? Because there's value. But there's a lot of other things, at least for me, from a professional point of view, that actually matter more. And so here was like the tipping point where I really started to go from like casually looking and following to getting serious. And like HTTP libraries, I was actually quietly observing on like GitLab. I just look at commits. And when I saw this, whether you know it or not, this is an enterprise level feature that actually Altium and the other tools do not have, which is a big deal if you know anything about web backend. The ability, and we're going to see an example. I'm going to tell you a horror story that an open file format, whether you like S expressions or not, doesn't matter. It's the fact you can look at it and deal with it, whether it sucks or not. You have a chance, right? That's the, so, but one thing I did notice, in my opinion, the 3D output generator is now superior. Like it is, objectively, and I'll say my objective. But the CLI, for me, it was actually one of the last pieces that kind of pushed me into, you know, investing company time and dollars and do this. And this was actually a V7 design. I think it's whenever, and Seth or Wayne might know, when TrueType font support was integrated. And I was actually filing some bug requests. This is MixMonkey. He was the little, I had these active pickups in my Carvin V, and this is the backplate. I made a little active mixer with like volume controls. And that was like V7 or V8. And that was just, hey, I'll give it a shot because I can put, you know, Mr. Monkey on MixMonkey, right? And so the other context here is, right, like, no, and this is actually, because I see there's actually like students, and I used to actually teach at Penn State, like this is the happy button. We all want the happy button to automate everything away. Here is the reality of success, right? In the long wavelength limit, long time and energy, knowledge of physics, materials, requirements, and knowing what you want drives success. I love happy buttons to automate, but that's not what stops you. If you take ownership of an outcome, like those are the things you have to know, right? Everything else is what helps you. Now, you know, as Wayne pointed out, there's actually a lot of happy buttons, right, in KiCad. But there's some other things that's actually, I think, even more important. So this was, I'm going to try to, this was mindful of time, but so some dissonance. So I pay maintenance on several tools besides Altium for several licenses. And every year it's another $2,000-3,000 between, you know, for each tool and for each license. But that doesn't mean you actually get anything, right? And it doesn't, and people will say, well, that buys us support. Well, does it, right? Like, and I put this to a test, and I consider myself, I mean, I've been using that tool in all its variations since like '98, but here's what happened last year. I had a project. It wasn't huge, but it was very time critical. And I actually had another, one of the other developers at Wave Number helping me. We ran into this binary corruption, but it happened at a very specific, it wasn't like at the start, we were pushing the PCB, he was doing placement, I was inspecting, but there was something, and we couldn't figure out where I did git pull, looked at the board, I couldn't click on anything, and the text was all screwy. And it was far enough along where starting from scratch was terrible, right? I could do git reset, we would follow the same process and always end up. Well, just to give you my several copy license, 5 weeks from the first internal support case where it wasn't just, hey, it's broken. I spent like a couple hours putting this together with files just to get someone to respond, right? Here was the reality. I fixed it myself. Through the help of various tools, I just reverse engineered the PCB.doc format. I found where the problem was, and it had to deal with net classes and how things pushed. And I finally, someone got up. By the time they believed me, and for developers, I mean, that's a long time, right? I'm nobody, but like I feel like that money should buy at least someone say, yeah, we're looking into it, or we'll feed that to the developers. So this was real. I mean, I had to save face with a client. Like, this is a pretty big deal. Like 3D, small example, but this was real last year. Client who does a lot of SolidWorks, they wanted something in a Parasolid format with their little logo. Altium can do that, and there's another level to export more. It was broke. Like, this board, we could not figure out why SolidWorks would barf and everything else barfed on it. But it was an Altium, and I just gave up on the support. Well, the solution, I imported in KiCad, exported step, opened FreeCAD, got to XT. And believe it or not, that is the FreeCAD render, and it was beautiful. I did no fiddling around. And so, I mean, that was a real story because, once again, I have to deliver. It's not like I can wait around. Now, this is a funny one, right? And this is where I just started, like, and I don't want to pick on Altium too much because there are really good things I like, but Altium has what's called multi-board. It actually solves a real problem of you have boards of boards, right? And it's more than just bringing step. There's linking information. I've been using it since the early, like the betas, like as I was on the beta program. I have perpetual license on a local network server. Well, I did an update. It said, sorry, you're done. Pay more money. I'm like, well, I'm perpetual. This is a feature I had. I gave my time for a long time feeding back beta, right? What's up with that? He's like, and so yeah, like, well, we need you to move the cloud model. And by the way, we're going to redefine what perpetual actually means. So yeah, like we're altering the deal, and let's pray we don't alter it any further. So I was a little angry, but I'm not alone in that. Like that's not, like you can just go to like Reddit and like see a firestorm. And depending on now I'm small potatoes, nobody, but in bigger companies, for whatever reason, they just maybe don't care enough. But it wasn't long after that horror story with the binary, it might have been weeks, I woke up, I saw this. I have no idea what this was about, but I'm like, what psychopath like came up with this? And now this went in automated Windows, but there is some, in the Altium, like my network local server, I can't use a VPN. If I was to come to here, right, and do my little tailscale VPN, I'm in violation. I'm in 800 meters away. I'm like, that's psychopath. That's behavior that, like, I'm sorry, like, no. I'm angry cat. So this just pushed me. But like, the reality is I actually do like Altium. The core part, like, and Ben and I have been interacting for a while, it does some things really well. And it was the first to do a lot of things in the industry. The first really usable 3D visualization that used DirectX in video cards. I mean, the first functional push shove multi-route was Altium. Other people were doing it like OrCAD, Altium, OutJobs, 3D design rule checking. Like all that is actually really good. Like, and to this day, I still like it. Draftsman documentation, still nothing else like it. It's a little slow, but like, so I don't want to pick on them too many. They do a lot of good things, but I mean, reality check. I mean, I got to pay a mortgage. I got to pay some people. I want to retire someday and like work on stuff and not be stressed all the time. But right. But I mean, I think like all big companies that get acquired, you move into a phase from value delivery to extraction, right? $5.8 billion, someone wants that money back plus, right? Now, I have to still use Altium. I have clients that use it. I have old designs, right? But it was timed like some sort of parallel path, right? And there's always an argument, well, KiCad, or I'm sorry, I keep saying it wrong, but like productivity really is more about like happy buttons. And like not everyone does 10 gigabit per second diff pairs, right? The bulk majority of boards are 2, 4, 6 layer, right? That's known, right? Workflow, open interchange, and all this other stuff is probably more important. Stuff around the edges of board design, not the actual board design, stuff that comes before and after. So it's like machete in the jungle time. It's like, how do you go from A to B? How do you eat the elephant? And so, my way was hard, but I had a specific idea of how I wanted to do it based upon my existing workflow. So there's a lot of ways to enter. This is the way I chose. So we stood up a system where the same library, the same metadata, could be used in both tools simultaneously. So all that internal part numbers, data sheet links, all that are shared. Anything I make in Altium now is instantly available in KiCad. So Git version controlled was a big port. And now the workflow is 100% supports pull requests, merge requests. It actually scales pretty well with people merging things in. Now, just high level, there's a lot of details, but this is like high level. So if you've never used Altium, like to me, there's like really one way to do libraries, like that really scales. It's their database libraries. And it's a little different. Like you kind of treat every little piece as like this little atomic little thing. And so you have symbol libraries, which is just a symbol, no parameters. Little footprint libraries, just footprints, nothing else. But then you have metadata that has to exist in a database. And we'll use that term loosely, just stuff in tables. Well, Altium always did it through this dblib file where the metadata gets joined. And literally think of like a database join operation where you have tables that define this symbol, this footprint, these parameters. And ODBC just like, it's an old Microsoft tech to like try to like give you pseudo-generic access to any data store. And we do one symbol file has one symbol in it, one footprint file has one, so like merging is sometimes possible. Now, why would you even do this? That sounds really hard. Well, the reason you do this is once you set up, building up extremely large libraries of Jelly Bean parts is trivial. So like an example, we have resistors in Panasonic Yageo from 0201 to 2512 and all packaged, all heights modeled. Capacitors from Murata, Yageo. So when you put the stuff in your schematic, all metadata is in there. You run a bomb, it's clean. So there is no such thing to me as a generic part. It's like someone's got to order the thing. But that's what then drives substitution. So, but think about that resistor library. That's thousands of things. Well, it's one symbol and really a handful of components. It's just the automation in the database, right? And all of that can be automated out the wazoo. So I wanted the same thing. And the ODBC interface kind of sucks now. It's old and it's not the new cool thing. When I saw version 9 had HTTP libraries, I knew right off the bat that was it. Because I've done a lot of like IoT and web backend type projects. It kind of works exactly the same, except you replace that database, you have something serving an API. Think of it like, and if you don't know what HTTP API means, when you go to a web browser and say http google.com, it returns you an HTML document, right? That's what it is, except it returns JSON. It's just a structured little thing. It kind of looks a little bit like C. But it's the glue. Anyone does like web development, it's like the duct tape that's holding the entire internet together, like with services. But the thing is, almost anything can consume it and generate it, but it separates and abstracts the data store. And that's actually pretty important. You can replace, like what's behind that server actually doesn't matter. The contract is that API. But KiCad does the same thing. Everything kind of joins in, like into a part. We're putting these things together. I've really wanted this feature in Altium. I've asked, and they say no because we want you on Altium 365 for an extra couple thousand a year. But I'm like, well, okay, like, And KiCad has the other style as well, but this to me, I really liked. So now, how to make that happen? Because this is really like Machete. So this is libcruncher, right? So I wrote a Python script. And what it does is, and I'm going to try to show you a quick demo, is that at the base level, actually the data stored locally are CSV files. And I've gone through everything. It's the only thing that is mergeable, easy, upgradable, and I can sync it with like a back end, and it works for everything. And it's a nice editor, does basic, metadata checks, meaning do things match up? Do the names and symbols, and does it meet some standard? But here's the big deal, is every independent symbol, it automatically auto-converts with KiCad CLI, like in the background. So it just happens. I also use it I have this other requirement that if I want to bring someone in, I want them in 5 minutes to be productive. So that's what libcruncher does. A new developer come in, within minutes, has the whole library configured. The whole global symbol table goes away. You don't have to worry about it. It's auto-generated. And everyone gets the same preference. We'll see I have this crispy black and white classic pro audio themed schematic. Everyone uses that. But it also serves as this HTTP server, and that's what we stood up. It sounds like a lot, but actually once I just understood what the pieces were, it went pretty quick. So I'll just get this quick as I can, because like it's 15 minutes and you want to eat some lunch. So I'll just show you like what libcruncher looks like, and it's that's kind of visible. So this is actually PyQt. So LLMs, right? They just help you write this stuff if you know what you want. But so what you're looking at now is just a skin over like these CSV files. Like, and I'll go to something with a lot less stuff. I'll go to like IC, I don't know, like what's a good one? Like MCU, right? And so this is all the metadata like that's behind a part. And like I said, it's a CSV file. But in here, right, this is a typical, this library path. This is how these DB libraries work. You say, all right, where's the lib file? What's the name? Where's the footprint? Well, I just have the KiCad one in there. And now it's auto-generated because I have libcruncher rebuild. It auto-generates the actual HTTP lib file, handles all of the global symbol tables. And so what we get, let me go over here. I was trying to have this staged, so we'll take a look at some of this other stuff later. I'll just click on here. Now keep in mind, this is being served like locally, but there's almost 9,300 parts in here. But all of these things came from Altium, and I'll just see if I can get this in view here. So we can just go in here and click. These were all from Altium. And so I have all these parts. And so usually I say, okay, libraries to me are the most useless thing on the planet, right? And I say that tongue in cheek. Jelly bean parts, I put them on. That big FPGA, you put blood, sweat, and tears in configuring that, copy the whole schematic. That's the value. But when I'm building a filter or something, being able to pick parts, I have all the values and all that stuff is nice. But I was originally worried about performance, but like this is the part that's faster than Altium. Like here's one of my favorite audio DSPs. I'll type in RT685. All right, brings it up, got this fancy BGA package, and there I have it. And so it's actually pretty performant. Like that's a lot of parts. So I'll go back here and I'll say, what if I want a 10K? Here's all the things that match, 10K in various, little 402. We put it on. Yep, and there we go. And it's got a crispy black and white. Beautiful, right? It's clean. So quick, that's a quick demo, of what the outcome is. But, that's what we worked hard to get stood up. That way we use the same system because all the downstream things, bomb generation and pushing into like a back end was important. So here's the next problem with like all engineers, myself included. Right? You got to push the baby bird out of the nest, right? When's it stop being the planes in the hangar and you want it to be perfect. The reality is you'll never have perfect time. February, March, I actually had a real project. We had some boards. They're going in the production. Total of 6 boards. 2 of them were, I just said, these will be in KiCad. And there was a third for an acoustics conference. Two of them were 4-layer, one was 6-layer. I said, I'm going to do it, right? And there's a saying, a mentor said, nothing motivates a person like knowing they're going to hang in the morning, right? You figure it out, right? And so whatever state we had it in, we're going to push through and do a real design and get paid for it, right? Because that's the big deal. We want the money, right? I want to buy my coffee and pay my mortgage. And these used a mix of parts. I used the new layout replication feature for the LED board. It was a Friday morning. I drew the schematic, a couple hours of fiddling around, and it was done, right? I was actually fairly impressed. Altium, while there was NRE in getting here, of these 3 boards, I didn't feel really that less productive in the core part. There's obviously me fiddling around. The difference is I've done so many boards, I know what I want. I know I can get there, but I didn't feel like productivity was a big deal once you spend the NRE. But I have almost 30 years of NRE in Altium, right? Versus a couple months in KiCad messing around. So this is the other cool design. Like I was just going to show because I like the name. So this is a new vibration sensor, codename Yoshi. And I'll tell you the story of why it's called that. Thumb screw USB-C is a thing with gaskets that's actually pretty cool. USB audio interface, separable casing to swap piece and parts out. To generate, this is a spectrogram to do plot in a 2D version of power spectral density. It's big in acoustics. And so this was like, and this is what I presented at the Acoustic Society of America a few weeks ago. This is what Yoshi is. It's how it breaks apart. The big deal is the separable base plate. And actually the top, you can replace the USB-C connector with a blind mate adapter. So instead of being hooked to your computer, imagine a little module, it's now Bluetooth, or it's now a data logger. Why is it called Yoshi? Well, if you played Super Mario World for the SNES, well, in the early 90s, it was a big freaking deal. Mode 7 scaling and rotation, these graphics. Well, you had Mario. Almost immediately in the game, you see Yoshi. And what can you do with Yoshi? Well, you jump on top and you become more powerful. So Yoshi is, you have these mechanical adapter pieces. It's like you're jumping on top of Yoshi and you become this more powerful sensor. So, renders. These are actually beautiful renders, right? Like KiCad. It looks great. So this was 6-layer board, had epoxy filled cap via 5mm trace and space. Boy, it actually went pretty quick. I was a little bit under duress to get it pushed out the door. But yeah, beautiful design. And there he is. There's Yoshi. And this was the, I always like to get cases machined from clear PMMA. They're just like really cool to look at. The real one's like anodized aluminum. I'm trying to go for Yoshi green if I can get it. But yeah, I had an earlier project where the product family, we wanted to recreate the entire NES universe on silkscreen. So we had Zelda and Mario. Well, I'm up to SNES now. So, we're moving on. So for me, like now I'm a little weird, but just being able to look at C++, like I write a lot of embedded code. I'm not like a GUI programmer in like Windows, but I know enough about C++ I can figure it out. Just being able to inspect, right? Just to know where some boundaries are. I mean, I set up the build. I know enough about build tools. I was actually really impressed with KiCad from a developer that I was set up pretty quick. Now, I had to crunch a while on my machine, right? CMake, and run Ninja took a little while the first time. But but for me, like I think in terms of outcomes and building what I need so I can have a stable base to work from. So like, now that example I had of like the $200K initial cost plus there's probably still paying $80, $90K a year. I was like, well, what's the cost of a full-time C++ developer in a large org? I'd rather have the developer, right? I could build out what I need for my workflow for a long time, right? That's the way I think. So, Altium does, and the other tools have scripting engines, and the problem is they're not amenable for like, you can customize it, but Altium, they've kind of abandoned their whole C# SDK. They have like this, Delphi script that you can kind of do, but you're still confined in the tool. It's just really hard to adapt to what I'd call like modern CI/CD. Product longevity. I still have clients. I wish they would go away. I love they pay me. There's literally a board in software from 20 years ago. The problem is, you need an old version of like Windows or whatever just to deal with it. But that is a value in the industrial world. Like, that's normal, right? Now, there is another reality. So I kind of sit, I'm a, like, you know, on the one side of Gen X, not quite millennial, but I'll say I'm still solid Gen X because it's the best generation ever. No, there is a reality, and I'm seeing it. I'm probably right on the edge of, like, and it's an age thing. Sound ageist, but it is. So, like, all right, there's a lot of circuit board designers, all right, that are retiring, right? It's an industry filled with a lot of old men, right? That's what it is. But, you know, there's a lot of students coming in. I saw this when I taught at Penn State. They're coming into it from a different perspective, right? You know, Git, continuous integration, and just software development stuff is normal. So the day where you become a circuit board designer, and that's what you do for the company, those are over, right? Like, people now, the tools we have are better than they've ever been. You know, like, one person can accomplish a lot. And so, like, that's why I say I love doing it. It's hard to give up, but I don't ever want to hire a PCB designer. I want, like, a stem cell who can do anything and help build them. Here's the other reality, like LLMs, like AI, well, this is a buzzword. Here's the reality. Someone who knows what they want will get that to hallucinate what they want pretty quickly, right? No, but it's true. It's not, I don't see it as taking any jobs. I'm seeing it as someone who's good could go really far. And I'll give you an example of that. But like that HTTP server is like, well, I don't, like, what's the latest and greatest? And in a couple hours, I had it stood up and serving parts. Now, maybe it's not the best code, but I could start and hand it over to someone once I figured out where the value was at. And then we can keep hacking at it. And so that's just another reality that even though you might not consider yourself a software engineer, like, if you know what you want, like, software automation's a thing, right? And I like to embrace it. So I have a mechanical engineering is now a grad student who's a stem cell. Just, I would starve to be able to pay, you know, keep paying him, keep him a job. He's that good. He's never touched a PCB, is now productive. Started out in Altium, builds Blender. He was awesome in Blender and SolidWorks, but I've also found out that I think mechanical engineers are actually almost primed to be really good circuit board, people who do circuit boards. The reason is, like, PCB design is interesting. It's not like one thing, it's like four. You got to know what to put on the schematic, regardless of the tool, right? That's some of the electronics engineering. Well, there's using the tool. You're just the technologist. Well, the PCB design is more physics, right? You say you need some physics. Well, then you have the whole manufacturing, 3D and everything else. It's like manufacturing engineering, mechanical engineering. That's an interesting person, right? I think it's awesome. So what we're doing now, so it's still up in work. We had a couple boards out, having a couple more. I'm building out, I'm starting with, like, there's like the KLC library checker. We're building, like, this footprint sanitizer. Like, I am pretty rigid on, like, nothing comes into the library that has, like, you can pull from external sources, but it gets filtered. Like, because if we're making a $50,000 build decision on something, like, we're checking it and we're testing it and just don't assume anything. Some work automating templating. So in the Altium system, I have a back-end system. I say, you know, new part of this project, this assembly, it sets up all of the schematic and PCB with templates and part numbers. We're building that in the KiCad, doing some work with the PDM. The real vision is, and this is to me when looking at LLM technologies, like, all right, I can remember a lot of things, but that doesn't help anyone else, right? I can remember, oh yeah, remember 15 years ago we put, you know, OPA 237 on this design. Well, to someone new in the company, no, they don't, right? But what if, like, you could have your company data store saying, hey, what ADCs do we like to use and what's been successful? Like, that's the perfect thing for an LLM. But I think a company needs to own that. That's your magic stuff. And, like, to me, the only way you're going to get there is with open formats and your own stuff and a way to parse it. And so, yeah, so I have someone just working all summer on, you know, there's some work in 3D and some in tooling, and that's all he's doing, and it's awesome. If I had more money, I would just get more people to do stuff. So, and I at this point, I'd rather honestly invest in some of the right code, right? Because, you know, everyone kind of benefits. And I want to come here. I mean, there's some, I'll say some selfish motivation. I want to meet some developers, maybe schmooze a little, maybe say, hey, do you like me? Let's collaborate. There's some of that. So yeah, and I don't want to give money to people who don't like me, right? Like, so, now I say that, yeah, okay, I'm joking. But no, the reality is like, I do make choices, like, and this is me personally, but like, my wife and I, we go out to dinner, right? I'm going to spend I don't care if it's 2x. I want to go to the restaurant that's local. I know the owner because his kids are going to college. I make purchasing decisions based on long-term thinking, right? And that's just, a big deal to me. So, and my thought is like, I'm focused on a V9 because that's just where I really like focused in. It's like, it's more than like, I look online and people arguing whether it's professional, and that's like just a ridiculous word to begin with. It's like, I've seen stuff that's professional that's absolute garbage. Like, and I've seen people use virtually nothing to create awesome things and make lots of money from. And professionalist means you get paid money to do it, right? You're supposed to have some good workflow and process along with it, but there's nothing stopping you, at least in my opinion, from KiCad. I like to make schematics look like old amplifier designs. Like, that's just the way I am, black and white. And I like black and white because as soon as you add color, I can like see like a differential. There are some things like I'm hoping to eventually see interactive 3D placement, something I miss, real-time 3D clearance checking in the tool. Altium does have a feature of find similar objects, and KiCad is pretty close. That I use a lot more than you think. Draftsman for the output documentation for fab drawings. Variance engine, I'm excited to see that. And I think it's all going to come. And like I said, I'm willing and able. Put code, time, blood, sweat, tears, like, right, I'm in, right? And I think once you decide you want an outcome, right, everything else is like details. But yeah, some more to come. All right, so I'd say Altium, any tool works for you, that's awesome, right? That's the end of the game. But I do think, for me, it's like a serious option, right? You shouldn't discount it because you perceive it a certain way. Like, I consider myself a pro. I've been doing it for a while. I get paid to do it, all right? Do okay. All right, I can see it's gonna scale like to where I need to. It might not have all the happy buttons yet, but that's not usually the constraint. The constraint is, hey, how do we meet a deadline for some other ridiculous reason? Or how do we hire people, right? Like, those are constraints. I'm actually working on a design that right now it's gonna be a 10-layer design with DDR4 memory, a giant FPGA, but 64 of these to get 64 channels of 1 gig of sample per second for a spectrometer. I consider that as, if we can pull this off, that's as real as anything. Like, it will be in KiCad. So I'm still doing Altium. Like, I have projects ongoing with other people, and I'm probably still going to go to. But for me, I think the investment's going to pay dividends. SolidWorks is still part of the workflow. I mean, that's another nut to crack, but do one thing at a time. But I do, Nathan does a lot with Blender to sell the industrial design dream, and I use a Libre. But FreeCAD is starting to be attractive, as well. We actually had a valid use case where I needed it. I couldn't get paid unless I had it in the loop, right? And people want their paycheck at the end of the month, right? It's a big deal. Now, I do want to say this is something I'll do a lot with NXP. I couldn't show it today, but one of their global head of marketing, directors, Justin, I work with him. We're actually contracted and paid to do this, some new development boards for the new MCXA. He said, we want it KiCad open source. Like, that was just requirement. So it's going to be, first one's going to be like Adafruit feather form factor. But the other side of this, like first class open source software tooling, Zephyr RTOS, like I'm a big Zephyr fan, but also everything else. And going to feature some other cool stuff. And this is more like this winds of change. Like, and I'm actually allowed to talk about this now because it's weeks away. Like NXP and like the LPC microcontrollers have put in a secret processing core that's kind of like the RP24 PIO. The developer, I met him, he added it because he had a little bit of area when he was writing like VHDL and synthesizing, and he put it as an experiment, right? Well, it turned out, manager and suit and tie pointing here says, "Oh, we got a customer that are going to go with company whatever. how can we get them to switch? Well, we have Easy H. We can make this peripheral, and it's been in there since 2006, right? Once I found out, in the reality is he wanted to push it out, but it was a support surface area. They just weren't sure if people would, and Adam had his docs, which weren't really that great, and it was, I mean, he's a real nerd, and they weren't sure if anyone would like figure it out, but this is gonna get opened up, and it's part of this design. It's just changing thought process. Even if someone as big as NXP, open source, they have to conform to a lot of things, so it's not like overnight, but they're pushing like all the SDKs, everything's on GitHub, right? Huge in the Zephyr now, like, and I also think internally all their dev boards are, they use Allegro and some Altium, but the Renesys acquisition and TI's in the same boat. Like, they're like, do we really want our competitor? They're like perceived to have, like, and so the winds are changing, right? And I was pleasantly surprised. So I said yes, right? All right, so there we go. Thanks for attending. That's BrewBot. That was an old design, but he's saying goodbye. So, hey, I'm only 5 minutes over, so we're not too past lunch. So, questions? That's a lot.
In your evaluation for the HTTP libraries, did you check out any other options, and in particular inventory, that provides things like stock management for both parts in stock and export production outputs? And also, do you support any of those things in your tooling?
No, that's a good question. So, like, I actually didn't start, like, I started with, KiCad had the database library, the same style with ODBC, but, for that to work, you need an ODBC driver on Windows, and it's kind of terrible. There was just a lot of, I was having some friction when I saw HTTP. I was laser focused on my own system. Plus, I have a system that kind of does that internally to fetch things, but I did see that PartsBox just has integration now too. Like, it's a inventory kind of thing. But, for me, I kind of see it as like, I think of it as like glue, that like, it can work with anything. So I like that there's gonna be like 8 different solutions. Like, to me, that's awesome. Like, it's just, I have a very defined workflow right now because like, I have somewhat of an attention problem that I'll fret, even like naming a part, like, what's the name for the board? Like, and should we put the part number first? I automated everything away that even if I don't like it, there's a happy button. That's where I want the happy button, so I can just get focused. And to me, this was another thing that I saw it as the glue, and it allowed me to start at least stand something up. And then the inventory and the pricing, that's like another good nut to crack, because the other thing with the LLM, the where used, where have I used this part and what's my impact? I just feel like I don't want that behind someone, if I don't satisfy whatever monetary things, to lock it up. Like, I got to know, like, that's, but I just saw, I don't know which form was on that. Yeah, it was inventory, and just PartsBox was the other one. So I was super happy about it. Like,
you get inventory, it provides a lot of that
stuff. Yeah, the where used. So yeah, I'm definitely going to be an advocate just for that way of doing libraries, because it is something that no other EDA tool has. And that's why I say it's enterprise. Like, even though it's new, I just think it's a big deal. Yes, sir. Uh-oh, here comes a hard one.
No, this is really easy. Are you gonna publish the black and white schematic theme? It was awesome.
Yeah, I can. So like, actually, well, here's the thing: is it actually started? There was already a black and white theme. I just had some other things I applied to it in terms of like size of text and fonts. And the big deal was really, I use a couple different machines. Everyone does, and so I wanted a simple way that, and I'm always blowing them away and starting over because I use Windows and I do it every 6 months, just to say, like, libcruncher setup, and it literally sets it. I mean, it copies preferences, and I just have my setup everywhere I go. And so, but yeah, I could push it out. Actually, my libraries, it might actually be open on GitHub. I don't know if we locked it down, if wants to look at it, but that's where I started. I just went further with like the, how I did fonts and colors. And for me, actually, there was a real reason, is like, I just have so many things hitting me. Like, it seems like I have to shut off my phone, and I like lose attention. That with a complex design, you think black and white, it's hard to see something. it's like there's all this stuff that's necessary but not important. I like the black and white because when I highlight a net, I can see it, and it's like, holy crap, it's like the dynamic range is huge. So that, and boy, it looks like an old Carvin amplifier schematic. And to me, like, I don't know, like, I love that. That's just what I kind of cut my teeth on, so I feel that's the most awesome way to do it.
Okay, thank you, Eli.
Yeah, thank you.
So that we have some lunch for everyone out in the hallway, and you're welcome to go grab some. There's a vegetarian option off on the side as well. So if you don't see it immediately, it's there. Also, if you're interested, there are some people walking around with KiCad T-shirts. I brought a bunch of them from the store and have set them out. If you're interested, I'll be sitting behind a table. Come on over. You don't have to pay for shipping, so you save a shipping charge on KiCad, some KiCad T-shirt if you want to pick one up today. So, and we'll pick up this afternoon. Does anyone have the schedule in front of them? I'll get the exact time. I think 1:40. All right, so we'll pick up at 1:40. Should be time to grab a bite to eat and recharge for the afternoon.
Sound check, sound check. Sound check, sound check, sound check. Sound check, sound check, sound check. Sound check, sound check. All right, I got that. Sound check, sound check, sound check, sound check. Sound check, sound check. Sound check, sound check. Sound check, sound check. Sound check, sound check, sound check, sound check. Sound check, sound check, sound check. Sound check, sound check. Sound check. Sound check, sound check. Sound check, sound check. I don't think I'm getting. There's no sound out there, is there? I hear it. All right. Is there sound coming out now at all? Not now. It was a second ago. Okay, yeah. So I think I have found a mic in, but it's actually going to this local speaker and then through this microphone. So. Sound check, sound check.
Yeah, I can hear it.
But not very loud, right?
It's loud enough to hear. I mean, you don't have a lot to overcome.
So how about, does it work at all? Does it work at all? I don't think so.
It seems to be, yeah, no, it seems to be picking up from there. I think it's only working when you're near the podium.
Yeah, I would like to be able to, Sound check, sound check, sound check, sound check, sound check. Now you got it. All right. So how's the audio sound of this? Alrighty. So we have it, and I'm going to reconnect this where it was. It's just that this is going to be so much easier for me. I've never presented with a fixed mic like that or held it or anything. Though their sound is very good here. I would say it's very good.
Let's do a picture now.
Alrighty, let me straighten my bow tie. Let me take off my phone. All right, so that's my number one slide. All right. Well, I don't even know what to say. I have my slides, but I'm not sure what to say.
There we go.
All righty.
So now I have a picture if all else fails.
All right, very cool.
Something goes wrong. Hey, someone new just committed a schematic capture. It's an elliptic rejection filter for 1 kilohertz, 6-fold plus zeros. Something new.
I'm devastated you've not tried QSPICE. Deal is, if you're not using QSPICE, life is not worth living. You know, that next breath of air you're all thinking of taking, you're literally wasting your time. I'm just saying. Okay. I am Mike Engelhardt, yes. I think this is a little too loud.
Are you using your own microphone?
Yes, I am.
Oh, okay. You could have thought we could have provided one.
Wait, Hector, is this
I don't know.
podium mic? Okay.
I don't know how to use one of these.
Okay.
So I can't stand still. And I've never done it, so I just bring this. Yeah. Lighter one. This is as good as it gets. This is a Countryman. Come on. Yeah. Screw half measures. Just get the best, you know. Just screw half measures.
Audio is underrated.
Not as much as sight, though.
Television without video.
It's called radio. Yes. QSPICE will set you free.
I don't know yet. That's what I'm hoping.
You're going to find out, yes.
You use NGSpice?
Oh, a little bit, yes. I'm not real proficient with it.
Television without audio. I saw you about 5 years ago.
Oh, yeah? Probably here in San Diego?
I believe it was, yes.
Okay, yeah. I used to come down here for seminars with some regularity. Yeah. I had a little bit more hair then, though.
Me too.
Yeah. Your hair is in shape. My hair is, you know, my hair is already in the history books, you know, and that's.
You were giving away fishing.
Oh, the official LT Spice bass scaler.
Yes.
You know, it's like you're fishing, you catch a delicious bass, and it's covered with scales. What do? You take out your LT Spice official bass scaler and you get rid of those scales and you enjoy your delicious bass. I traveled the entire planet giving everybody I met an official bass scaler. Except in India, I called it a multi-tool because, you know, half the people don't fish, you know, so I had to. Generally, I'm not a very polite person, but, you know, I cut a little slack there, you know, simply because the food was so good, you know. I'll try to speak slowly and distinctly for my Australian friend there. Yes, sir? Oh, yeah, well, you could. Yeah, so I told your friend there that when I go to New Zealand, I was always told by my townies that I should, as an American in New Zealand, I should always speak slowly and distinctly because in New Zealand, you never know when you could be talking to an Australian. You what? I'd rather live in New Zealand anyway. I like New Zealand. I actually prefer the southern island. You know, I've been there quite a few times, but Christchurch got depressing. I used to go there, and I felt like I was doing a, you know, a Peace Corps sort of thing, doing seminars in Christchurch when, you know, the place was obviously just deteriorating after the earthquake, and everyone was moving away, and there was hardly any business there. But I like it. It was great. You ask people what the property taxes are, and they have no idea what you're talking about. It's like, what's not to like about New Zealand? How do you do? Awesome.
Okay, so I hope everyone had a good lunch, got refilled for the afternoon. All right, great. My wife is at a conference right now in New York, and she sent me a picture of their lunch. She had a single slice of cheese pizza, and it looked like it had died. So. I didn't want to rub it in. So we're starting just a little bit late. So don't worry, Mike. You have your.
I'm all good.
Okay. All right.
I take great pride in my ability to follow directions. You just tell me, okay?
Wonderful. So our next speaker, we are very, very fortunate to have Mike Engelhardt. So for those of you who don't know. Mike has been writing his physical simulators since 1975. His first simulators were written for high-energy physics labs, instrumentation companies working in charged particle optics, and hydrocarbon location for oil exploration. So he has also developed simulators for a number of EDA tools, and today we're going to be hearing about his work with QSPICE. So please give a warm welcome to Mike Engelhardt.
All right, thank you very much. Yeah, whenever I hear that, I always think, God, it's just the gosh darndest thing what a guy will do for a buck. You know, there's no accounting. But okay, so I wrote QSPICE, and people wonder why I would write QSPICE, because many of you know that I also wrote a program called LT-SPICE. And so after having an experience like that, why would I do it all again? And the thing is about LT-SPICE is that I wrote it 25 years ago, and I wrote it in a period of about 10 months. And if you write a project that big in 10 months, there's probably things about it you don't like anymore. And in fact, the matter is there isn't anything in LT-SPICE that can't be done a lot better. So QSPICE is my way of saying, I'm sorry. And I've got it right this time now. So basically, QSPICE started out just as a personal mission to get SPICE right, with no business model, no concerns. I just wanted to get it right once in my life, because it is a complicated code. Even if you're like me and are from UC Berkeley, and you've had someone from the original Berkeley CAD group explain it to you, it's still a complicated code, you know, and trying to figure out why it was architected in that way. I mean, it was like 1970s concept of object-oriented programming, and it makes no sense. Even if you're a native C++ speaker, it makes no sense the way it's written. Anyway. It's a complicated code, room for improvement. But, you know, in the 25 years ago, the computer hardware has changed. You would do things differently simply because you would use a different algorithm because the nature of the hardware is different. And there's numerical methods that weren't known 25 years ago. But this is the big thing. We were successful with SPICE simulators. We solved problems, and we don't need to solve the same problems over again. Today, we have new problems to solve. Simulations requirements changed. That's the deal. Okay, so This goes through some details. We don't need to get into this. Let's just jump into why QSPICE is important and why it's going to change your life. Now, this part here is basically SPICE done right. This is basically LT SPICE, but 10 times better. You know, there's no device IV curve discontinuities. So there's bugs in Berkeley SPICE where the IV curves actually have discontinuities in it. Those discontinuities, even if they're in a unphysical part of where you would ever operate the thing, the simulator doesn't know that it would never operate there and has to iterate through that to find the thing. So if you have discontinuities in value and slope, you cannot analytically iterate to the solution that's meaningful. And I fixed those in QSPICE. The corrected device equations, and actually let me show you how gross some of these discontinuities are. So my mouse is, why is my mouse not working? I'm going to reboot my mouse. Oh, it's working on the display, but not here. Well, that is bizarre. Okay, well, I got it. We got it everywhere here. Okay, great. So this is what I mean. These are gross discontinuities. This is MOSFET channel punch through. Now, sure, gentlemen do not punch through their MOSFETs, okay? But the simulator doesn't know you're not doing that. So if it, in iteration, ends up here, it can't follow this line and end up where it's supposed to be over here. Well, QSPICE has that fixed. Some other SPICEs work like this for the same MOSFET device equations. QSPICE has all of that stuff fixed. All right, corrected device equations. This is what I mean. So these are the output characteristic curves of a JFET, whether you're using Berkeley SPICE or LT SPICE or Peach SPICE or H SPICE or you spend $100,000 on Spectre, those are the device equations. But if you go curve trace a JFET, it looks like this. So the device equations are extended so you can actually properly represent a JFET. And this is actually how I fell in love with KiCad. I had to measure these curves myself. I made a curve. Standard curve tracers are a little bit hard to use. If you actually want to develop the device equations, you need to use a pulsed curve tracer because you can't tolerate any change in temperature because you're trying to get the device equations and you can't tolerate you have to know the temperature exactly. So even if it's a small signal JFET, you have to do like 10 microsecond pulses, then wait half a second, then do it again. So you have zero temperature rise. And the other thing is that you really need to know the current. So the current measuring was done with a TIA circuit. You know, it's basically done with an electrometer type circuit. So you'd know the current. You didn't have to worry about 4-wire techniques. I could just casually connect alligator clips to my device and get these curves. So that's how I fell in love with KiCad, is making the board for this thing. And it was 8 that took my heart, and the thing that took my heart was the fact it had copper pour that really worked well. It was just a simple 2-layer plated through board with a ground plane, and it did exactly what I wanted all the time. So you can benchmark QSPICE to other simulators, and these are circuits that were collected in academia. They're not some contrived benchmark that I did use QSPICE good. QSPICE is the first simulator I've ever seen that can run every single circuit. These circuits were collected and they found discontinuities in the curves. They didn't work for reasons they didn't understand. They just collected in academia and says, we can't solve this IC. QSPICE can solve every one, and they do preposterous things like charge pump the substrate node off into voltages beyond the rails, and they're difficult circuits to solve. Now, the time step control of QSPICE is completely original. It's completely re-architected over any other SPICE simulator. And here is an example that shows what it means. This is a hysteretic switch. So the circuit is a current that charges up a capacitor until it trips the hysteresis. Then it discharges down to a voltage where it overcomes hysteresis in the other direction, so it will charge back up again. It makes an oscillator, okay? And this is actually a desirable circuit to be able to simulate accurately because it only uses one node, and simulation time goes like the number of nodes and not the number of devices. So this is a desirable circuit, but Berkeley SPICE and LT SPICE confuses time step iteration with Newton iteration and can't give you the curve working right. Well, QSPICE just gets all that straight. You know, it understands it works fine. Now, a lot of SPICE programs can't simulate this. For example, in PSPICE, it doesn't have a hysteretic switch, and that was to avoid this behavior because they knew they couldn't solve it. Okay, and you know, it kind of floated because you know. The algorithm used in SPICE requires continuous value and slope, and a hysteretic switch doesn't have that. So in the head frame of SPICE, it seems like it's non-physical, but it's not. You can buy a relay, and it's hysteretic in when it trips or not. And that problem is simply solved. I mean, it's something you can simulate. Okay, so that's one aspect of time-step control. And then here is another aspect of it. If you just put in a sine wave, in SPICE, every single one of these data points is exactly the right value, you know, to 15 digits, but there aren't enough data points to reconstruct a sine wave properly. So if you run a sine wave in SPICE and then do an FFT, your spurs will be, you know, just 20 dB down, okay? But in QSPICE, it knows exactly how many time points it needs to do, so that if you say you want 0.1%, your spurs are 40 dB down. If you want 0.01%, I mean 60 dB down. If you want 0.01%, the spurs are 80 dB down. It has no personality as far as the relative tolerance and the accuracy that you'll get out of your simulation. So that's what I mean by improved time-step control. Now this simulation, so I said that this corner is basically LT SPICE done right, okay? And this is a LT SPICE style simulation. Okay, this is basically what's inside of the models in LT SPICE. There's no IP here. I mean, it's not any particular part, and this is all next generation devices. But this is what it would look like inside of a linear tech part. Let's run the simulation. Now you got to watch fast. You got to watch close because it happens pretty fast. Okay, right click. It's done. So in this simulation, so this is the archetypical linear tech part. You know, it's peak current mode control, quadratic slope compensation, frequency fold back, and you can phase lock it to an external source. Here's the phase frequency detector, and there's the error voltage on the VCO, and does the soft start, and it comes into regulation there. So that's the point to QSPICE. That's what I was trying to take out as a mission. I just wanted to get SPICE done right once because I knew that LT SPICE was off by a factor of 10 of the performance that was available. Okay, now, back to why QSPICE is compelling. This here. This actually came because when I developed QSPICE, I was interacting with a number of IC manufacturers, and there are IC manufacturers that make power products that are wildly complicated for the amount of digital logic that are inside of them. I mean, I'm not just talking about I²C to set the output voltage. I'm talking I²C communication to set the commutation dead time, the number of pulses used to bring the switch load node to pre-charge the boost capacitor. You know, there's devices with 100 registers controlling 200 values. You know, 100 8-bit registers to control. You know, through divvying up the bit fields, maybe 100 different values, and you just can't do that in SPICE. So in what I've done with QSPICE is that you can just draw a symbol, type in some C code, and it includes a C++ compiler, and it will execute that logic as native Intel opcode during the simulation. What I'm saying is the digital logic in QSPICE runs faster than the hardware. I mean, unless you're simulating a Pentium processor, then it's the same speed. It's almost technology. I mean, I don't like to use technology unless you have lithography and ions and bakes and things. So I don't like to call software technology. But this is almost technology. It's a big thing. And you know, it uses the open source Verilator to convert digital Verilog into C++, and then it compiles it with the digital Mars compiler, the free compiler. All that's included. You just install QSPICE, those compilers are included, type in what you want, and it just works. Okay, so now another thing about QSPICE versus LTSPICE is it has unrestricted licensing. Now, it's not open source. I know a lot of you are going to, they'll grade a lot of you, but, it's not open source, but it is free. Now, by free, I mean everyone can use it, even competitors. The easiest way I can explain the business model of QSPICE is this. And I'm going to do vis-a-vis LTSPICE. Every electronic engineer has heard of Linear Technology Corporation because of LTSPICE. But essentially, no electronic engineer owns an IC from Linear Tech. They might have designed them in some place, but they don't actually personally own any of them. QSPICE solves a reverse problem that Qorvo had. No one's heard of Qorvo. But every electronic engineer owns an IC by Qorvo because they do the RF for your cell phones. So you all have Qorvo ICs in your pocket right now, but no one has heard of it. So Qorvo bought QSPICE to fix that problem. And in fixing that problem, it's unrestricted. Everyone can use QSPICE. My agenda today is to motivate you to include QSPICE in your KiCad stuff. And I'll go into the software technology to do that at the end. Okay, so it has unrestricted licensing and includes model generator tools. So if you want to use some MOSFET and you don't have a MOSFET for it, it includes separate executables that will help you digitize the datasheet. You just make the datasheet a big, a PDF of your datasheet, a big picture on your screen, and you say where the origin and upper right-hand corner is, set up scales the same, then you click on points on the curve, and it will make you a model that fits that point. Okay, it will match the saturation and the RDS-on precisely, as well as the body diode and the gate charge. It also nails perfectly, at least as well as the information is available in the data sheet. So you can do that for that. Those tools exist for MOSFETs and for diodes and for JFETs. So that's why QSPICE is compelling. There's one other little aspect to it. QSPICE is, the graphics of QSPICE is based on gaming technology. I mean, if you go into a computer store, you look at newegg.com, and you look at graphics, or you talk to NVIDIA, it's all about gaming. The gaming business is driven by teenagers' video gaming needs. That's what drives the business. And I've never used any of these games, but I'm okay with the whole thing. I mean, they need faster computers so they can score more points, so they can buy more weapons, so they can kill more space zombies. It's all in the name of progress, But what it means is, when they draw those video games, what they need to do is draw a lot of triangles fast. Okay, the image that the kid looks at, the teenager looks at, is all tessellated into triangles. And that problem has been solved so emphatically by this business that you can draw two right triangles connected with a hypothesis to look like a line faster than you can draw a line. It's unfathomable that you can draw 6 lines and fill them in and shade them and dill them and look like desktop publishing quality graphics faster than Brescia-Hans algorithm. It seems like it violates physics, but it does not, because your eye can't see faster in video rates, so it can draw a million of those before a video uprate, and you don't realize that that's what it's doing. Okay, that's the video graphics it lives off of, and it lives off that for the waveform viewer, so that you doesn't have to compress the waveform data. It can plot out lines, straight lines, 100,000 times faster than a CPU can, and I use that GPU. Okay, so it's using DirectX 12 and 2D2, and the net result is that you have desktop publishing quality graphics for everything, all of the time. All the waveforms, all the CAD, you will never see a pixel. And even on a 4K monitor, once you see what it's doing, you can't go back. You can't go back to looking at pixels. I don't know how to explain it. Here's what I mean by beautifully dithered lines. You can't see the pixels. And the waveform viewer is The user experience is entirely revamped. There's almost no modal dialogues. The problem with a modal dialogue is, okay, you look at a value and you right-click or double-click and a dialogue pops up. You have to move your eyes over to the dialogue, fill out the form, say, okay, and then move your eyes back to the part. I'm not a skeet shooter. I'm an old man. I can't move my eyes that fast on the screen. So if I look at something, that's where I edit it. And all of the, there's more hints, those hints drawn underneath what you're editing, but everything is edited in place. And the commands are accessed via right-click menus. There's not that many toolbars, not that many toolbar buttons, because the problem with the toolbar, they were great in the 90s. They looked almost like technology. But the problem with the toolbar is you have to move the mouse all the way up to the toolbar, click it, then move it all the way back. And people have shown me how great toolbars are, and I watch them edit their tool, and they're sitting there swatting at the computer telling me how great it is that they have to do that. It's not okay. It's just not okay. Everything is accessed by right-click menus. Almost everything, unless it's an unusual command. I can show some exceptions. Now, importing models is pretty straightforward. Let's see here. Control Q, and then Control B. And if I have a model here, here's a 741. I just take the file, drag and drop it over to the schematic, and it will make the symbol, and I can edit the symbol in place. And I'm going to steal that thing where you resize the symbol, the pins connect. I saw that this morning. I really like that. I'm going to steal that, and I'll have that implemented within a month. That was sharp. I'd like that a lot. I don't know why I never thought of it. But anyway, importing models is drag and drop. It's the same sort of thing where it'll run all the KSPICE models, and it should be able to run them better in KSPICE. It's a much newer simulation engine. The 45-degree rotations is supported, so you don't need different diodes drawn at different angles. And all these in-place editors work at all the different angles. Here's my little editor, and the full editor's working at every angle. These red dots here is what justification point you want. This little circled red dots, it's justified by that point there. That's the text justification. Everything is in place. It has intelligent selection guides. What I mean is, say you want to look at a MOSFET, and okay, you may have seen a selection guide that looks like this. You can sort them by RDS on or the gate charge. But the problem with sorting them with RDS on is that if you have a library of a large library of MOSFETs, some are high voltage MOSFETs and some are logic level MOSFETs. So they're you want to know the RDS on as the part is intended to use. That's an appropriate way of saying this is the RDS on of the part without further information. But what you'd like to be able to do is say what voltage you're going to run it at. It might be even a different voltage yet, and have it just compute the RDS on. So that happens. Say you want to run it at 4.8 volts. You say the gate voltage here, 4.8. You see, a lot of them are infinite because they're not enhanced yet. And you can sort them by the voltage. And that's possible because the same person that wrote the device equations wrote the selection guide. So it has stuff like that in it for intelligent selection guides. For a varactor diode, you can sort them by grading coefficient, which is the parameter that says how fast the capacitance changes with reverse voltage. Or you can sort them by the Q. Zeners, you can sort them by the Zener impedance, not just the voltage, and so on. Oh, and then for like standard parts, you have a standard value, and you can have the 1%, 10%, all the different values will be showed up. There's drop lists of all the standard values, whether it's EN96 or 24 or 12. So the selection guides are all pretty good. Same with inductors. Okay, and for plotting, this may, so when you're simulating, you want to overlay simulation results. And people that come from a SPICE background know the drill. You write a .step statement, which will step a user-defined parameter, and then you make a component value depend on that parameter, and then you get to look at the same simulation run with different values for that component. And they're used to that. They accept that. But a lot of times you just have two simulations, you just want to overlay them. So people that come from a simplest background, they just want to overlay unrelated information, and it handles that too. Let's take, okay, great. Here is, I mentioned I fell in love in KiCad because I had to do a curve tracer, and this is part of the curve tracer circuit. The curve tracer didn't use a PCI data converter. It used the USBs because I didn't want to bring my desktop computer into my lab. I just used a notebook computer. So I was basically digitizing DC levels for but a pulse tester. So I put DC levels on the thing. I would pulse the waveform, and then I use sample and holds to store it long, to store it. And the square pulse was shaped to a Gaussian so that I could use an electrometer type circuit, and the electrometer could keep the virtual ground near ground and not pop a gate while it was working. So that's the way the thing worked. We'll run this simulation. Now the way I do the pulsing is a pretty standard idea. I use a JFET working into the virtual ground of an op-amp, and I use a JFET. JFETs are usually used here because they'll have less charge injection for the same RDS(on) as a MOSFET. Standard technique. But if you get to like 10 microsecond pulses, let's look at what this thing looks like. Zoom up on this thing. And you see this is the DC level, and these spikes are the charge injection. Well, that can be handled by, instead of having this end connected to ground, you duplicate the MOSFET over here. And see, when this JFET is on, it's connected to this node, the non-inverting input is connected to ground. When it's off, it's connected to ground. But the charge injection is balanced between the two. So if I run this simulation, I can, let's do this one. And I see it doesn't have that problem. And if I want, I can just drag this waveform over to that waveform and overlay them. So you can just, these are unrelated simulations. You might have a peak current mode controller and a constant on-time controller, and they have different transient response, and you just overlay the two. They're completely unrelated things. So you have dot step, and the dot step thing came historically from the fact that was the only way you could get all of the waveform data in the same address space. Well, QSPICE supports an arbitrary number of address spaces. And one of the big things about this also is, say you want to, where is this? Do I have a good example here? That's not a good example. Okay, here we go. So here is a model of a temperature sensor, and I have some measured data here. I can take the CSV file and overlay it onto the measured data. So it will overlay CSV files or ASCII SPICE files or binary SPICE files. And you can export your waveform data to any of those formats also. You can just take a fraction of your waveforms and export it into a smaller waveform, or you can export it into an ASCII file, or you can export it to CSV. So all of that is a lot more professionally done now in QSPICE. All right, let's look at a few more examples here. Well, that was the whole curve tracer. It would work for power devices, because it used to be in the silicon carbide devices, and we'd put 50 amps into through a transistor. And this is my electrometer with a half ohm current, TA sensor. Let's see. Okay, so this is a legacy Unitrode type controller. Let's take one that's a little bit more interesting. This is the archetypical Unitrode power supply. The 3825, push-pull offline. Here's all your transformers. I'm actually running it voltage mode, but I have a current sense amp. This is done as a hierarchical design, so you can enter into these symbols. These things are just full wave rectifiers. Enter schematic. That's, you know, just a full wave rectifier. It's duplicated here for the current sense. Now, here is, let's go into the schematic. The model, you can look at the model, enter schematic, and you see the analog bits, and then this thing here isn't implemented as instanced out gates and flops, but it's just written in C. So you can just look at the source. So this is included an example, and these examples are here to show how to model parts using C++. It's an unusual style coding technique, but it's straightforward, and it's definitely worth learning. So the problem that this is solving, you know, looking at this at a very high level, the thing it's solving is that I told you I wrote LTSPICE, but I actually also implemented the majority of the switcher models myself personally. And it's laborious to model all those things in LTSPICE, instancing out gates and flops. So QSPICE solves that problem. You can model easily 100 times faster. You can probably have one individual do all the modeling for a generic S&P 500 company for their parts. It's a big deal. That's the whole point why you want to be able to just mix and mash and spill over into C in the middle of your implementation of your modeling. If you learn how to model in C, no one will be able to keep up with you. There's a number of examples like this. This is actually an MPS part. You enter the schematic. This is an older part, so I actually implemented more with gates and flops simply because it's easier to read. You know, but in C++, you can access the circuit temperature if you want to. You know, so you don't need this temperature lockout here implemented with circuits. And this is the a page of C code is all you end up writing. Oh, and there you can simulate 3 milliseconds of a 500 kilohertz switcher in 2.5 seconds on my notebook. That's the stuff that's, you know, that's what it's about. Yes. Oh, and this is, before I get into how to integrate this with QCAD, let me just say there's one other problem that's solved right in QSPICE, and that deals with the arbitrary capacitance. So here I have a capacitor, and instead of saying, giving it some value, by the way, it does handle capacitance saturation as a native circuit element. You can give it the, you know, the saturation charge, and it will just model a dielectric, you know, the ceramic capacitor saturation. It will just model that as a native circuit element. But you can, you know, roll your own with writing an equation for charge. And in this thing, this is sort of like a Van de Graaff generator where you charge a staple and you run it into another voltage, you dump off the charge, and then you come back. This is what this is a air vane capacitor. And if you put, say, a 9-volt battery to charge it, and then put a motor on the spindle, then as you pull the vanes apart, the charge will be conserved, which means, but the capacitance goes down, so it means the voltage goes up, and then you can make a higher voltage. It's like a generator, except it runs on charge instead of magnets, and you need to prime it with some voltage source. Well, in LTSPICE, you could write that, but it wouldn't solve it correctly. When you have, there's this idea of transcapacitance, where the capacitance between these two nodes, transcapacitance is capacitance at a distance. Let's start with a simpler idea. You know what conductance is? It's the coefficient that tells you the current between two nodes. That's conductance. Transconductance is conductance at a distance. It's the current between these two nodes because of the voltage between these two nodes. And then there's capacitance, which is between two nodes, and transcapacitance is capacitance at a distance. And this is using, and it's something that actually only comes up in making charge modeled transistor devices usually. But this is a transconductance example because the capacitance depends on something else. And you know, it will run this correctly, and here's the output voltage coming up to a couple hundred volts. But this is what, I don't know if there's any real SPICE aficionados here, but people who know SPICE know that if you're going to write a charge model that's complicated, as in involves transcapacitances, you don't want to write the equations in capacitances, you want to write it in charge. That's the only way to conserve charge in your circuit, okay? And that's why BSIM is so much more complicated than MOS 1, 2, and 3, is because it has a charge-based model instead of a capacitance-based model. And you know, in the 80s, you would take Berkeley SPICE, replace the charge model, go around all the semiconductor manufacturers and say, look at your SPICE, look at the circuit, see that gate voltage is dropping off to infinity. Now, however, if you run that circuit in our simulator, it doesn't run off to infinity. Your simulator doesn't conserve charge. That's why you pay us $50,000 for our simulator. That was the business model in the 80s for SPICE houses, okay? Well, so this is all based on the idea that you can't conserve charge if you write in terms of capacitances. That's only because you don't integrate the equations correctly. So in QSPICE, I add a corrector step when I'm integrating the differential equations. Here I say the capacitance is based on something, and it conserves charge. And that's basically because I've added a corrector step to the integration of the differential equations. That's original to QSPICE. You know, you can buy this from Spectre or HSPICE or whatever, and they don't do that. They just don't have that technology. They don't have those numerical methods implemented in it. All right, that's enough of all that. Let's get to KiCad. So the idea is, so QSPICE runs many processes. The schematic capture, now the schematic capture might have many windows because of all the child schematics, okay? But the schematic capture is one process. The simulator is another process, and the waveform viewer is a third process. So, and the inter-process communication is now all completely documented, and I can coordinate with you guys to iron out any problems you have. But the idea would be you would draft in KiCad, and you would use QSPICE to simulate it. And on Windows, you'd also have a waveform viewer. I can compile the simulator for Linux, but I don't have a DirectX 12 and Direct2D capability in Linux. I mean, there's people that kind of fudge it, but it's not correct. It's emulated with the CPU, and instead of being 100,000 times faster, it's 100,000 times slower. So that's not an option for me. Yes, I understand that you can't be a self-respecting software engineer and use Windows, but you know, if you're agnostic, you just do with what you have to do, okay? And as much as I'm a native C++ speaker, I am a native Windows user. But I was a Linux user in the 90s when I was, you know, and I was the first person to port SPICE to Linux. I understand, but unfortunately, it does not pay the bills. Okay, so this is the idea. This is the way it would look. And what do I have here? Do I have oh, yes. And this is the help documentation. And there's an appendix I've added that is documents the inter-process communication. So the schematic capture program basically creates this process. I pipe the netlist to that process, just not to make any temporary file clutter. You could have it as you could write it to a temp file and give the simulator the file, the netlist to read, but I just pipe it with an anonymous pipe. Then this is the process you do to start the waveform viewer. And then if you want to run post-processing, you know, like, you know, execute your .measure statements and your .for statements, that's how you'd run the post-processor. And those are all the message numbers. It's who's talking to who and what the two parameters are and a description of what they do. So that's what I'd like to see happen, is you, for KiCad users, you'd replace the QSPICE schematic capture. Not that I mean, the QSPICE schematic capture is perfectly fine. It's not that great for PC board integration because it doesn't even have multiple parts per package. Okay, it's not a PC board schematic capture tool. But you would use your schematic capture tool and then have QSPICE simulate them. And that's the overall flow of it. Was that exciting? Let's see, is there anything here? Yeah, so what do you guys think? You. Thumbs up is not thinking, you know. I appreciate it immensely, you know. But, yes, sir.
Pardon me. Super cool. But I know one of the big principles of KiCad development is being platform agnostic, and I think that's going to be the main hurdle to adoption here. Is that, you know, I'm a Linux user. I don't own a copy of Windows, and so I couldn't, with the system you're proposing, view any waveforms. And I don't know. That's all I wanted to bring up.
Yeah, I'm aware of that. The choices made for QSPICE came from, that was hit me with two prongs. I understand loving Linux. A self-respecting person doesn't use Windows. I get it. It's okay. But the things that, the two prongs that hit me to totally go down 2 feet with Windows, one was that the graphics is such an important part of simulation, and nothing is close as a Windows. I mean, you know, there's this, you just don't get a direct 2D implementation with a very smart GPU in Linux. You know, people don't put multi-$1,000 cards in their Linux machines. They might to dissipate heat, but they don't get much use out of them, and I use that. That's one reason. The other problem is that I am from the semiconductor manufacturer side of things, okay? And I go and talk to, well, with LTSpice, I actually spent more customer face-to-face time than any other person in the industry. I would log about 20,000 hours face-to-face with customers per year because I would travel the whole world. I was on a different continent every month, talking to many people all over the world, and I didn't see one person use Linux. Okay, I know that CAD is often towards Linux, but people doing, you know, light industry design of circuits are using Windows. And the fact that they have this technology that isn't agnostic on platform is why I'm in Windows. Okay, that's it. But I love you dearly, but you know, maybe someday, maybe there's a Vulkan method. The OpenGL was a complete disappointment. And it's not like I haven't developed GUIs on other systems. You know, there was a Mac version of LTSpice, and I wrote that thing. I wrote the whole thing. I wrote the whole, you know, all of it in the Mac version. And honestly, developing on a different graphics library, the way I describe it was, before I developed on a Mac, I felt that if I were traveling through the universe and came to a different planet, I would be able to tell the difference between life and a rock. After developing on a Mac, I didn't believe that anymore. It was so different. It shattered that belief that I had. And so, you know, maybe the technology will come to Linux and it will be, you know, enjoy some ubiquity and be, yes, this is the solution is going to go. And then maybe at that point, I will write a waveform viewer for Linux. And actually, the waveform viewer is a lot harder than, I don't want to, yeah, waveform viewer is the hardest thing. And so if I could get the waveform viewer running on Linux, then maybe there would be a Linux version, an agnostic version. But for now, those are the two prongs that hit me. Having spent 20,000 hours per year talking to customers and where the technology is sitting, what's driving the graphics business.
Yeah, different direction, but I wanted to, I guess, provide an anecdote. So I
loved your talk, by the way.
Oh, thanks.
Just so you know.
Well, so I have two different, actually probably three different things, but we'll just keep it short. I just wanted to say, just to maybe provide some, anecdote about, I think about 2 years ago, it was like fall of 2023 that I didn't do it, but one of the guys that works for me, we we wanted to do a simulation, basically of like a hysteretic mode current source. This was the only thing that could do it with minimal fuss. And the only reason I knew it could probably do it because I had read an article a long time about some of the computational methods in QSPICE, and that when I heard that you were involved with QSPICE, I was like, oh yeah, we're gonna do it, and it works obscenely well for like nonlinear switching. Then that led on to design of a sigma delta converter.
Oh, okay.
Which I mean, effectively is kind of the same type of problem. It's just it's weird, and it's like to converge on that's hard. The other place, and I don't know, you may have come across people using it, but when I was in grad school, like one of the best courses I had, and he was on my thesis committee, who taught acoustic transduction, and everything we translated basically into a circuit, but it was kind of like a circuit that can model three-dimensional behavior. At the time we used LT-SPICE, and we'd write equations and kind of get it in the system, but there are people doing, electroacoustic, transducer design, but using, because there was one circuit element we needed a gyrator. It's kind of like a transformer, but different, right? It inverts one component. So just to, I don't know, provide an anecdote.
Gyrator is a transinductance.
Yeah, it's something that you don't like, you don't go
It's
to
like an old radio. They didn't have a variable capacitor. They had two in coils, and you would rotate it, and you'd tune the inductance.
When we developed some of the models to model behavior in, radiation and things in acoustics, you actually need that model. It's not like you go to DigiKey and buy it, but just to, it really is for those types of things extremely useful to the point where, for me, like a KiCad integration would be great, but it's like I always separate problems of, there's the problem of putting things on the page. How do you do that? And knowing what goes on the page. Like this tool helps me figure out what do I actually need to put on the page in my final design. So having two separate is actually fine, but integrated would be great. But knowing that like the numerical methods are just awesome, like the equation solver. So just want to provide that.
Well, thank you for all that.
Well, and the Verilog part too, I didn't even know that. So that's the other piece. I do a lot of like HDL and simulation, and that's just really interesting.
There is a big difference between making PC boards and doing circuit simulation, and the thing about circuit simulation is what it does is it develops your understanding of the circuit. Okay, it's how you nurture your intuition, so you can so you know what you need to do to test something, because not everything, you may not have modeled something over temperature, but after you see the circuits and get familiar with it and becomes part of your intuition, then you know what you need to do to test it. I mean, the whole point of simulation is just to understand the circuit better, and so it assists in knowing what to put on the board, what to put there. It assists in that process. It helps flush out the way you feel about what you're choosing. That again, it takes a tangent in what you're saying, but when you talk like that, it reminded me of something that people miss. Because people don't know what the point is of simulation. They think it's, that's how you verify design, or someone else might say, well, it's a sanity check. Well, it's not how you verify design. Simulation models don't have production scatter. So what are you going to do? You can't verify your design with simulation. That's abject nonsense. And is it a sanity check? If you're worried about your sanity, you should talk to a therapist. It's just, it's nonsense. The whole point is to cultivate, to nurture your intuition of the circuit. That's the point of simulation. And which is different than getting, the contract done to make the board and make everything work and get paid. It's a different thing. It is a different thing.
I think I'm up next. Just was curious if you'd ever considered, when you were starting QSPICE, if you considered doing an open source piece of software, and what the reasons were that you chose to keep it free but not open source.
The full story there is that I got sick of LT-SPICE and I wanted to make it open source. But I mean, Linear Tech had paid me a buttload of money to write the thing. I didn't own LT-SPICE. I had written it, and I was the only person that wrote it, and I wrote all the models, but I didn't own it. And at that time, ADI had bought Linear Tech, and they didn't like that idea at all. And the result was that I left the company. QSPICE, like I said, it was like my way of saying I'm sorry, just get it right once, the whole thing right. And what the business model would be, I was going to, again, respect ownership. I would sell it to somebody. If they wanted to make it open source, it would be open source. If it wanted to be free for everyone to use, it would be free for everyone to use. In fact, I did not call it QSPICE. I called it SPQR, and I called the company Marcus Aurelius Software, and the simulator was called Caligula, and the waveform viewer was called Vespasian, because you can't trademark these things, and it was a way of telling the person I was going to sell it to that you will name this. Okay? Honestly, I knew the simulator was going to be called Caligula. Everything else was camouflage because all SPICE programs have evil names. You know, SPICE was originally called Cancer. And Larry Nagel's first job when for his master's thesis was to think of a nice name for this program because the dean says we're not going to have a software project on this company called Cancer. And you know, this is in the 70s, and if you're, you know, you might be able to reflect on what the concept of taste was in the United States in the 1970s and understand there can't be anything nicer than spice, so we'll call it SPICE. It was another in-your-face name. And then other simulators like Spectre, well, it was written after the James Bond novels. There's no way it wasn't named after the evil empire. Like, they all had evil names. So I thought I would call my, you know, why not just finish it and call it Caligula? You know, be as bad as possible. Because I wanted to completely rethink how a SPICE program should work, completely rethink the time step control. And who rethinks everything more than a despot? For they rethink the very nature of good and evil. You know, it's like no despot thinks they're a bad person. You know, they are who they are. They're not a bad person. They rethink the very nature of good and evil. And that's why it was going to be called Caligula, and that was its code name in-house. And then the waveform viewer was called Vespasian because he built the Colosseum. Real bad guy. Just real bad guy. Maybe even worse than Caligula because he did it on a mass scale. And in Italy, everybody hates Vespasian more than anything, you know. But, you know, the Colosseum is where you sit back and look at everything, you know. It's where you kill those parts with too many volts, you know. So it was going to be Vespasian. And the post-processor was Romulus, because in Western history, the last legal emperor, last Roman emperor was Romulus, though, you know, the last Roman emperor was actually Constantine in the East. But I called him Romulus to stick with the Western version of history.
So points on Windows, well understood. I had one confusion point I wanted to clear up to understand. You had mentioned briefly the simulator could be possible to compile to Linux, and I was wondering if you had ever considered maybe just compiling a simulator binary for Linux and seeing if you know, the development community could try to tackle waveform presentation.
I have, because of other work I'm involved with, I have it compiling under Linux. If someone wants to write a waveform viewer, you know, you can. It'll be the waveform files are bit identical between Linux and Windows, so you have your test vector, and then if they have a working waveform viewer, let's just go and get the thing, you know, properly operating system agnostic as it should be. Yes.
We'll pass the mic over to you. So when it comes to designs, when it comes to designs, like things that we simulate are not necessarily the entire design. So like maybe an analog or same active filter, or take your pick, right? Can you speak to like best practices when it comes to like isolating the things you want to simulate versus things you don't?
Okay, very good, excellent. And this is one of the things where there's a bit of a disjoint between PC board design and circuit, you know, the schematics you use for simulation. There's a disjoint there. Now the thing is that engineers break big, unsolvable problems into many smaller solvable problems. That's what engineers do, and that's what engineering is. Okay, so if you can break it into a smaller part and understand that smaller part by itself, that's what's the right thing to do. That's good. The risks there, and the reason why you want a simulator that can handle a bigger, smaller part, is so that you don't have to make as many simplifying assumptions, so that the smaller simulation that you develop your intuition on is not a literal representation of the real part. Let me just run an example. So here we have a, this is actually a Qorvo part. And so you can't do this simulation in most simulators. You know, this is actually an I2C control. I2C is a native circuit element in QSPICE. You just tell it here, you know, what address you want it to talk to and what data it does. And then when this thing gets, when write gets a positive edge, it just spits that stuff out. And so in this simulator, this part is part of a cell tower power supply. It's also used in military radar sets. And it, I think this one has 62 I2C registers controlling about 100 parameters inside. And it's the soft start. It's how the soft start behavior switches over to a low pass filter if you put a reference, use it as a reference voltage instead. It's the commutation dead time. It's the gate voltage. Here I'm using GAN FET, so I have to be careful with gate voltage. Anyway, when I run this simulation, that's the I2C clocking in data. Okay, and you know, it has no impact on the simulation speed of the rest of the controller. So that's a half-bridge simulated thing. So what I'm saying is here, I did not. The nice thing about a good simulator that can handle more complicated circuits is you don't have to simplify the thing. You don't have to say, oh, I sent these I2C registers over to the thing. Well, this one actually won't even turn on until you tell it to with a command. Yes, you should always simulate as small a thing as small a circuit as possible, but you have to be careful of simplifying assumptions, and you would like the simulator to make it so you don't have to make as many simplifying assumptions. You know, you won't see a power IC that's controlled by I2C CAN or SPI, where you don't just somewhere say, oh, these are these values, and you stick it into the back of the part through, you know, as a global parameter. You know, you actually just simulate the literal circuit. So it makes the process less error prone. Now, what I'm trying to say is, yes, break your big circuit into smaller circuits, and then there's a disjoint between the circuit that you use for PC board generation and you're simulating, yes. But don't try to simulate a literal version of that smaller circuit. That would be my advice. And if your simulator can do that, you're ahead of the game. It just makes the process less error prone. I mean, hardware engineering is just like software engineering. You do everything just to make it less error prone. That's the whole front and center part of software design, is you do make this, you know, how can I get this thing working? Yes, with no overhead, but no errors in it. Because that's what takes time, is fixing the problems, fixing the bugs. And in hardware, it's even worse, because then you have to get more boards from China, and then, you know, what are you going to do?
Oh, netlist-wise, is the format the same as for LTSpice?
For the, mostly yes. The differences would be that the C blocks, there's no analogy in LTSpice. And I use, the C blocks have variable number of node names. So there's 3 groups of ports encapsulated in what are called gimlets. They look like the German double quotes, because that's not a valid character used in SPICE, so I get to use it for something. So I say, these are the input ports, and then I can say, this is the ground. I can hot deck my logic, so I can say, what's the ground of that DLL? And then I say, these are the outputs. And then the first letter is an O with a slash through it, the Norsk O. It looks like a 0 on a 70s computer terminal. So that would be different. Another difference is that LT-SPICE uses A devices, and QSPICE, I wrote those things over a Memorial Day weekend, and I just really don't want to ever see those things again. They're not, it's not a good, I'm not happy with it. They're not implemented correctly, okay? And you have to go through a lot of convolutions to design large amounts of circuits with those, using those gates and flops. So the A devices are not there. And I don't use the A device for anything in QSPICE in case at some point, I mean, because QSPICE is free, if Analog Devices wants me to include the A devices, I will. But I don't like that mixed mode simulator. I've written a lot of them, and that's one of the worst ones I've written. So I don't believe it anymore.
So you still have, for example, this capacitor primitive in QSPICE. It has a built-in ESR.
Yes.
Okay.
Yes, there's a built-in ESR for capacitors, and then additions there is you can say VSAT for the saturation voltage when you start losing differential. If you have a ceramic capacitor, there's 3 points you can give to have the thing saturating with charge. The initial value, and then you can pick a point here. Say at this voltage you have this much reduction. So it's VSAT and SAT frac. So you can pick any point along here, and then it's the CSAT, the value asymptotically approached. Because if you just use a hyperbolic tangent, the capacitance vanishes at high voltages, and you can't solve the circuit. It's not physical. It doesn't work. So you specify the value asymptotically approached, the initial, and any point in there, and then it's going to have the right second derivative through the whole thing. Is it going to match more points? No, but it's probably okay. And same for inductors.
Oh, nice.
Oh, and it has a transformer that has. I can show you the transformer. Here's the thing. I forgot to say this. If you haven't used QSPICE, the first thing to do is run some simulations. So under File, Open Demo, these are just examples contrived to try to teach you something. And here under Transformer Saturation, we see a transformer, and I'm going to run the simulation twice with the load connected or not. And I say and you see if you disconnect the load, the thing saturates, yet if you connect the load, you pull flux out of the transformer and it doesn't saturate. So you actually need more current if you don't have the load connected. And there you see the values. It's ISAT and LSAT, what the saturation current, what current saturates it, referred to the primary, and then the turns ratio, and you can pull flux out from as many secondaries as you want. And that's another part that's different. That's actually, it looks like an X, but it's actually a cross. This is not a sub-circuit. It's actually the multiply symbol. I don't know, it's like 200, ASCII 200 something in unsigned charge. And it has also variable number of ports with little gimlets, little German. Here, view. Netlist, there's the X device, and that's the symbol that I mean by gimlet. Okay. And that is collecting the ports. It has to be an even number of ports because it'll be the primary, secondary, and it doesn't matter how many secondaries you have there.
Thank you.
Okay, if there are further questions, I think that Mike will be available during the break here. But I want to thank Mike Engelhardt for a very inspiring talk.
I really appreciate your interest, okay? I really appreciate your interest. And I'm sorry about LT-SPICE.
Okay, our next speaker this afternoon is Amit Bahl. And Amit, if you want to go ahead and set up, So Amit also needs no introduction. He is the PCB guy, and he is currently is the Chief Revenue Officer at Sierra Circuits. Sierra Circuits is a awesome little PCB fabricator up in the Bay Area. He earned his Bachelor's of Science from UCLA, launched a career in Silicon Valley, and he has been working at Sierra Circuits since 2009. He dedicates his hours to democratizing design for manufacturing best practices and guidelines for PCB designers and engineers. His mission is to simplify the PCB design journey. Today, we're going to hear about how you can use KiCad 9 custom DRCs to avoid common DFM problems from a manufacturer himself. So please give a warm welcome to Amit Bahl.
How's everyone doing? We're having technical difficulties. Hello. Okay.
I'll take your laptop here.
How do I? Sorry. How do I get it to?
So that should, if you present. Oh, actually, it didn't click on. Oh, there it goes.
Oh, it didn't click on. Okay.
Seems to. There you go.
All right. Thank you. I thought I would mix it up a little bit and talk about PCB manufacturing and DFM rules. How many people are bored of that already? It's all I talk about. Yep. No problem. Is that yours? Okay. So, you know, in designing a circuit board, you have to take into so many considerations to end up with something that actually works. It's like a miracle every time. Thanks for laughing. So I'm going to try and run through some basics, okay? And if anyone wants to dive into something deeper, please tell me. And if I have more to say on the subject, I would do that. But basically, when you think about PCB design, always start with your stack up first. How many people have designed stack-ups that are more than one lamination? Okay. So how did that go? Yeah, more than one lamination causes so many more complications in fabrication, so hopefully I can touch on some of those. You have to pick your PCB materials not just for electrical properties, but also for manufacturability. So that's like the first kind of thing. Then you get your stack up, and then you have to actually lay out your board. Forget components for a second, selecting components. So you have to lay out your board in a way that is etchable. And then balance all of that with, hey, does this thing perform electrically? Because really all a fabricator and an assembler is responsible for is to make sure that it meets a spec. And that's it. Not really that it works for you, but that we've manufactured to a spec. That's literally the thought process of a fabricator. So there's just a lot going on in there. So DFM is a thing, and it's very important because for a couple of reasons. First is you'll be as close to having something that works at the end of the process. Number two, if that board is ever going into anything serious or going into production, you'll be passing on something nice rather than a nightmare. Just a quick story. We're building a military board right now that was designed 10 years ago. And that board, that design literally is bouncing around from PCB shop to PCB shop because no one wants to make that board because it's impossible to build. It's not that difficult. It's impossible to build, but the scrap is so high that no board shop wants to make it. Somehow we got stuck holding that bag. And so we're building it, but literally every single month we raise the price because we can't lose money on it, right? Otherwise, why would we want to build it? And that customer keeps sending us an updated PO with an increased price because they have no choice. So this is, you want to avoid that at all costs, right? It's like, do good for the world and don't design something without going through a DFM process. So that's what this is about. Is that motivation? Was that story motivating? By the way, I invite anyone to come and tour our factory and run one piece of equipment one time without getting your fingers chopped off. Okay, so when you pick your PCB materials, if you guys haven't heard, you need to really think about what the dielectric and core materials are when selecting that material. How many people know what a core material is? Okay. You guys probably know more than I do, but I'm up here. So if you have a specialty material like high-speed materials like a Megtron or EMCs becoming popular, any kind of high-speed PCB material, it's really important to make sure that your fabricator either stocks that material or you communicate ahead of time and they order ahead of time, because material delays happen. It's a practical part of the business, and a prototype that is waiting on PCB material is not really a prototype anymore. And I have a lot of customers that aren't really happy about that, but if we don't have the material, we don't have the material, right? So pick materials and cores that your fabricator possibly has in stock, and you would have to know the core materials, especially in any high-speed designs. You want to work out that stack up ahead of time. So, one point in terms of a DFM is you want to make sure that the materials you pick are appropriate to your design specifically. And one of the things that a manufacturer has to consider, and the designer should also, is there enough, let's say, prepreg to melt during lamination to properly bond your copper layers together? And I know it's a little nuanced, but a class 3 board requires 2 plies of prepreg in between copper cores for just that reason, because you don't want to end up with a board that has voids in the materials or any potential of separating, which is called delamination. So that means that even after the board fabricator has built a good board and checked that there's no issues, that you could still have delamination after the board is in the field, which is the worst case scenario. So you want to make sure that you pick a material that flows properly for your design. And really what that means is that if you have a board that has a nuance, your fabricator is going to find out about it and really give that feedback to you. And that is the point of prototyping, right? Don't just throw it over the wall and expect version 1 to be perfect. So going back to the nightmare I was describing, that designer designed a very large board with a very uneven copper distribution on the cores. So core is, again, copper on both sides. One part of the core was, 2 ounces of copper, flooded ground basically, and the other side was very long, parallel 3 mil traces, and that makes etching very hard. It makes all sorts of kind of imbalances in the construction, and hence why very few American fabricators can build it, and lots of scrap. And they can't change the design because it's ITAR and military and 10 years old and all of that. So I kind of talked about those. This is a video of a highly paid blue-collar worker that is basically putting together what's called a book, putting together the cores, putting together the prepregs, and then, per the modeling, and then putting it into a lamination press. How many people have seen a lamination press? Ooh, less people. I again invite you guys to come. But this is a lamination press. We have oil lamination presses to apply heat evenly across the sheet. Because if you don't apply heat evenly, then some places will melt more, some places will melt less, and then you have the delam issue that I was talking about, or any kind of voiding you might have. So that's what lamination is. The next kind of thing to think about in DFM is copper etching. I alluded to having very thin traces on one side and very thick amount of copper pore on the other side is very hard to etch. The other thing that's hard to etch is when you have heavy copper. You end up with these trapezoidal features. You end up with areas where you can't etch out to properly, have a nice clearance. And this is where the designer really plays a big role. If the designer can add enough spacing where they need to, then even if you have a little bit more copper, like a 2 ounce or 3 ounce, the manufacturer won't have any problem etching out the copper that they need to. So knowing which cores you're using, what the copper weight is, and what is the spacing that you can design to so your fabricator will really not have any problems. Does that make sense? Spacing? Yeah. So this is not trace-to-trace spacing necessarily. This is also basically any copper features. So if you have like a trace next to a ground pore, what's the spacing there? It should be at least 10 mils of spacing, and then if you have heavy copper, it should be more. So here are some very common etching issues. First one is the uneven copper distribution, which I was talking about. So one thing I really like in the new KiCad is the way you can control your zones, and you can, really kind of more automatedly, pour your copper, which is great. And then if you want to move some traces around, you can then re-pour your copper. If anything that a PCB design tool can make it easier to pour copper properly with enough spacing per your DRC rules, you're going to get a better electrically performing board, and it's going to be easier for your fabricator to etch. And then also in lamination, things will stick together. So all that, you get all of that with a nice copper pour. And I didn't even mention, electrical, better return paths and, less EMI issues to deal with later when your design's done. So all that is because of copper pour. So how many people use copper pour efficiently? That's good. Preaching to the choir. It's good. All right, so the other issue that can happen is sliver formation. So it might be hard to see, but if you look up where there's arrows, you don't want like this little bit of leftover resist in our etching process, because that can flake off during plating or etching, causing all sorts of problems. So be careful of not having inadvertently designed in any slivers. And the other item here is basically, how you really, kind of keep copper from the edge of the board and not have any exposed copper after someone's done routing your board. The next big area is designing your via structures. So a few of you had mentioned, or a lot of you had mentioned, that you've done boards with multiple laminations. So it looks like in KiCad 9, you really have a lot of leeway on designing your different pad stacks and drills that go from one layer to the next. Maybe they're blind vias that are really tiny. Maybe they're mechanical subs, mechanical drills for your subs. These all have different design rules for annular ring and different design rules for aspect ratio. So all super important. So it looks like KiCad 9 really supports that well. So for a mechanical drill, even though the mechanical drills are getting really good and are very accurate, almost as accurate as laser machines, people still want, fabricators still want larger pad sizes for your mechanical drills. So you should aim for a designed in annular ring of as big as possible. So maybe 7, and if you can't do 7, a 7 mil designed annular ring, then 6, then 5, then 4, then maybe your fabricator might say, sorry, that's a little bit too much now. You should never push your fabricator. So the other option, the other thing to consider is aspect ratio. So if you have a sub, like a 4-layer sub or a final through-hole drill, mechanical drill, we're plating the sub separately. We're plating the final through-hole mechanical drill separately. So in those scenarios, you want to make sure the aspect ratio is right for that plating process. Also recognize that when you're plating a sub, that inner layer can be considered an outer layer. And so you're not processing an inner layer, you're processing an outer layer. And there's different design rules for outer layers versus inner layers. Okay, so also for drills, other than aspect ratio, annular rings, pad sizes, is drill to copper. Drill to copper is a little bit tricky because when the way that we like and most fabricators like to see the finished files is to see a finished hole size plus or minus a tolerance. And then most manufacturers will drill larger than what you specify as the finished hole size. And in that case, when you're drilling larger, you could have that drilled hole wall too close to another copper feature, maybe a ground pour that I was referring to earlier. And if that clearance is not at least 8 mils, then most fabricators would have a problem. And the reason why fabricators would have a problem is that PCB materials move around a lot, and they especially move around after lamination, and that's called misregistration or registration issues. So every fabricator has to deal with how to realign drills after lamination before plating. And so most fabricators are looking at the data, trying to figure out the scaling, and then they'll drill. But if you don't leave enough spacing from a drilled hole wall to the next copper feature, if it moves around a little bit and the drill wanders during drilling, all these can happen. You could end up with a board that is quasi-reliable. Again, maybe it went through testing, everything's good, but then when it gets into the field, you have field failures because of a problem like calfing or any other kind of vibration or expansion and contraction. These are all real issues that can happen. So having a board that's functioning after manufacturing is not still necessarily a reliable board. How many people design for aerospace? A couple people. So in aerospace boards and Class 3A boards, you have a wicking requirement, and wicking is essentially the acknowledgement that after a board is built, even though it's good and electrically performs, you can have field failures with copper, migrating and wicking through the materials of the PCB. So it's a real issue that has happened and plagued the industry. That's why you have different requirements for flight boards than Class 2 boards. How many people work for SpaceX? Okay, good. I can say something bad about SpaceX. So SpaceX literally has been designing to Class 2 boards and then wondering why stuff doesn't work. I recommend that you follow IPC class specifications. You will get a more reliable board. I know it's a groundbreaking suggestion, but I'm not cheap. I don't know. Okay, so enough about drilling. We talked a little bit about annular ring. Another thing that KiCad offers is teardropping. So teardropping is great because it gives you a little bit more leeway as a fabricator if the drill doesn't hit directly into the center of the pad, or because of scaling, the drill needs to be offset a little bit to basically find the best center across all your layers. You have a teardrop, and so that kind of helps a little bit with, not having to scrap a board and restart. And obviously, I'm talking about designs that are a little bit more complicated, a little bit tighter. But teardropping is great practice, no matter what kind of a design you're doing. So what the picture you see on the slide is breakout, and breakout does give you a decent electrical connection. But for Class 3, it's not okay at all, and for Class 2, it's okay. But people probably don't like to see that. But it's fine for Class 2. That's why you don't want to put that in space. This is just a quick video of laser drill. So laser drill is great because it has really good registration, and of course a laser drilled hole can be very tiny. Down to 3 mils is what we consider as pretty much standard. However, it really just goes from one layer to the next. So if you have a laser drill from 1 to 2, that's still only one lamination, so it's not going to really increase your cost very much. But if you start having laser drills from 1 to 2 and then an offset laser drill from layer 2 to 3, that's basically 2 laminations at least. And every time you have a lamination, it's basically going through the manufacturing facility twice, and that really does increase cost and lead time, and it's not conducive for quick cycle time. So you can definitely get benefit for laser drill. You can even get cost reduction with laser drill, but you have to really think about it and plan your stack up ahead of time. I dedicate this slide to solder mask. I don't think solder mask gets enough attention. Does anyone have any assembly issues ever? It might not be because of the assembler. It might be because of the solder mask design. Seriously. Because we assemble also, it's my assembly shop is always blaming our fabrication shop for poor solder mask. But sometimes, you know, it is the assembly. It is our own assembly shop. But be aware of your solder mask. So solder mask web, I think, is the key thing. Most fabricators that don't also assemble, they would ask for, if there's not enough solder mask web between the pads, they would ask you to remove that web, you know, and that's called like a gang opening or a window. Well, that's very easy to fabricate, but very hard to assemble now, because the purpose of solder mask is to prevent solder from, you know, bridging and things like that. So they just completely eliminated the purpose of solder mask. So yeah, so we don't ask for getting, you know, asking for windows anymore in the solder mask. Instead, we ask to maybe add a little bit more webbing, encroach the opening onto the pad a little bit. That's also okay. And just get a bigger web. So we like a 4 mil web. I think most fabricators are down to 3 mils. We're special that way. And if you have anything other than green, definitely have a bigger web, because these other colors, even though they look really nice and pretty, they're hard to expose. They're hard to process. They have a different processing window than green. So you want to design to a different color of solder mask. Did everyone know that already? Oh, I got someone who didn't know that. That's good. I'm going to pat myself on the back. All right, it was all worth it. Yeah, different colors process differently. So, and if you're going to have like a tight, dense design, probably just go with green, or really ask your fabricator what their tolerances are for the web. Silkscreen also deserves a shout out. There's a lot of designers who make their silkscreen kind of impossible to read. AOI at assembly does use silkscreen. Did I say solder mask? Does use silkscreen to, you know, look for, you know, pin 1s and to make sure the components are rotated properly and to make sure it's putting the right component in the right spot. So silkscreen is still definitely useful in assembly. So try and design your silkscreen so it doesn't get clipped away by the fabricator, because, you know, there is no, it shouldn't be allowed to have silkscreen on top of a pad. That would also be a problem. So just be aware of your silkscreen, and you're following the guidelines for that. So just a couple of sentences about what you should do before you send your design to a fabricator. I'm really encouraged by all the power in KiCad, being able to set up custom DRCs, being able to set DRCs per layer. So if you have like a core layer that has 2-ounce copper, you can set spacing guidelines differently from, let's say, other signal layers that have 1-ounce copper or 1/2-ounce copper. These are really powerful features, and, you know, KiCad is making that available to you. Absolutely set as many DRCs as you possibly can. That will help you later on, you know, when you're about to throw the files over to the fabricator. The second thing is KiCad supports ODB and IPC. I know people love Gerber. I would never use Gerber. I know that's hurtful, right? Well, if you do ODB or IPC 2581, you can kind of visually check it and make sure it is what you designed. You know, Gerber is, I would say, just old. And it has no information. It's basically, you have to send all these other informations with it because it doesn't have anything. And for an assembler, it's almost impossible to assemble with Gerber. You have to recreate ODB or 2581 to assemble your boards. So if you're going to send, you know, files to us where we do fab and assembly, you know, we basically need ODB or IPC 2581. And KiCad has you covered on both those formats. So I think it's a no-brainer for that. Second, you want to verify early on that you have picked components that are readily available and you have a well-formed BOM. You know, even though COVID is like kind of, we're over the worst of it, there's still supply chain disruptions. There's still delays in components. I don't know why. Maybe you can ask Corvo. But we experience it day in and day out. Even if DigiKey says they have it, maybe they don't the next day. All this type of stuff happens. So if you can pick a component that's readily available or that your assembler has on their shelves, all the better. So these are a couple of things you can do ahead of time to make sure that your order goes really well. And, you know, lastly, fab notes. Where's my, oh, I thought I had fab notes in here. But make sure your fab notes really call out anything, you know, special. Maybe you have edge-plated holes. Maybe you have tolerances on your cutout. You know, maybe you don't want any contamination in a certain area. You're very sensitive to a certain area of the board. Anything special at all, that's what fab notes are for. You can copy fab notes. Please don't tell anyone I said that. You can copy fab notes, but read them before you send them to us. Yeah, fab notes are important. We read them. If we don't, we get in trouble. So you should read them too. This is some of our, you know, our overall kind of like, hey, what do we check for at each stage for DFM? We have a really nice DFM guide that's out on our table where Lucy is manning. She's a very wonderful lady. You can talk to her. She's out there. She lugged all these crazy design guides, which have great information. So I am pitching you not to buy a circuit board, but just to pick up a design guide and say hello to Lucy. And with that, I think I'm over. I'm done. Thank you.
I am so happy you brought up fab notes.
Thanks.
Well, no, I actually know, because I've been through every possible iteration of every way of doing it through different companies, and I always want to understand the perspective from the other side. When you're a hobbyist, you don't even know those things exist. When you're building things and there's money on the line, they're important. Like, for example, Altium has a tool called Draftsman, which is beautiful. You can make a readme.txt. I've been trying, and I redo the workflow, it seems like every year, about how to standardize so my process is quick, but also so it's quick for the person on the other side. And maybe you could comment, what would people like you want to expect, or are there standards? I would love it if the IPC file could just bake it in, because it's like such an important thing. So yeah, so I'd just love to hear your thought on that.
Oh, I think that's an amazing idea, because, you know, we get fab notes that make no sense. We get fab notes like fab note number 7 says one thing, fab note number 12 says the exact opposite. It's just kind of all over the map, and people do what they want. And you know what? I think that's an amazing idea, frankly. And you should join an IPC consortium just for that. It might suck up some time, but.
Well, I think where I'm is one thing I'm passionate about it when I'm looking at KiCad. You can certainly do it in the PCB doc and the schematic of. Sometimes it's figuring out a way that you can minimize time and get maximum value, and everything from where's pin 1 on that LED and just where should conformal coding go, and so the outputs are nice and clean, and you can get the happy button, as I call it, just to generate docs, because I'm guessing you receive them in like on carrier pigeon, like smoke signals, whatever. So
It happens.
yeah.
Yeah, we got a CD the other day. I was like, what?
What?
Something that Sierra has done, and we're very open with information. And on our website, we have a knowledge base section, and it lists out what the fab note should look like, at least what the bare minimum information. So if you're designing edge plating, or if you're designing, conformal coating, or whatever special feature you may have, what would the fab note look like? And honestly, one of the number one things is, what are the surface finish specs that you should call out? Like, some people still, ask for 100 microinches of soft bondable gold, which is going to cost them a fortune, and where it's sometimes not needed, or ENIG that's, there's too much gold, even per IPC that they're calling out. So we've put all those basic fab notes there on our knowledge base. We also just recently put together a checklist for designers that we'll make available. That's what we've done. I think there's other questions.
Yeah, so along a similar train of thought,
Yeah.
Precisely speaking, where and in what form do you prefer to have the fab notes? You just want a PDF thrown in with the rest of the design files? Here's a zip and here's a PDF of my Word doc of me typing things out. Is there what is... I understand you can do a lot of things, but what is most digestible for you, the fab house?
Yeah, I think having at least one layer in your design that is basically a fabrication drawing, and then also outputting that into PDF as well. Okay. Because our, obviously we can view data, that's not an issue, but, it's also very convenient to have it in PDF, so anyone on the shop floor can pull it up and things like that. So I think having your fab drawing as a layer, as well as a PDF, is just perfect. Is fine.
And by PDF, you mean a PDF of just that layer?
Yeah, exactly.
Okay, cool. Thank you.
Yeah.
Thank you.
Yeah, great question. Well, if you have a fab drawing and an assembly drawing, that's already like huge. I know I have low expectations, right?
So back here.
Sure.
Recently worked on a board where we had these little QFN parts with an exposed pad in the middle that were having some solder connectivity issues. You mentioned mask, but it turns out the issue for manufacturing on this part was the stencil.
The stencil, yeah.
It turns out they had the area in the stencil for the exposed pad was a little too big. They put a little too much solder in the middle, and so it raised the middle, and all the edges were little columns, and a couple of them disconnected. And so the fix was smaller, like quadrants in the solder. Do you have any suggestions about solder masks and anything that KiCad might do to help with solder mask, or not solder mask, stencils?
Solder paste. Yeah, that's called the solder paste layer. Again, I'm not a PCB designer, but when you're designing a component, I know you design the solder mask part of the component, right? When you're doing a component library, do you do solder paste also, or can you? So, I think Sierra should contribute to that. I don't know how, but, we are continuously refining solder paste design, because what the notes that come out of the semiconductor company is not always the ideal notes for fabrication. They may say the mask should look like this, they may say the paste should look like that, but it's not really sometimes actually the best. And so we have all this real world knowledge on what solder paste should look like, and we basically make mistakes too. So in our assembly facility, we have a solder paste deposition machine and then a solder paste inspection machine, and we just replaced the solder paste inspection machines with newer machines, better machines. And it's really about collecting the data and making sure that the solder paste is the right volume. So yeah, that was a really good feedback you gave. Yeah, it's really nice.
Do you still need fiducials for parts placements?
Who's speaking? I'm sorry. Okay.
It's on, yeah. Do you
yeah,
still
no,
need?
it's on.
Yeah. Do you still need fiducials on the board for part placement?
Yes, definitely. Fiducials are really important. You know, the equipment's always getting better. Equipment's already always getting more accurate. But if your board is getting denser and you're putting down a tight pitch component or a sensitive component, you know, to placement, having a localized fiducial is really key to part placement. Because I remember going back to PCBs, I mentioned PCB materials move around. The boards shrink or stretch during processing and after lamination. And prior to assembly, you know, pick and place and solder paste, our assembly shop is using our scaled data from our fab shop and, you know, to get as accurately as possible, to get the stencils designed properly and put the paste properly, and then pick and place also to be more accurate. And I think that's a really key thing. And, you know, this literally happened. I had a customer in the conference room, and I was telling him we use scaled data, and this was 10 years ago. And then you should, you know, think about that because your design is very dense, and you're using a separate board shop and a separate assembly shop. And I guarantee the board shop's not sending scaled data to the assembly shop. And the guy got really mad at me. I've never heard of this. What are you talking about? Scaled data. So it's a real thing. Our assembly division always asks for fiducials, and now we're even asking customers to add fiducials on their design, of which a lot of customers say no, but at least they, you know, maybe the next iteration of the design, they would add a fiducial. If you can't put it on the board, put it on the rails when you design your array. How many people design their own arrays? Yeah, don't. Let the fabricator / assembler design the arrays. It's the right approach. It sounds easy, but it's really hard. I don't know why.
Do you care ODB++ versus the IPC? Which best for fabs?
ODB has a licensing thing hanging over people's head. It's not like just an open thing, and IPC is driven by a consortium. IPC 2581 is driven by an IPC consortium, and I think they're really pushing it forward. So long answer is I prefer IPC. You know, Cadence and other tools are able to import IPC 2581 stackups, which I think is a really nice thing. You know, I think KiCad has it on the list, or they should have it on the list to import 2581 stackups. So it's allowing for bidirectional conversation. A fabricator and assembler really tweak the designs a lot before they manufacture. And for us, we are in the practice of always asking for permission because, you know, the boards are going into space or some military thing, or even if it's not, you know, we always just ask for permission. But a lot of fabricators don't ask. They'll just modify your design and build it. So you really don't know what they're building. I mean, in all honesty, and especially if they're assembling too, you don't know anything. But 2581 is promoting bidirectional conversation. So you get the data back. You can import it into your CAD tool if their CAD tool supports it. You can look at the comments or changes or have like a nice discussion. There's lots of possibilities, basically. People aren't doing it as much, but yet. But yeah, long, short answer is go with 2581.
Yes, I like to use tin bismuth with a smidgen of silver, 138C solder for prototype assemblies for ease of rework. What is your outlook on that? Is it becoming more popular, or it's dying? Or some houses will do it, some won't.
I think if you specify the solder paste that you want, the house should do it.
Okay, thanks.
Yeah, but what's the most common, it's really up to your fabricator because, you know, it's all about process tuning and process refinement. And, you know, if a fabricator and assembler is used to one kind of solder paste, it's because they've perfected that solder paste. So I would, you know, it depends how how much you hold that near and dear to your heart. But I would always go with what the assembler wants to use or prefers. But if you have it as a requirement, then just make it. And that is very nice.
Okay, so I hate to cut this short,
problem.
but Amit is available outside at his table for additional questions. I know that there were a few that we didn't quite get answered yet, but I want to give us an opportunity to get up, stretch legs. We have some coffee and refreshments outside. We'll reconvene in 20 minutes, so that is 3:50. So we'll reconvene at 3:50. Thank you, Amit.
Fabulous job. You must be exhausted.
No.
Yeah, still going.
Energizing.
Still going strong.
It's bunnies. who's our next talk? You're our next talk, aren't you? Okay. Oh, can't believe I just found out that I messed up the QR code. So, all right, let's get you set up here. Do you need network or just the presentation?
No,
okay.
just the video.
So. It's a Dell.
Oh, Dell.
Which, let me go ahead and just get that.
Germany's really bad. They know how to do the code jobs. They build those facilities for them and
Oh, okay. There we are. Close. Okay. Go here, display. Is that not? Okay, good. All right, so I turn off the networking, disconnect, just in case. And then documents, presentations, KiCon 2025. There we go. See, document viewer, it should be, oh, hey, look at that. There we go. So this should have a presentation here. Present as slideshow. Oh, wrong side. Okay, so.
It's all right, just leave it on that one.
So I'll just go right over here. Or you know what? You know what we can do? We'll just mirror these.
Mirror the screen.
There we go. Display. Mirror. So then, okay. Just don't do anything funky that you don't want people to see. Slideshow. All right.
All right.
There we go. All right. So let's get you. Move this out of your way.
Is this a walkie one or? Actually, I don't need a walkie one. I'll just stay here.
So. No.
Do I still have 40 minutes, or are we?
Yeah.
trying
Oh
to
yeah.
catch up?
No. You're fine. You're
Okay.
fine. Take your time. If we run over, we run over. It's fine. We're rolling into a reception after this, so
Okay.
so we can always push that.
Cool. Okay. Are we live? No? Yes. Hello. 1, 2. Do we have audio? Okay, good. All right. It's hard to tell from up here. So, hi everyone. First of all, I'd like to say it's been a fascinating day so far. I'd like to see the range of people. You know, we've heard from very esteemed simulation and board houses and all sorts of different people, including mechanical. My angle is again different. I'm not an electrical engineer. My background is in software. And this is kind of a little bit of a story of how I came to be involved with boards and KiCad. It's mostly mechatronics, what we've been doing. We're in the robotics space. So again, that's probably a different angle. It's not sort of high-speed stuff, although we've gotten into radio a little. So yeah, that's where I'm coming from. I hope it adds some value for some of you. There's been a lot of project management and stuff crossing over, mechanical, electrical, supply chain. So that's what you can expect. Okay, so first of all, why look at hardware? Well, frankly, software is getting boring, okay? After that whole crypto thing, it was just like, I'm sorry, I can't take this seriously anymore. I need to do something different. And I had a little pile from the crypto thing, and I thought, I'm in China. I've got to make a decision. I also had a daughter, and I thought, well, it's time to get serious. What am I going to do here? I decided that food was an area that robotics could be applied to that had the potential for serious returns. Anyway, how hard could it be? So I thought, you put some ingredients in a box, you shift them around a bit, you do some cooking, maybe pump it out in some kind of plate bowl thing, and, people will be happy. How hard could it really be? I think my software brain was in overdrive. With software, you just make mistakes and you can fix them. It costs you nothing. It's really not like that in hardware, but the tools for control, in terms of how you think about things and how you tackle complex projects, are in fact very, very similar. And so there's a lot of value you can bring over. So I guess you could say that experienced software people are comfortable exploring a solution space and iterating towards a complex emergent goal with multiple conflicting design constraints. Aren't we awesome? But we can't estimate. We just cannot estimate. Because let me tell you, I have been on the verge of tears so many times with this project. It's like I would never have started if I knew how hard it was. So 2016, there I was in China. I was like, this looks easy. This Arduino, there was a PIC thing I tried 20 years ago. This looks easier. Let's give it a go with that. Well, Arduino is great. I love it. I think it's fantastic to sort of bring down the level of complexity for first-time users. The whole USB upload thing, great. Power over upload cable, great. That's already solved so much problem for people. But when you get into it, you realize, oh, well, it's library this and library that, and there's clashes, and really there's a lot of simplification that doesn't necessarily come for free. At a certain point, all those little wires, they stop working reliably. So then we went on to PCBs, and we thought, okay, we better get somebody who knows what they're doing, somebody who can stick their hand up and say, I can design a PCB. They must be the right person for the job. But we didn't know how to spec. So we'd be sending out these specs saying, I kind of want this thing done, maybe on like a square. Can you make it square? We didn't know anything about how to spec these things physically, supply chain. It was just garbage in, garbage out. And so we wound up with a bunch of completely disparate boards from disparate designers, which through no fault of their own were just of limited use for us going forward. So over the time this has been going, in fact, we shifted cities twice. This was our third city. So you can imagine you've got a whole team of people, a family and an office, and you're actually moving that multiple times. It was really, really stressful. And at the end, it was starting to get a little bit difficult. We really needed some good news. And it came. Money. Somebody said, that is awesome. Let me give you some money. God, it was fantastic. It was like a godsend. So we opened the Noodleplex. I thought, if Google can do theirs, we'll do ours. And we moved across from Shenzhen, you can see on the right there, over next to Macau, and we got ourselves an industrial space. And we filled it. We filled it with really awesome gear, slicing and dicing, metal, polymer, dedicated electronics lab. It was great. So once those rat's nests had taken off, we kind of started iterating better. We got some better consultants. We kind of set some better rules. We improved our specs. But it was still quite slow. The hardware had been going well, but then came COVID. Actually, I've skipped a slide here. Well, it was going pretty well, and then we had to COVID, right? Now, when we got there, everything stopped. Literally, you couldn't get a visa to go to your own company. It was an absolute shocker. So by the time we got back there, we had other challenges. Chipageddon, as you're probably all aware, being in the industry. And I just thought to myself, without a team, this is actually the perfect time to reassess whether or not the electronics work should be done externally. And what I learnt was, this is a perfect motivator. What went wrong here? Why can these boards not be produced? And so I found a really experienced consultant who's been a great mentor to me. And I'm still the first to admit I know very little, but I've learnt so much, and it's been fantastic. So for the next 2 years, we basically just went through everything, redesigned everything, block by block. All the designs were improved significantly. Costs came down. We could iterate on boards rapidly at speeds that you just can't get in most parts of the world. And the costs are very low. Now, at the same time, KiCad was moving forward quite quickly, and there were some breaking changes. So that was a little bit of friction for us. Now, essentially, at this point in the talk, I'm just going to switch over. We're going to start looking at some of the things we picked up along the way, managing mechanical, production, and the electronics together. And we'll bring it back to some more general points at the end. So the better milestones that we came to over that period, I'll just leave them out there. You can read them yourselves. Very exciting. You know, when you make something and it just works and you think, it's not incredible. It's actually working for a change. And that happened more and more. And we got to the point where, you know, we were building quite complex, relatively high current electrical systems. You know, we're doing cutting our own bus bars on the laser. We're doing, you know, all these different things in very different fields. So that gives you a sort of sense of the range of mechatronic solutions we're looking through. So what I'd say is the first thing is, if you ever attempt such a ridiculous project, which I don't recommend, zoom out, okay? The zoom out really helps, because every time you do something without doing your research, I know everybody's going, yeah, we know this, it hurts. And so that just got battered into me every month, every day for years. Next one. Don't invest in the individual instance of something, but go always for the process. And I know there was a discussion outside about drawings and the use of drawings for mechanical and the use of drawings in electronic design supply chains. The sorts of things that are very low-hanging fruit, CI/CD and good test gear. I mean, it doesn't cost you anything anymore. I've never been in, you know, a corporate electronics lab, but you can get this LXI connectivity for not a lot of money. Automate a whole lot of things. You can use it for, you know, if you want to do a better nail style test bed, but just for regular test work, it's fantastic. Absolutely great. So coming from software, this is just fantastic. Next thing, we really lost a lot of time initially allowing the different consultants to provide disparate designs. Those designs didn't share libraries and parts and design philosophies and things that we'd learned elsewhere. So bringing that sort of single source of truth mentality into your management is important. And the generative methods, which I'll talk about more shortly, do save a lot of time. Now I don't want to say this is a negative about KiCad, but over that period there was probably more friction. I think it's all pretty much sold now. Okay, everything's been smooth for me recently, but at that time we had core changes. I think one of the core file formats shifted to S expressions and it had been something else in the past. We had a reasonable number of things that were causing problems just keeping that many projects, that many boards up to date. So what we did was we just deferred. We just stuck with 5.1 for ages. It wasn't a bad decision. Now, the mentor told me functional blocks, and everybody's probably rolling their eyes. Yes, I know this. The interesting thing is, it's kind of still not a solved problem, and I think that Wayne's talk tomorrow about the schematic design blocks primer, I think that's actually going to tackle the new way to do it. Now, what I wanted to share here was the old way to do it, which I basically made up being a software guy, but not really wanting to delve into the C++ and whatnot, was we just went through, scripted the thing to remove all the designators, and then we'd back it up in a separate repo, which became like our library, I guess. When you wanted to deploy it, you just copy it in, link that in with a schematic sheet, bang the name in, and it would link just fine. So there are other ways. There's some plugins and things, but I just wanted to share that was the method we've used since the 5 series, and it still works, as far as I'm aware. Probably you want to learn from Wayne, but if you've got that problem, there is a solution. It was very quick to implement and worked very well. Component management. Now, it's like there are as many part libraries as there are people. Like not companies, but people, it seems like. Everybody has their own way of doing it. What I learnt was I tried to put off having those skills in-house to draw the parts. I spoke to professionals that were maybe outside using professional software, and they said, oh, I just send it out to someone. I don't like doing it myself. what I was kind of getting the sense is that a lot of people don't like doing it. It's easy to make a mistake. But at a certain point, you have to do it. So once you've learned to do it, it's good to contribute. I think over that period in particular, KiCad moved to GitLab. And I think a lot of people were pulling their files from distribution-based sources, so they weren't on Git, really. And so there was a bit of friction about getting feedback. I think that's improving now, but that was the situation at the time. Now, one tool I really want to mention, because for me, it has been a fantastic point of, let's say, save time, is this Nicolas Toussaint. He did this JLC to KiCad lib. It doesn't cover all the parts. It's basically the LCSC parts are covered, but that's a lot of parts, and they're really good. Like, you just click the thing, you get everything, including 3D. So that's the solution I've been using recently since I discovered it. It works quite well. This is probably something that people don't consider very often. So one of the issues we had over Chipageddon was that we had uni-vendor ICs that were doing things like small motor control or whatever. They basically had they were so old in the first place, they shouldn't have been allowed in the designs, but we didn't know any better. So we replaced them with discrete components. Now that sounds a bit odd, but the beautiful thing is, once you've got multiple suppliers and they're jelly bean components, you know, it costs you nothing. And in terms of board space, also very little. So, you know, we have used that to bring down costs and to bring up design longevity. I know longevity was mentioned by some of the other speakers earlier. It's a valid strategy. Works for us anyway, just throwing it out there. The problem is you do need to replicate your layout. And of course, we did mention earlier that there's a new feature coming for that. There was actually a demonstration earlier today about one of the new ways to do that. It's built into the 9 series. In the past, we would use the Replicate Layout plugin, which is still available now in the plugin and content manager. Performs the same thing. So, you know, you can rapidly replicate the layout. So the layout work you can get basically for free, and the schematic work is free. So it's very low friction to use. I would recommend it if you're concerned about cost, you're concerned about longevity of design, and it's something that's well documented in an older sort of set of literature. Go for it. It's been great for us. Firmware debugging. I mean, coming from software, it's not fun. It's not fun because you can't really test without a physical setup, and everybody knows, oh, I've got one board on my desk, I've plugged in all my test equipment, you know, I'm doing this test, and then, oh, I've got another board, and then, you know, I need to switch back. And there's just an overhead in context switching that exists with hardware testing that doesn't exist in software testing. And you don't want to be doing it if you can avoid it. And the best way to avoid it is to use tested code, and the best way to do that is to generate the code from the model. What is the model? The model is the actual design. So you can actually just pull out the net list and see what connects to what. And you can say, well, in all our designs that are using, you know, this particular approach, we use this particular software approach, and therefore you can generate the bulk of your firmware. And you see that on, you know, the ST's tools and all those sorts of, you know, commercial products. They'll also do the generation for you. All I'm saying is you can implement that very, very rapidly under KiCad, and we have done so with good results. This is very basic stuff, but like, I mean, some people are saying it was their first board, so just make sure you write it down. And when you write it down, write everything down. Write down when things went out, when they came in, what you observed. It never hurts to have extra information. And in fact, I was surprised at how quick things would be turned around. I never would have noticed if I hadn't had the habit of writing them down. It's just good practice. So with that LXI type connectivity as well, you just pull in like dumps from your test equipment. It's instantaneous. And with Markdown now being standard across all open source projects, I mean, it should be the standard in the hardware world, I feel, you know, of course, if you're doing high speed stuff and it's very complex, we've probably got a better way of doing it. But for like basic mechatronic integration type things we're doing, I found it to be fantastic. So yeah, do duplicate some of the information to the schematic. That's, again, another area where everybody's got preferences. Now, before ordering, we talked about, I think there was, from the board house, we had some insights there. These are the sorts of things we've done as a beginner. I would be mucking really basic stuff up. Sometimes, you know, you'd be tired and it'd be 3 a.m. or whatever, and you'd put in, you know, your footprint, and it would pop up with the wrong component type, and you'd click on that, and then your board house has a fit. So it's things like polarization on caps, picking the wrong footprints, making sure that everything's been run internally. So, and then a very interesting thing is actually just checking availability. So if your supplier has that capacity, just write a script that tells you, because often the web clicky interface for uploading, it takes a reasonable amount of time, and you might get to like step 27 and it's like, oh, this part doesn't exist. And then you have to go back and redesign the board sometimes. So much better if you script it and it can just check, oh, there's enough parts, or maybe there's only enough parts for 50 boards or 100 boards, you know, maybe you want to start rethinking that. So that's something we integrated quite quickly, and it was just from that repeated pain of having to do things over and over. So this is sort of like, I guess, an example of like software mentality applied to hardware development process, where it sort of can save you time. It's just about being practical. Tip 11, I mean, this is again, very basic stuff. Probably people cover this in school, but I didn't get the benefit of that. So here's the benefit for those who are doing their first. I mean, I actually had a little trick which I really liked, which was I'd often have problems with the C libraries, you know, and they would pop out in funny ways. We kind of get to the point where we're maybe pushing some of the MCUs or other components to sort of closer to memory limits, and issues would occur. One strategy that worked for us was actually running a fair amount of entropy through the system automatically after upload, and that would actually flush out bad changes immediately, which saves a huge amount of time when you get those difficult bugs that only crop up now and then. That was a good step for us. Now, this basics of testing. Start with power, go block by block, subsystem. That was normal. I'm sure everybody learns that in school. For us, you know, it had to be done manually. At the end, we just put our interpretation, hypotheses, and investigation in line. So that worked out very well for us. You get a full, you know, brain dump. Future you can see what you were thinking at the time. Now, we had a little bit of a discussion about this earlier. It was a very good talk earlier on. We basically came to the conclusion that the 3D was great for the board, but when you started to go further down for the things like the clearance, as was readily admitted, I think in an earlier talk, it's not quite there. So we just used a sort of 2.5D approach by marking out on a DXF, which had come out of the MCAD, you know, this area has lower clearance, etc. Works fine for us. Now, interconnects are like a problem that it seems like everybody that gets, you know, it's a big problem for the consumer, big problem for, you know, high density designs. A lot of it's to do with how frequently you're going to be plugging and unplugging, and is that automatic, and how much force is applied, and all those sorts of things. Look, for the mechatronic stuff we were doing, absolutely not worth it, right? There's thousands of potential options, and just go for the basics, honestly. The amount of space you save with some of these things, it's minuscule. And you can just be waiting there for this thing to arrive in the mail so you can, you know, solder up your... We just found it all to be fairly wasteful in the end, stuck to basics. So that's cat cables, you know, ribbons, and the JST type connectors, and bus bars. Bus bars are awesome. So, yeah, one of the issues is there's just too much to learn. So one of the approaches that I use, and I highly recommend for anyone else attempting a kind of cross-disciplinary R&D project, is use the availability of things to filter whether you spend time on them. Things might be great in theory, but if in a year's time or on another continent or whatever, they're just not available, you need to really think about whether or not you want to invest that time. We also had, for our sort of situation where it's not high speed and all those sorts of things, and we were really looking at iterating over many designs very quickly, we found that MCUs on module were excellent, a very good value. It just meant less components to lay out, less complexity per board, cheaper boards. You know, you're going to stay within that cheaper or sort of relatively inexpensive category with your board house, because you're not sort of pulling extra reels for everything just because you need one or two of some particular component. So it really helped to bring down costs and increase iteration speed. I think if you take this approach for many things, it will be quicker, and you can always do a final board where everything's all together. Now, one of the challenges we had, and it's probably a kind of partly cultural thing, partly because I was personally fiscally extended deeply into this project, but it was just like, you got to be really careful about things walking out the door in the situation I was in. So we would actually split, and I think that the military industrial complex does this as standard. That's where I picked it up from. When I was younger, I did a little bit of work in Australia. But basically, you know, we just split information up and try to introduce additional physical controls. I think culturally, you want to avoid having to do that, but sometimes it's necessary. And finally, this is one that I really feel is important. Like, if you go out there and you ask vendors for a solution, there's all these things, and they're just not good value. Like, they do the job. You know, the salesman will take care of getting you parts, and somebody will know how to put them together, and they've probably got lots of extra checkboxes from various authorities and all that sort of thing. And you do need that sometimes. But a lot of the time, they're basically a trap. They are a trap because if you call up that vendor, and I'm not going to name vendors, but very big vendors, you call them up and you say, oh, I'd love to have this particular part, please. I need it for my, you know, control system or my such and such. Oh, sure, sir. Well, that'll be a 9-month wait on that part, right? There was a lot of that over the last few years, and I think what it really taught me was, if you can avoid it, just don't order anything that exceeds the most basic complexity threshold and the highest volume threshold from these industrial automation vendors, because it's gonna need a redesign when they stop supplying. So that was an issue. So I've got this example where we're actually building a sort of power distribution system with metering and some other features, and literally went through, I think, 4 or 5 different commercial vendors. They had, you know, it was Ethernet control and all these other things were in there. We get quotes up to like $20,000. We managed to replicate the same functionality for $150. So that's the level of savings you could make reinventing the wheel. So I just wanted to sort of underscore what is considered to be good practice. Sometimes you need to question it, and it's not for everyone, it's not all the time. You know, you're still going to have to checkbox that with your government authorities, but, you know, it can be worth it for that much per assembly. So, like, after all these years, where'd we get to? Well, we had about 70 people contribute to the project so far. It's been really difficult on many levels, but we actually built this restaurant, and it's pretty awesome. It's, you know, the size of a fridge, but it functions as a fridge and the cooking part of a restaurant, and there's 4 parallel sections. It's very small. It's inexpensive to assemble, largely because of those kinds of savings and other optimizations. And we have drone integration, not entirely complete, but it's objectively ahead of everybody testing in Texas right now. And we didn't even need any humanoids. Sorry, Mr. Musk. So, having shared some of our learnings with you, the valuable audience, I just wanted to note that I am kind of out here still on a limb, also financially though, with support of existing investors. If you happen to either be or know any venture capital sources that are keen on VC in the hardware space, I would love to have the introduction. If you want a job around this area that relates to KiCad and mechanical engineering, mechatronic systems as a whole, including factory-type automation, please come and speak to me, because I believe that we'll probably meet our funding goals in the near future, and we've identified a fantastic site not far from here. With that, any questions?
Hey, thank you for this. My first question is make sure I understand your business revolves around what is it at this point? You know, a single large product, and so one chain of PCBs to support that product. Am I just understanding that right? First of all.
Yeah. So I did want to focus the question portion maybe on KiCad specific concerns. Maybe you could come and talk to me afterwards.
Sorry, leading into my what does the I was going to ask on what does the actual chain of boards look like, and what does the scale of complexity of those boards, and how does that work with
so
like
from a rough standpoint, we've got probably, I would say, around 200 boards per machine. They would encompass aspects like the control of HVAC, induction, hydraulics, pneumatics, radio, various protocols, display. Yeah, like there's a significant, and a lot of mechanical like motion systems with control. There's many sensors, ranging from sort of physical presence, proximity, distance, air quality, water pressure, you name it.
Yeah, so a wide range of devices. Then, have you found that KiCad's development tools have been meeting your needs for all the many
absolutely,
types of boards?
Absolutely everything has been done in KiCad. Okay,
cool.
So this is a real message I want to get across with this presentation. Everything has been done in KiCad. First, we mandated it because we wanted to get stuff back from consultants that we could actually trust we could use in another year or two, and we didn't have any of those licenses. And then secondly, because it's just so good, like it does what you need. So by the time you've learned, the quirks or whatever, and you've gotten going, there's really no point to shift. So I absolutely could say, from the perspective of the project as a whole, using KiCad was an excellent decision.
Super cool. Thanks.
Yeah.
You said that using MCU modules was actually cheaper and easier than using chips. I was wondering if you could talk a little bit more about that and maybe give an example.
Sure.
Because that's been the opposite of my general experience.
Yeah, look, it is going to vary by the MCU, but the actual cost of putting one of those chips on a board is, you've got to do the chip, the peripheral components, the power. You got to lay it out. You got to debug it. You got to have a programming interface. You got to consider how you're going to power it during programming. Like, by the time you've done all that, it can actually be better to kind of just use something that you can get in arbitrary quantities for like almost that money, or actually less in our particular case. So it's very close. I think that people perhaps jump to do integrated designs where, particularly in a mechanical, like a mechatronic heavy, iteration heavy environment such as we were in, it wouldn't have been the most optimal approach.
Yeah, so complex electromechanical system with maybe 200 boards. I'm really curious how KiCad helped you with the multi-board design.
Sure.
And also, did you use any of KiCad for harness, like cabling and harness design?
Very good question. So, okay, I'm going to tackle the harness first. So on the harness side, I think there's essentially like maybe 3 traditional schools of how to like build an enclosed system. You've got like the harness school, which basically dates back to like NASA and cars. They sort of do that traditionally, although they're moving away from it, really for the same reasons that it wasn't right for us, which is, if you design a harness, you get exactly what you want. I think part of the win was it's like a weight reduction, which if you're doing space probably matters. For our area, weight is not a concern. What is a concern is, can you get the right length of that particular thing like very, very quickly? Is it familiar? Are the connectors cheap? Like, are they going to withstand the physical environment? In our case, we didn't have like a vibration problem with like the rocket taking off. We didn't have a vibration problem with, the car running over rough terrain. So those sorts of concerns aren't really significant for us. And I think that's why, in our case, we actually opted for separate AC, DC, and comms lines. And there is some duplication. In some parts, for physical reasons, we combine some of that stuff, or we have like custom solutions. But generally, yeah, Cat6 and raw copper. Yeah. Did that answer the question?
Kind of.
Yeah, on the first.
Did you do did you use KiCad to do schematics for your wiring and all of that sort of thing, or?
No, see, the topology at that level, we used a modular approach. I think everybody that designs something like this would typically use a modular approach. Once you're at that point, you know, it's essentially a mathematical graph with very few nodes. It's basically simple enough that drawing out a schematic is of dubious utility, given that there's less than 12 endpoints or 24 endpoints in you know, one part of the system. Yeah.
Yep.
Yeah, but when it comes to showing it to a government approval agency, of course there'll be a schematic. Yeah. Yeah. Any other questions?
Okay, thank you very much.
Thank you.
So next up is Reed. Is Reed here? I don't actually. Oh, there he is, right in front of my face. You have your own laptop? Great. Let me just disconnect here. This other way. Okay. So that one there should get you. So next up, we'll have Reed Harston. Reed is a self-proclaimed computer nerd. He is born with computers overflowing in the garage, the shed, the basement, and from under the bed, and now spends his time on ways to make what he had more accessible to the rest of the world, so we can figure out how computers work without having to have hundreds of them piled around. So today he is going to talk about his Jigsaw project and how that is going to create interchangeable prototypes and dev boards with KiCad. Please give a warm welcome to Reed Harston.
Thank you. Okay, so I didn't really consider that he'd be reading that out. I thought it was just something to have on the website. I might have thought a little more about how I worded that. Sorry, it didn't flow very well. But, so yeah, like I said, I actually call this project Quebra-Cabeça. My wife's from Brazil, I speak Portuguese, but I figured I would use the English term for the talk. But how did I get here? Like, where did I begin? Actually, a lot of similarities to some of the other talks that were given today, including Eli's. Yeah, those actually aren't pictures of ones we personally owned, because that's what I found on my phone. But those models are things I had. We actually did have one or two original 128Ks and one or two 512s. We had two of one of the other, the original Macintosh models, and a bunch of the classics and SCs and things like that. Beyond many, many others. My dad would bring computers home from universities and government agencies and things that they would be getting rid of the old computers, be bringing in new ones, especially back in the 90s where every year a new computer was actually improved from the last year, not like these days where you can have a 15-year-old laptop and it works just fine. The computers, though, didn't always completely work, right? You'd have this one and that one, and you'd have to change parts. And so that's how my brother and I learned how computers work growing up, is we'd take them apart, we'd swap them out, and my dad brought home used landfill bound computers on purpose so he wouldn't take apart his. Not that he would mind that particularly, but as a lawyer working from home, like if his computer didn't work, we didn't make money, right? So it was important to him to give us the opportunity to learn. And not just us, but everybody. My dad, sorry, I thought I was ready to talk about this. My dad's mission was to make computers available to all students, and he worked with. He worked with Boy Scouts groups and with schools And we try to get computers to these places for students to be able to use them, to take them apart and learn from them. And because he wanted to let everybody have access, he had, okay, that didn't work. I'll do it from here. This is on the wrong screen. Which way am I have to go? Okay, so when I say lots of old computers, wait a second. Just wait a few more seconds. They're gonna move over in just a minute here. Maybe I need to skip a little bit, but okay. So this is another part. Notice some iMacs back there. Some of you might recognize the iMacs. So it's not just computers in the shed, but it's mostly. And so yeah, growing up we had to deal with this mess, but there was a reason for it. Right, my dad wanted all the, and this was the good stuff. Okay, so my dad made this part up in the top of this building. This is a farm building. We called it the shed. I don't know what the official term would actually be, but it's meant for tractors and things like that. And my dad built this little upper level for the good stuff. Notice a pile of 2GSs back there, a Color Classic in the top. Those gray and white ones in the corner there. Which one's the little laser pointer? I don't know which button does the laser. Green one? There we go. Those are Duo docks. So there was a time where Apple made these laptops that you'd slide them into the dock. So you'd have all your stuff plugged into that. And you just slide the laptop in and everything would pop up and you slide the laptop out. Didn't last very long. So this was the good stuff they had set aside. And even in the good stuff, we had probably 100 computers. So this obviously is not obtainable for most people. My brother is currently, G4 iMac. That thing was awesome. This is not something that most people can do, right? And even should do. So my dad passed away about 8 years ago now. And my brother is still dealing with trying to pack this stuff up. This video is actually somebody that he found who came up from Portland and hauled away a trailer full of it. And what you saw there was after they had loaded half of the stuff into the trailer, after my brother's already spent years working on this. So that's, I think, just kind of the best way to really get a feel for where I came from and why I'm here. Okay, let's go ahead and close that up. So I came from this very small community where we had all these computers, and that was my backyard. I had 48K dial-up growing up, and that was good stuff because not long before I was born, apparently, we still had party lines. And so my dad said we had good dial-up because the lines were brand new because they had just moved them from party lines to real individual per house phone lines. And so that's why we had good dial-up modems. I did not see faster speeds until I was in college. So growing up, I did not have access to the internet. Not only was it new, but it wasn't really available for me. When YouTube finally came around, I would have let a 5-minute video load for half an hour before I could even watch it, right? Then I spent a few years in Brazil. I didn't mention this here, but I served a mission in Brazil. I was there for a couple years. My wife's from there. I'm very well aware that not everyone has access to all the tools that we all have. Not everyone has access to all the resources that we all have. Growing up, I spent all the time I could learning everything I possibly could about computers, taking them apart, putting them together. I didn't have a library with good books to go down to and get the books, right? The closest library was half an hour away, and it was a town of 2,000 people. We didn't have computing stuff. I was just trying to figure it out all on my own. And even then, I won awards in high school because I was just curious and trying to figure it out. So I'm working on something. Yes, I'm a computer science major, currently a firmware engineer. I've met a few people. I do currently work at Micron as a firmware engineer. This is what I'm working on and why I'm here now. I'm currently working on something that I think will help give people access to the sort of thing that I had and meet some needs I see in the education space for computer science. As a computer science major who meant to be an electronical engineering major, that was its whole other story. I had to do classes online because I was living in Brazil, and I ended up in computer science and realizing along the way that, oh, I want to know how computers work, and I got enough out of the computer science classes that I was able to figure out how transistors turn into gates and gates turn into digital logic that do all the stuff in the computer. Like CPUs was my fascination for many years. Like how does sand turn into something that can process that? Like that 3D image, if I go into KiCad, I will later in the demo, if I go into KiCad, I could just drag that around in real time and it's generating this thing, and sand did that. That was just blew my mind. Like, well, at first I didn't even know it came from silicon. I didn't know what it did. You know, what made a CPU work and how it worked. So I was curious enough to dig. Some people are curious enough to dig and don't know where to look, like I did. It took me years to find these things, and I want to help find, provide resources that will make it easier for them to dig. And some aren't quite as curious or just need a little more guidance. And so the idea here, I'm trying to keep this short so we can get on to the KiCad part. But the idea here is to have a computer that students in a computer science major can fully understand. Many times I wished I grew up old enough in the 80s, as a 90s child myself, grew up in the 80s where you'd have your Apple II, you'd have your Commodore 64 or your Atari, and you'd open, you'd do your basic, and you just turn it on and it started working immediately. I had some of that experience because my dad had old computers, but for some reason I never actually got into programming them until I was in college. I was always more interested in the hardware. Nowadays, what kids have is completely inaccessible. There's no way to program your phone from your phone. Like even Android, you can't really, it's just not a thing. Right? You can't program your phone from your phone. You can't know how it works. You can't even open it most of the time. Like someone here was saying how he's on screen replacement 5, I think, in his family. Like he buys phones specifically that have screen replacements. That is not the common thing that people do. And so working on this platform that will make it easier for students to understand, because the computer is simple. It's simple like 8-bit or 16-bit from a long time ago, but it's made for education so that it's an architecture that people can actually understand. The documentation's provided. I was going to take a class using the Raspberry Pi. That year the 3 came out. I bought the 3 because it was 64-bit. Wow. The class wouldn't let me use it because they were using the old Pi 2. The documentation wasn't available for 3 because no one had reverse engineered it yet. There was not good enough documentation from Raspberry Pi, the corporation, with lots of employees and money, for a class to actually use that documentation in the class. They had to wait for the community to come up with the documentation. Raspberry Pi is small and cheap. It is not simple. It is a full-blown computer with all of the features. So something simple that I can provide documentation, students and teachers can use. I'm looking for help in talking about ideas, what's actually valuable to have for the first version. Plan would be to have like your sophomore level one, and then a junior level one, a senior level one. We advance through the years of technology and complexity with multiple versions. That's the idea. But while I'm developing this, while I'm trying to come up with it, I came up with some problems. I too am from a software background, as I mentioned in the last slide. I've always had interest in hardware, but I never actually went to school for it. I did take a few classes when I got the chance, and I've picked up a lot along the way as a firmware engineer, but it's not my main, my major, it's not my main experience. So how do I start? Start with small things. I wanted to start with small things and pieces of this thing. Like one of the ideas also would be, this is something that you can expand by plugging in little modules. Well, what better than to use an industry standard? Some of you might be aware of Digilant. I just remind myself to speak slower because I'm not entirely sure I can fill 40 minutes, so I was going to speak nice and slow. And here I am just going through the races. The connectors on the edges here are just your standard 12-pin, two-row, 6-pin connectors. Digilant calls it PMOD. They have these PMOD connectors. They make these little boards that are used in education that you can plug in VGA and sensors and all sorts of things, and you've got an FPGA in the middle, and you can program it to work with those. And so very, very flexible, well-supported. This PMOD specification's been around like 15 years or something. And just so happens that Digilant lives just up the street from me. So I actually know people who work there. The idea, I think, is great. You have things that you can plug in, play. But in PMOD, all these things are different sizes. You've got one that's this big and that big and this big, and one's too wide and one's one wide, and some things are too wide even though it could have been one wide, because you could have them as 1 row 6, or you can have them as 2 row 12. And like the VGA one is 2 1x6s instead of 1 2x6. And I just, right there, it kind of evolved naturally over time, and it doesn't all make perfect sense. And for something that I want people to be able to kind of piece together modules onto, and while I'm developing, kind of break it into pieces that I can develop smaller pieces, I thought of something that I'm calling quebra-cabeça, or puzzle pieces, where I'll come up with little pieces that are all the same size, and I can swap them out. If I have this piece, I'm like, well, I want this other one, I can swap it out. I don't have to redevelop the whole computer, I don't have to redevelop the whole kit, just that one little board, I can swap out that board, and that'll be easier and cheaper. And and you'll notice also, like, there's a USB-C port up there. Yeah, someone made a comment during lunch that I completely agree with. USB-C with USB 2 is the way to go. USB 3, super complicated. USB-C, the port, excellent. I want to be able to, plug it into a student's laptop, program it from the laptop, power it from the laptop, have nice plug-and-play compatibility there. And of course, I'm also here to, learn from all of you, get feedback, meet people. I've already met a few professors, handed out my card, because I'd like to know what are the needs you see with your students. I mentioned that I want to help students understand, I kind of glossed over that a little too quickly. Computer science fundamentals. Why did I mention fundamentals? It took me years to dig to the bottom of a lot of things, because we're at a state now in the industry where computer science is so complicated. We built on the shoulders of giants on top of other giants on top of other giants. It's very difficult to understand the whole architecture of anything. This computer I will not lift up. It's plugged in. If I may, this one, it's also plugged in. Okay, my phone. So these things are very complicated. Your phone, like, how can you turn it off? Yeah, when you press the button, it turns the little light on saying, look, you need to charge me. It's not actually off. There's always a little system in there. There's so many little systems in there that are actually always running, always doing something. DFU mode, like you press a certain combination of buttons and it will do something even though it's off. These things are so complicated. They have so many computers inside of the computers that how is a student supposed to wrap their head around all that? So I mentioned the idea of taking steps through time and complexity. If you give a student something that's simple enough, you can let them get straight to the point of that class without having to understand the whole computer first. That's my idea. That's the concept. If it's an operating system class, why do you have to spend 3 weeks going through all the weeds of ARM architecture to get to operating system? You want the 3 weeks of ARM architecture, but maybe not right away, maybe not in the beginning, maybe that comes later. So, so that's some of the ideas there. So where I'm going with this, I'm starting up a little thing I'm calling Appaloosa Computing. Appaloosa refers to a horse, but it's also the region of the Palouse. The Appaloosa and the Palouse are what inspired the name. And so I'm trying to support the education community, and I want everything to be open source. That also is for, Arduino, you can, if you want to, download specifications and build your own boards. Nothing's stopping you. I want to be able to do the same sort of thing. And so KiCad was an obvious choice for designing things because open source community, open source hardware, I want to be able to design things that will interoperate. I can make this thing, if you want to buy mine, great, buy someone else's that part of the module, make your own to expand things. I want it to be an ecosystem that, obviously it won't be the first ecosystem in this realm, but I haven't seen anything quite like the way I want to do it. And so, and also, want to work on courses and help people learn the computer science and engineering topics to help upcoming engineers. Someone made a comment earlier about people retiring because they've been in it for so long, and that is another reason of concern that I have. We have people with lots of years of experience, very wise. And what happens when they all retire? They're retiring out of technology that is so much more complex than what they entered into. New engineers today are entering into a field that's more complex than ever before, and they're expected to just get up to speed. I feel like we need to be able to ramp them up to speed. And especially with companies, I don't know in the electronical industry, but in software, there's been a long-running joke about needing 5 years of experience in a language that's only existed for 2 years. It's very common these days for companies to go, we want juniors to have 5 years of experience and seniors to have 20, and everything's so complicated. You need people to have all this experience to be able to do anything. Well, how do we help them? Well, Pullman, home of WSU, just a few miles from Idaho State University. I want to be able to work with students and bring them on board and say, okay, work with me, help me develop the course, help me develop these things, and learn this experience. Learn this for yourself, starting from the basics. And so that brings us to prototyping, which is kind of the main purpose of this talk. The idea came from, as I'm trying to develop this computer, like I was saying before, I need these parts that I can kind of test. Like, okay, this single board computer is not that complex, but it has multiple parts on it, and I really want to make sure I get each part right. So let's split it out into multiple bits. And from some recent experience I had at Micron as well, I realized that it's great to have these things that you can plug into each other. But someone set up this, like literally this big, like 4 foot by 2 foot thing, chunk of aluminum with a bunch of little holes in it. And he clamped down a bunch of dev boards and he wired them up to each other. And everyone's saying that the board that he clamped everything to was more expensive than all the electronics on top of it. And that's how he could keep everything in place. And that was still better and cheaper than just buying the first rev of this board that he's working on. And I thought there has to be a better way to do it, because the idea of prototyping is you're doing some pathfinding, right? You're doing feasibility and risk assessment. You want to be quick and easy to iterate on. You don't want this big expensive board to set up everything up on. You're going to learn from the experience. And if something doesn't work, you can quickly and easily replace things. There was one part, there was a dev kit that broke, and I was trying to replace it. And I had to find all the right wires, make sure when I unplugged everything, it came back and I plugged it in the right way. Everything's going to fry and let all the magic smoke out. And so, of course, prototyping helps reduce cost. Now, as not a veteran of many years, these are the thoughts that I have about prototyping. I'm actually curious if anyone wants to throw out any other quick thoughts about why they prototype, why they develop quick, small boards. Anything else you want to add real quick?
Proof of concept for management?
Proof of concept, yes. It's a great point. That I actually was going to mention something about that on the next slide, so great point. Anyone else? It's actually ironic you mentioned that, because the board I was just talking about is exactly that. It was supposed to be a proof of concept for a project.
So I'll throw another reason, which is so that you can develop the firmware or software when you don't have the actual hardware.
I'm ashamed of myself for not putting that up there. I'm a firmware engineer that keeps complaining about the electronic engineer. It's a constant problem where, by the time we get the board, they've been done with it for 3 months. Electrical does everything in the schematics, then layout gets it for like 2 months, and then Sierra, then the board house gets it for 2 months, and then we get it like 5 months later, and by the time we found a problem, like, well, we're on 2 more projects after that. We don't know what you're talking about. So yes, that is a problem. So prototyping, what are some things that might be seen as problems? Now, some of the things I put up here, I don't actually see as problems. They're just things I've heard. Now, this one, might be a good reason why you don't need to. Like, if you've been doing this for a long time and you really know how that part works, like, you've already prototyped that part of the board before, you can just throw it on there, then you might skip prototyping. This is a counterpoint to management. Sometimes management might say, well, it's a waste of time and money to work on the prototype. Why don't you just make the real thing? Yeah, let's not do that. I've seen prototypes go into development like, oh yeah, that's good. It's like, no, that's the prototype. That does not work properly. No, it's good enough. Spent money on it. Let's reuse it, right? And then you might just be revising an old product, and so you really don't need a new prototype for that one. It's just revision of the old one. So what are some ways of doing it? Well, there's the classic breadboard. Got my little breadboard here. This I went ahead and put together to show my kids kind of how it works. And I've got my little Arduino, I have my breadboard, I have my 9-volt battery, and you can see it hooked up there. I can flip the little switches, I get my hex out on the 7-segment display. Proof of concept, I was able to write my firmware for the Arduino, because that was the main thing I wanted to make sure I got right. Like, I'm writing some code, I want to make sure my code's right, just throw things out on the breadboard. Worked great. You can do it in-house. It's quick and easy to set up. It's easy to tear down. And so there are a lot of benefits to it. There can be some problems with breadboards too. Like, it's easy to tear down on accident. I'm actually very surprised this survived my backpack. Like, all the resistors are still standing up. I don't know how that happened. You know better than me, there are issues with breadboards as well. You can't do everything with them. So the next thing you might do is grab a perf board. I gave up before I finished this thing. I got 2 of 8 wires wired up, and it's like, no, I'm not doing that. But this is a great way. This can be it resolves some of the issues with your breadboard. It's also in-house. It's relatively quick to put together. But it stays together, right? Everything's soldered down, it stays together, and you can kind of wire it up however you want. Some issues are that you have to know how to solder. I went ahead and decided to do this one so I could show my son, like, hey, this is how soldering works. Half an hour later, he's like, I'm bored. He's like, yeah, I know, but when you see it working, it's going to make it worth it. Then he left, and then about 2 hours later, I was like, okay, well, here's it partially working. Obviously, I'm not as experienced as some of the technicians I know, but it's still a good learning experience for me, and it's part of the experience. This shouldn't have been as hard as it was. It's just been a long time since I'd done that much soldering, and I thought it'd be a little easier. So don't know where he went, but the gentleman with the hat mentioned, yeah, it is hard to estimate how long things will take. But perf board's a great option too. So what's the next level? What am I here to talk about? It's the idea of making your custom PCB, right? The pièce de résistance. I don't speak French. This is what I'm trying to get to, right? I threw this together in KiCad. Honestly, it took me less time to learn KiCad and lay out this board than it did to try and make this perf board. So, what I'm here to tell you, and you probably already know this, of course, is sometimes it's great to just go straight to one of these. For me, it was easier to do than the perf board. Sierra or GLPCB or all these others, you can often just get them pre-populated. When you order them, you don't even have to build it yourself at home. And in my case, I would have preferred to just order up one that was ready. I just didn't have time for the conference, because I could have been off doing something else. Yeah, it might take a few days to arrive, but I could be working on something else instead of doing up a perf board. Now you might say, but it will take time to set these up, right? Like, I have to make a new project every time. I have to start everything over. So enter KiCad templates. There are already a few templates that are in there. We've got Arduinos. We have some other things that like the BeagleBone and the Edgeberry cartridge. So they already have some templates in KiCad. I said the wrong name for years until I learned it yesterday that it is KiCad. Apologies. There are already some templates in there that you can use that make it easy to work with custom, common designs. So, got my Arduino here. If you want to make a shield for this, very unfortunate that they got the spacing wrong on that header. I was trying to wire up this thing for the breadboard, and I put a header on this perf board, and I went to plug it in. It's like, oh, that's right. I can't just plug my perf board into my Arduino. So common designs are already in there. They also make it really easy to make your own. Went back too far. So it's also actually really easy to make your own templates. And so that's where, what time am I supposed to, because I got started a little late. What time am I supposed to be? Okay. I got a little demo here. So I'm going to bring up KiCad now. And make sure it's on the right screen. So if you start a new project, there is a new project from template option. For me, it's Command T. So here's the templates they were talking about before. And you'll notice that there's this user templates option. So these user templates, I've already got 3 in here, and here's the path. Like, all you really need to do is create a new project in that path, and it'll show up here. So I'm just going to start with this first one. So that board I showed a picture of in the design is based off this template. If I hit OK, it's going to start a new one. It's going to ask me where to put it. I can put it over here in Talk and or KiCon. Give it a quick name, right? And so a couple things to keep in mind. Because it's just a project that got put in that folder, when you make a template, when you make something from this template, it just copies it over with everything inside, including footprints and symbols. So we got footprints here and symbols in here that I made custom. The PMOD connector is just a 2x6 connector, but it has special names on the pins and things like that. And so I wanted to make my own. I made my own symbols and footprint for, the footprint was just so that I could link the right footprint to that header, because the PMOD's always going to be that footprint. And they got copied in too. They were part of the local project, so they got brought in when I made my little project. And so this is going to make it really easy to make little boards that I can plug into my computer, because every time I want to make a new one of those, I can just pull up this template and it will be the right size. Because not only does the schematic come over and got brought up on the wrong screen. Let me, I was afraid of that. Okay, I got my schematic. It already has my header and socket. I can go into my PCB. And so everything in here, everything about the project comes in. So your page settings are, I forgot to fill them in here, but the title and company would have been in there. Anything you have in here, like custom net classes, text variables, everything that was in the original project would come over. So if you want to put your company name in your template, it will bring in to every single one of your projects that you work on. And now I got to bring over PCB editor, right? And this was the key for me, since I'm working on something that I want to be a puzzle piece where everything will just fit in. I want the size to be right every time. I'm going to lay things out differently, so I debated not even putting the traces on this template, but I just wanted to show you that, yes, everything comes over. This board will be the exact size I want, because this edge cut came over from my template. So now if I lay everything out inside this, everything's fine. But what if it doesn't fit? What if it doesn't fit on this one? Well, that's why I have my other template. Right, I've got a 4x1, right? So say I want more connectors. So I'm working on something that's going to be 8 bits of data, 16 bits of address, and 8 bits from some other stuff. The PMOD connector has 12 pins, but 2 are ground, 2 are VCCs, so I only have 8 bits for data. So for my little computer, I want 4 PMODs, right? Or connectors. So I'll hit OK on this one. I think I just put that inside the other folder on accident, but we'll ignore that. Right, this one has more space. I have more space in here. I can lay more things out. So I can make multiple templates. Well, actually, maybe I want a 2x2. So actually, what I could do, just delete those. I'm going to override that lock. This side, this. I don't have graphics selected. I'm going to resize this. I now know what it was like for him during the training yesterday, having to look off to the screen while doing this. It is disorienting. Why am I not seeing what I... Yeah, this is what I want. I want it to be, it's 0.8 inches for one, plus 0.7 for next. There we go. Bring up, oh, okay, we will ignore the zone. Let's just make, so I already had a ground zone in here as well, just to show that the zones come over nicely as well. We're going to ignore that for a moment because it would be a little bit more of a pain to, I had a custom shape on the VCC zone to go around all the pins, so.
It'll update the zones automatically if you press B.
No, yes, but I had to redraw it.
No, it'll stay within the edge.
No, well, since we brought it up, it's these little nubs here on the edge that I'm talking about. Yeah. Yeah, the zone's right. I just didn't, but yeah, that works. So anyway, now this one is a 2x, right? And it's only 2 tall instead of 4. And that is most of what I had to do. If I went back to the schematic, I could fix that up here. Delete these. I don't have all items selected. I'd want to renumber some things and stuff like that, but just to get the idea across. This one that I called test 2, if I come over to here, accidentally stuck it in. No. Where did I put it? Oh, there it is. Okay, so this is the one that we're talking about. If I put it in the 9.0 template folder, it's now here in the template folder along the other ones. If I hit Command T, user templates, it is now in here. It has the same name as the other one because I haven't updated its metadata, but I just saved a KiCad project, put it in the templates folder, and now I have a new template that is a 2x instead of 4. And there it is. So this is a new project based on that one. And that's all it took to make the template, was just a couple minutes to save it and put it in the right spot. The only other things you'll really want to do is you'll come into metadata. This icon shows up in there. This picture, I would want to replace this picture, but I have that here referenced in info HTML. And I'll just come in here and say, this isn't a 4 high, this is a 2 high. I would replace this image and change my title. And now when I go to the user templates, 2x1 12 mode, 12-pin PMOD bus board. So making a template is really quick and easy. If you have something that you want to reuse, design rules, there's some things you learned from the Sierra talk that, there are rules you want to turn on for all your boards, that everything you send to Sierra, you can make a template for everything you send to Sierra that has all these design rules built in. All of that will be brought over. Quick and easy to make. And there is, quick shout out to the team that works on documentation. Graham, I saw him earlier. Thank you again. QR code takes you right to the documentation that explains how to do exactly what I just showed you. That's where I learned it from. It's great. It's there. Everything's reusable. And I plan on getting the sizes all for what I'm working on, I plan on getting a few more prototypes built, and then once I kind of have a feeling for how wide I actually want things, what's wide enough to have enough space, but not so wide that I'm just wasting space. I plan on making some templates, putting them up on GitLab or GitHub, making them available for other people to use, and make their own things as well. I'm planning on making the thing that I showed. Yeah, that was, okay, the animations were a bad idea. You live and you learn. Anyway, this is the first thing, like I said, I plan on making. Want to make a few other things like that, and then make some templates available for other people to use, because I'd like feedback. I'd like other people to get involved and let me know what they think. Let me know what you want to make. I was going to, given time, I was thinking about doing asking you guys for some ideas to throw open a board real quick, but I think we'll call that good enough. Thanks for all the fish, and have a great evening. Any questions? I know I didn't explain everything that well.
So, do you have? I assume you've kind of done surveys of the current landscape for these sorts of reduced complexity single board computers. Do you have things that you feel like should be different from similarly from similar single board computers? I assume I saw in the image, looked like you have a CPU on there and a couple of I/O level shifters, maybe.
Yes.
And so, is that choice then a direct result coming from what you're seeing in other sort of modular systems? Ones I'm thinking of are like the Seed Studios has their small modular system. We saw another modular system at KiCon Europe for the Open Skunk Works has another kind of not the same but similar kind of overlapping. So wondering what your survey of that landscape was.
Of course. So obviously it would be impossible to survey all possibilities, because I would have spent all my time just looking at everything that exists. I eventually had to get to the point where it's like, okay, I've seen enough to know that there's enough people trying to do similar things that obviously there's a need to fill with them, but also none of them are quite like what I'm trying to do, so I think there's still space for what I'm working on. Some things that I was inspired by was, some of Digilent's boards, obviously because I'm using the PMOD. The main thing I'm going for something that I can target multiple levels of the education system, where starting with the computer science, I wanted to make something that was 80s simple. You can look at boards from a computer in the 80s. I forgot to bring mine with me, but I had one from a Mac Classic. You can look at that board and you don't even need a schematic. You can just look at it and you know what everything does because you look up the part numbers, the level shifters and all that, and you can figure it out. That didn't last very long. Many computers that people make these days that are simple as an 80s computer just reuse 80s computer parts, which means you're going to have problems sourcing parts. One of the tips that got mentioned. I actually considered that. I was like, okay, well, if I want a computer that's as simple as an 80s computer, use the 68K. Love that chip. 60K, wonderful. You can't get them. Like, you can get some and then they'll be out.
Are you kidding? You have thousands of them in a Mac.
So some of those are PowerPC, and they're multiple generations. You'd have to harvest them from the boards, but yes, touche. Right, and so sourcing parts would be an issue. And so right now where I ended up with is I'm actually using an FPGA that you can put a simple CPU on an FPGA that will be RISC-V doesn't go down to 8 or 16-bit, and so I'm thinking about, I don't know what else is already out there, or if we make something up ourselves, that's room for feedback. But if you make just something very simple that lets them power it on, and they can write some code for it, and it works. So that's one of the main differences from things like your Feather and your Seed and whatever, where you have an MCU. MCUs are small and cheap. No air quotes on those. They are small and cheap. They're small and cheap, but they're not simple. You've got 5 SPI buses and 8 I2C, and you got all these things they have to set up when you turn them on, and that defeats the purpose of the give this to a computer science student, not a robotics student, not an EE. They don't know what SPI is. They just want to write some code that makes hello world show up on the screen, right? So start with something that I can configure to be super simple for them, and then I realized, well, if it's got FPGAs on it, maybe we could hand this to EE students too, where like you're doing your digital logic, and you could have one class you write all the digital logic to make the computer, and then you hand it to your CS students, and they write the code that gets put on top of it. Or I give it to CS students already loaded, preloaded from the factory, so it can address multiple students. And so that's kind of where I landed right now, where it's something that's configurable, so students of different areas can use it, depending on what's already loaded on it. You want your CPU to run better because now you want it to be out of order or superscale or something. Throw that in your Verilog and you re-upload it, and now you have a better CPU, and now you can go up a level. Like, okay, the first computer didn't have all these fancy tricks. Now that you have an MMU or superscaler, now you have to worry about these problems in your code. And so they can level up the computer and then upgrade their software to follow it, instead of being thrown in the deep end of, you've got an MMU and you have multiple threads and all that. And so that's kind of what informed the decision of how, and then modularity as well. Well, USB didn't exist way back when. It's complicated. Start with a PS2 port, something simple. But if you want USB, you can plug it in on the end. You can add that and then write the software for it. So that answer the question? No?
Thanks, Reed. I had a question too. Thanks so much for your talk. It was really nice. I really like, obviously, the educational focus. I know we talked earlier. You started to answer it at the end there. But I just wanted to hear a little bit more about, where are you going to target maybe first for this curriculum development and the goals? I know you're going to work with maybe a couple schools up there. But which maybe classes or what aspects of classes do you really see this starting to work very well with?
Of course. The first one that I considered and targeted was the idea of the operating system, because that's where your CS student will actually get to where they touch the hardware close enough that the complexity of the hardware affects what they're learning and doing. I don't remember my operating system class terribly well, so I don't remember what all we did, but we did do some things with scheduling and memory management and some stuff like that. And I remember thinking, we're writing this code, but I'm running it on my Mac that I'm just kind of running this dummy code, just kind of get the idea of the algorithm, but I don't actually see it doing anything because it's not really, I'm not really writing a kernel, I'm not really writing an operating system. So my idea is if you have something that's that simple, you can get, okay, here's your 10, 15 pages of data sheet, this is your memory map, write this, it will load on using an SD card or program over USB-C, something like that, some details to work out. And then every line of code that you write will actually run on that and actually output from its VGA port or, emulated VGA back to your CPU. I don't know. They're again, details, figure out. Then, so the operating system is between hardware and software, so I thought it was a good place to start. But you could also use it for like an algorithms class where you want to visualize your algorithms. On something this fast, it doesn't matter if you bubble sort or quick sort. It'll be done in a millisecond. But if you put it on some old slow CPU that's running on an FPGA, your algorithm will make it a lot slower, right? So you can stick it on some simple computer, put it on there, have a little visual output, and oh, that algorithm is really slow on this computer, and you can actually see it, you can feel it. So that's another class I think might start with. But I'm also open for what professors think, like, oh, that would be really good for this class, something that I can customize and make fit the needs of that class.
Awesome. I think your ideas are great. I look forward to seeing
Thank you.
Okay, thank you, Reed.
Thank you all.
So this concludes our final talk for today. We have a reception tonight out where we had lunch. We'll have a chance to mix and mingle, a little more conversation. There'll be some dinner and some refreshments available for you out there. So I look forward to continuing our conversation. Thank you.
Thanks. Did I get you my card? Yeah, I did. All right, thanks. Awesome, thank you. I went from thinking I had too much to thinking I had too little back to like, oh, I went over.
It all works out in the end.
Yeah.
Like these concerns, they smooth out, and I think it went over really well. So
well, thank you. Thanks for having me.
Excellent talk, by the way. So one thing that sparked a memory of mine, so I have a very mediocre computer science. I have a degree in computer memory is always felt.
Yeah, there's a few of them.